可以 started. Hello everyone, welcome to the Mobile AI Workshop 2021. My name is Andrei Ignatov. You can also see Radu Timovta. Radu Timovta, can you see something?
Welcome to this event, and I think that the best is to start the schedule because we have 9 hours ahead. And the first talk today is provided by Andrei. So I think.
Okay, just a second. Good. First of all, several organizational notes. Right now, the main event happens on Zoom at CVPR, and you can find the corresponding link in CVPR workshop landing page. The event is also streamed on YouTube. Welcome everyone watching us there. And the majority of recordings and slides will also be available on our YouTube channel. Each talk will be followed by a short Q&A session. Zoom participants can run your questions in the chat. YouTube visitors can post your questions on the forum. And after each talk, we'll be checking this forum. And if there are some questions, we'll transfer them to the speaker. But note that there is approximately a 1 minute delay between the actual event and the YouTube stream. Therefore, if you are writing some questions, try to do this in advance. So deployment on mobile devices. Why do we need it? On this slide, you can see lots of different tasks that are currently running on mobile devices. These tasks are critical. They are related to various problems such as photo and video enhancement, image categorization, biometric data processing, voice enhancement, adaptive power management. And the most important thing is that we can solve all these tasks efficiently with deployment-based solutions. And the resultant solutions always usually and significantly outperform the classical approaches. So then the question is, how can we run and how can we deploy the resulting models, the resulting machine learning models on the actual hardware? And in case of normal tasks, in case of normal development for desktops, for server systems, everything is actually super simple. Because our task is to get good numerical and visual results. The runtime is not that critical. Power consumption is also, it's okay as long as the model fits into GPU memory. What happens if we want to develop something for mobile devices? First of all, we still want to get good numerical and visual results, because who doesn't? Next, the runtime usually should be around milliseconds. The majority of tasks running on mobile devices, they require real-time data processing. And even for tasks that do not require this, the runtime should also be quite small because large inference times will result in device overheating to fast battery drain, and therefore the model should be fast. RAM consumption for mobile devices, a model that is using 1 GB of RAM, it is huge. Model that is using half a gigabyte of RAM, it's okay, but it won't run on lots of specialized hardware. 100 megabytes of RAM, it's already good. It will be compatible with the majority of AI accelerators. And the most important thing is that these restrictions, they refer to any problem, not only to image classification, but if you want to perform upstreaming of your video to 8K resolution, here are the same constraints. And the final thing that we want to address is to make sure that our solutions, the developed solutions, are compatible with mobile AI accelerators so that they can run on NPUs, DSPs, GPUs, so on. So if you're interested on how to deploy neural networks on mobile hardware, how to optimize them for edge devices, and how to run them on dedicated mobile AI accelerators, then welcome to the Mobile AI 2021 workshop. First of all, I will briefly introduce the workshop schedule. At the beginning, I'll provide a brief introductory talk that will provide you with all basics related to deep learning on mobile devices. I'll tell you pretty much all basic information about mobile libraries that are used for running neural networks on mobile devices. I will tell you about mobile hardware, about several optimizations that are key for on-device inference, and besides that, I will tell you how to run any TensorFlow or PyTorch neural network on your mobile device in less than 5 minutes. After this presentation, there will be several several invited talks from all major SoC vendors, and the guys will pretty much educate you how to efficiently run models on their hardware. They will tell you about some particularities, some additional optimizations. So it will be pretty much a good tutorial telling you what is the best way to convert and to deploy your solutions on the hardware from each vendor. Besides that, in this workshop, we'll present the results of several mobile AI challenges. In these challenges, the participants were solving several real-world tasks related to mobile devices, and which is more importantly, all these tasks were obtained solutions were evaluated on real mobile hardware. So we had Learn Smartphone ISP challenge, where the runtime of the models was evaluated on MediaTek Dimensity APUs. We had Image Denoising challenge with evaluation on Mali Exynos GPUs. Image Super Resolution challenge with evaluation on Synaptics Smart TV platform video super resolution, where the models were running on Qualcomm GPUs. Depth estimation, where the models were evaluated on the Raspberry Pi 4 device, and camera scene detection with evaluation on Apple Bionic chipset. So the results, these challenges and the results will be presented during this event. And besides that, you will also see the presentations of several interesting accepted papers, accepted workshop papers, where they also developed some efficient models for on-device inference. So let's begin, and I will first start with a short introductory talk that will tell you in 5 minutes how to run any TensorFlow or PyTorch model on your own Android smartphone. So if you think that this is impossible and you do not believe me, just right now pick up your favorite deep learning model and pick up your favorite smartphone. And in 5 minutes, you'll be able to run this model on the smartphone. So first of all, general overview. If you want to run something on mobile devices, first you need to train the model, and the good news is that generally you don't need to do any modifications here. So you're using just standard TensorFlow or PyTorch framework, define your model as usual, train this model as usual, and finally you're getting your neural network that can perform some tasks. After that, we need to do the 2 steps. First of all, we need to export this model for mobile inference. How to do this? If you are using TensorFlow, if you are using Keras, then this can be done in 3 lines of code. So first of all, you define your model architecture, and then initializing TF-Lite converter, passing this model to TF-Lite converter, running converter.convert, and saving the resulting model to your hard drive. And so only 3 lines of code, and the model is exported from device inference. And here you can see the full example showing how to initialize and export unit model, performing image super resolution task. If you are using plain TensorFlow, then the situation is exactly the same. But instead of passing your model, you need to pass your session, input, and output tensor. And after that, 2 lines of code, and the model is saved. In case of PyTorch, everything is a little bit trickier. So in general, we do not recommend you using PyTorch right now for mobile development, but if you still want to do this, then this code will do the trick. You initializing your model, then converting it to ONNX format, then loading the resulting ONNX model and converting it to TensorFlow, and then finally the same 3 lines of code, converting the resulting file to for on-device inference. So that's it. If you to perform the second step, in general, you can just use this the provided code snippets, and after that, the model is ready for on-device inference. And then the last question is how to run the exported model on your smartphone. Everything here is also quite simple. First of all, connect your smartphone to your computer, copy the resulting model.tflite file to the download folder of your smartphone. For instance, here you can see Nokia 9. Just copy this model to download folder. Then go to aibenchmark.com/download and install AI Benchmark mobile application. And after running the standard tests, you will see this screen. Then press on the promote button, select the custom model tab, select the desired acceleration option, whether you want to run this model on CPU, on GPU, on NPU, or with other acceleration options. Press run, and here you will see the runtime of this architecture. You'll see its average latency, you will see initialization time, you will see memory consumption, so pretty much all information that you need. So you see that it's really super simple. Just first of all, train your model as usual, then convert it using the provided code, and then run it. And more importantly, you can run it on any Android device, and not only a smartphone, it can be even a smart TV platform or any other hardware. It's just important that it's Android. That's it. And for those who still don't think, for those who think that this is impossible, just after this presentation or after this event, just try to follow the steps and you will understand that it's actually doable and there are nothing complicated here. And why did I tell you this at the very beginning? Because right now I hope that you all realize that on-device inference and on development for mobile devices is not something that is far away from you, that is not something that is extremely, that is impossible, that requires like days of Android coding. And yeah, so in general, for almost any architecture, you can just spend 2 minutes, and after that, you can run it on your smartphone, and you'll see its result on real hardware. You'll see its results on NPU, on DSP, on GPU, whatever option you prefer. So, and by this, I also hope that right now you realize that the next presentation is not something completely theoretical. No, it just refers to you, and it will tell you pretty much the particularities of each step, because the provided information is very general, but each step required for on-device inference has its own tricks, has its own particularities, and the rest of this presentation and the presentations of smartphone vendors, they will basically tell you what are the best options for exporting your model, for running your model, and so on. So let's move to the main part of the presentation. So to run some model on mobile device, we need two key components, software and hardware. We will start with software, and to understand what options do we have now, how we can accelerate the models, and why it happens like it happens, we'll first travel a little bit back in time. We'll go to year 2015, and if you wanted to train some model in 2015, train some deep learning architecture, then you pretty much had to use one of the four deep learning libraries, either Theano, or Caffe, or Torch, or TensorFlow. Note that TensorFlow was just launched at the end of 2015, and therefore it was not yet that popular. And suppose that you trained your model, trained your neural network, and now you want to convert it for on-device inference. Can you do it with these libraries? The answer is no. Neither of these libraries were supporting on-device inference, and there were some unofficial ports, but they were pretty much non-functional. Only partial support was offered by TensorFlow, but as I mentioned, TensorFlow at the time was not really popular. It was just launched. And therefore, usually, the majority of guys were still using Theano, Caffe, or Torch. Now, just realize that all smartphone vendors, all SoC vendors, they understood that they can solve these problems that I already mentioned at the very beginning of the presentation with deep learning models. And then they can get much better solutions. And more importantly, by deploying the solutions on mobile devices, they can provide the users with a better user experience. And of course, here we go to the question how to run the models. And since there was no standard option how to do this, how to run neural networks on all devices, the solution that was created by vendors was simple. Each vendor created its own SDK. So Qualcomm in 2016 introduced Snapdragon Neural Processing Engine, Snappy SDK. Huawei next year introduced Hiya SDK. MediaTek introduced NeuroPilot SDK, Samsung Neural Add-in SDK, and Unisoc Uni SDK. So with these SDKs, it was possible to run neural networks on devices, and it was also possible to achieve acceleration on special hardware. And what is the general workflow when using these SDKs? First of all, you train deep learning model with some framework like TensorFlow, Caffe, Torch. Then you use this SDK to convert the resulting model to a special format defined by this SDK. And then you again use this SDK to run this model. And everything is in general great, apart from one thing. Each framework supports only hardware from the corresponding vendor. What does this mean? This means that if you develop some model with snappy, then you won't be able to run the resultant solution on all other platforms. And the same goes for Huawei. Model developed with high won't run on anything else, and so on. So if you decided, if you were going to use SDKs, and if you wanted to achieve acceleration on different platforms, then you pretty much had to integrate 5 different SDKs into your application. You had to convert your models pretty much 5 times to get models supported by these SDKs, and also integrate the resulting models in your library in your application. And this was only the beginning, because as soon as you start using this SDKs, you will realize that they support slightly different set of operators, set of layers. And to achieve good acceleration, you pretty much need to tune your model for each SDK separately. So at the end, besides using 5 SDKs, 5 models, you might also need to develop 5 different architectures, or fine-tuned your model for 5 different vendors, so that it runs fast, there are no problems during conversion, during the runtime, and so on. And this option is, of course, good if you're a smartphone vendor. So for instance, you're Nokia, you want to develop some application for your own device. And in this case, you just use, for instance, Snappy, design your model, create the application, and that's it. But if you are developing an application that is available for different platforms, this option will actually require you to spend even several months. It might be even not just weeks. It might take several months to optimize your architecture for all platforms, to do all conversion, to integrate everything, and to make sure that everything works as it should work. And of course, this solution was not optimal, and everyone was looking for something that can be used for inference on any hardware. And this solution appeared at the end of 2015, and this solution was called TensorFlow Mobile. TensorFlow Mobile was pretty much a full port of TensorFlow for ARM devices. It was even able to run standard TensorFlow PB files, PB models. You didn't need to do any conversion, and it finally supported all smartphones, all Android devices. And the only problem with this library is that it was able to run them only on CPU. And at the end of 2015, the end of 2016, vendors started to introduce specialized silicon, specialized AI accelerators for neural networks. And of course, everyone wanted to use them to speed up the inference, to decrease memory consumption, to decrease power consumption. And therefore, TensorFlow Mobile, it was an interesting option, but it had a really critical issue. And this is the main reason why TensorFlow Mobile was killed in favor of TensorFlow Lite. What do you need to understand about TensorFlow Lite is that this is not a TensorFlow port. TensorFlow Lite was developed from scratch, and at the beginning it supported only a subset of TensorFlow ops. And the general idea is that whenever we're adding some new operator, some new layer to TensorFlow Lite, we first optimize it for on-device inference. We optimize kernels so that the memory consumption is low, latency is also low, and so on. And TensorFlow Lite, same as TensorFlow Mobile, it supported all Android devices. And I should mention that at the beginning it had lots of critical issues, including issues with CPU runtime, but its development was really rapid. And you can see on the slide that during the last 3 years, CPU backend, TensorFlow Lite CPU backend was improved by pretty much 3 times. So right now you can run almost all models will run 3 times faster than at the very beginning. And therefore, right now TensorFlow Lite de facto became a standard for on-device inference for mobile neural networks deployment. And if you want to use TensorFlow Mobile in your application, everything is also simple. So this code, you should already be able to recognize it. This code shows you how to convert your standard TensorFlow model to TF-Lite format. Again, TF-Lite converter, converting your model, getting the resulting file. And if you want to integrate TensorFlow Lite into your application, everything is also very straightforward. So you initialize the TensorFlow Lite interpreter, passing inference options to this interpreter, defining your input and output tensors, and then pretty much running the inference. And the results will be stored in your output tensor. So this is how to work with TensorFlow Lite. And honestly speaking, no one would really care about TensorFlow Lite at that time, at least at the time when it was released, if it was only running on CPU. But the main advantage of TensorFlow Lite at the time is that with TensorFlow Lite, it was finally possible to accelerate standard models on smartphone AI accelerators. And how this became possible? So recall the situation with SDKs. So with SDKs, we pretty much need to add the corresponding SDK to the application because it contains drivers needed to access the corresponding NPU, DSP, or GPU. What if we move all these drivers from these SDKs to device firmware, so that whenever you get device, it already has these drivers already present in Android operating system? This is good, but what if we also make a unified API for communicating with these drivers, so that you don't, whatever platform you have, whether if the phone is from Samsung, from Qualcomm, from MediaTek, from Huawei, you can just use the same API to pass pass some operators to communicate with these drivers and with the corresponding hardware. And finally, what if we make all machine learning libraries to interact with NPUs, DSPs, and GSPs not directly, but through this API? In this case, these mobile machine learning libraries, they would never longer need to have some codes, special codes needed to access NPUs, DSPs, and GPUs. No, they can just run all computations through the same API, and everything becomes very simple and straightforward. So your machine learning library, mobile machine learning library, just parses your model and uses this API for accelerating it on NPUs, DSPs, and GPUs. So, and right now I have basically described you the idea and the structure of Android Neural Networks API. So Android Neural Networks API was introduced in Android 8.1, and it is pretty much an intermediary layer between high-level machine learning libraries and the actual AI hardware, AI accelerators. And how it generally works. Your machine learning library, for instance, it's TensorFlow Lite, when you load your model, instead of running this model on CPU, it just transfers this model to Android Neural Networks runtime. And this neural networks runtime is just checks whether there is some registered hardware that can be used for accelerating this model, that can efficiently run either this model or some operators or layers and so on. If it finds some hardware, then it passes the model to the silicon, it runs the inference and returns back the results. And the results are then propagated back to your machine learning library. You're getting back the results. And in this case, you basically do not even need to know anything about the actual AI accelerators present on your device. You don't need to use any special codes. You don't need to add any special SDKs. You just tell inside your library that just using an API, then the model is transferred to an API and executed using the most efficient way. And how to use an API in practice? You'll be surprised, but you can do this in 2 lines of code. So in the previous example, TF-Lite interpreter was initialized using 2 lines of code, and now you just need 2 extra lines of code where you define an API delegate and then passing this delegate to your TF-Lite interpreter. And after that, the interpreter, instead of running your model on CPU, it will try to accelerate it on available DSPs, NPUs, or GPUs. And the general idea is very good. What you really need to understand is that Android Neural Networks API, it cannot directly communicate with AI accelerators. Android Neural Networks API, it can pretty much communicate only with an NAPI drivers that each vendor develops for their accelerator. And despite the fact that, yes, Android Neural Networks API and NAPI is available in every smartphone with Android 8.1 and above, the actual acceleration depends on the drivers designed by vendors. And if these drivers are missing, it won't be possible to accelerate these models on some AI accelerators, even if they are available, because an NAPI will just simply will not see them. And vendor NN drivers, vendor NN API drivers is something that is super critical, and that pretty much defines the speed, defines the problems, defines the particularities of the results that you'll be getting on each device. And again, if NN API drivers, if these drivers are missing, there won't be any acceleration, even if device has some special NPU, DSP, GPU, whatever. And if these drivers contain some issues, if there are some bugs in these drivers, you will also be getting issues when accelerating the models, and an NAPI itself will not save you. An NAPI can do nothing here. So what is critical is an NAPI drivers developed by SoC vendors for their particular hardware. The second thing, if you decide to use an NAPI, you need to understand that there exists a sort of fragmentation. So an NAPI drivers, this is not something that is fixed, and they are developed throughout the entire chipset lifecycle. So at the beginning, when the chipset is just launched, usually they contain some critical bugs, some functionality is missing, then this functionality is added, performance is improved, in new Android version, some new features and support for new ops is added, and generally it evolves. And sometimes it evolves like significantly. And till Android 12, it was not possible to update an API driver separately. You could update them only with full firmware update. And the entire update procedure was looking as follows. So first, SoC vendor develops new API drivers HAL, and then it sends it to smartphone vendors. Smartphone vendor tests it and integrates into new phone's firmware, and then sends this firmware to the end user. And as you know, with mid-range and with low-end devices, there are almost always issues with updates. Sometimes devices are updated quite late, sometimes they're not updated at all, and even with flagship devices, sometimes these issues can occur. So in this case, you need to understand that if you have two different devices with exactly the same hardware, then on these devices, you might be getting absolutely different results depending on an HAL version that is present in the firmware. And therefore, if you decide to use an API for development, just take this into account. This doesn't mean that you should not use an API. No, an API is a very useful thing, but just make sure that if you want to run some model on devices of your customers, of your users, then that the results of your model on their devices might be different from the results that you are getting on your own test phones. And make sure that you add additional sanity checks, that you add some backup options in case there are some issues with inference, in case something is crashing and so on. And the good news is that since Android 12, and an API drivers, at least for some vendors, they will be updated separately through Google Play services. And more information about this will be provided in today's presentation from Google. They will tell you how this will be achieved and what devices are eligible for this update. And the last thing that you should understand is operator coverage. So as you already know, TensorFlow Lite supports only a subset of normal TensorFlow operators. And an API in its turn supports a subset of TensorFlow Lite operators, and the actual NN drivers, NN HAL, it also supports a subset of NN API operators. Why? Because it is with an API, you can accelerate only operators supported by an API. Even if your NPU can accelerate some other operator, but it is not present in an API, it's not possible to run it and to accelerate it on this NPU. And then the good question is how many ops are supported by an API? And the answer is that at least in Android 11, there are already almost 101 operators that are defined in an API, and that can be technically accelerated. And what does this mean? This means that actually this is quite a lot. This means that you wouldn't have any major issues when running some standard classification models, when running some standard vision-based models. You might run into problems only when using some customized designs, when using some natural language processing models, and so on. And then the question is, what will happen if what happens if you have some custom operator not supported by an API, and NPU actually can accelerate this operator? Will it be possible to actually run the entire model on this NPU with full acceleration? And the answer is yes, it will be possible, and you can do this with TensorFlow light delegates. What is TensorFlow light delegate? TensorFlow light delegate is pretty much a custom library that can be developed by SoC vendors to access their hardware, the AI accelerators directly without using an API. And this delegate can be integrated together with TensorFlow Lite, and in this case, the inference performs the inference is performed through this delegate. So the workflow looks as follows: when running your when loading and running your model, for instance, with TensorFlow Lite, instead of telling TF-Lite to use an API, you just tell TF-Lite to use some special delegate, and then this model, all supported operators will be transferred to this delegate, and this delegate can just directly run this model on NPU, DSP, or GPU. And what are the advantages of using delegates? First of all, delegates are independent of Android operating system. So you integrate these delegates directly in your application. And in this case, you can use the latest version, the latest available version, and you can make sure that on all devices you'll be getting the best possible speed, the best possible results, and the largest possible support. And besides that, with these delegates, it's possible to overcome different technical and API limitations. For instance, yes, in this delegate, you can implement some additional operators if they are supported by NPU, DSP, or GPU. These delegates often lead to slightly better performance than when using an API. And besides that, you can also add support for legacy devices. For instance, you can accelerate models on devices running Android 5, 6, 7, where there wasn't even an API, where an API does not exist actually. And using these delegates is also super simple. You're just, instead of passing an API option to TF-Lite, in an API delegate to TF-Lite options, you are initializing your custom delegate and passing this delegate instead. So what are the main delegates that you can use in your application? The first one and the most important one is TensorFlow Lite GPU delegate. This delegate can accelerate pretty much any model on any GPU supporting OpenCL or OpenGL. So this requirements pretty much any mobile GPU released in the past 5-7 years. It satisfies this condition, so you pretty much can run your neural network on any mobile GPU. This delegate provides very good acceleration, and in some cases, it can reach even to the level of specialized NPUs. And besides that, this delegate can run really huge models consuming several gigabytes of RAM. And this is extremely important if you want to run some heavy vision models, because you won't be able to run them on NPUs because their RAM size is often limited, but you'll be able to run them on GPUs with custom delegates. The issues with this delegate, pretty much there are two major problems. First of all, the issues with accuracy. So we saw that for some models and some devices, the results might be almost random. It's possible to fix this problem by enabling high precision mode, but in this case, you will also lose in the runtime. The runtime will become larger. And the second is that TF-Lite GPU delegate is currently not really optimized for PowerVR graphics. So it will be possible to run the majority of models on PowerVR GPUs, but the results would be far away from what you would expect. And so this is the main information. And another important aspect here is operator coverage. Since TensorFlow Lite, and TensorFlow Lite GPU delegates are developed pretty much by TensorFlow team, there is a synergy between their development, and all operators introduced in TensorFlow, all new versions of each operator, they shortly appear in TensorFlow Lite GPU delegate and shortly become supported by TF-Lite GPU delegate. So right now, it provides the largest OPS support compared to an API and compared to all other delegates. So whatever layer you have, usually if it is not supported by TF-Lite GPU delegates, then it is not supported by anything else, but by any other option, acceleration option. So TF-Lite delegate is actually a very, very, very good starting point if you want to accelerate your models on standard mobile hardware. What are the other options? Another option, important option, is a Qualcomm Hexagon TF-Lite delegate. It allows to access Hexagon DSPs directly and run neural networks on them. And this delegate usually it offers better op support and coverage compared to the corresponding API drivers, and it often leads to much better runtime results. For instance, you can see here that the runtime of the Inception V3 model improves by 20 and 25% on the Snapdragon 845 and 855 chipsets having the latest NNAPI hub. And the only downside is that on some devices, external access to Hexagon DSPs is blocked. For instance, you won't be able to use it on all Google Pixel phones, on some OnePlus phones, and it will just tell you that the phone is not compatible. So in general, yes. So if you want to run something on TF-Lite on Qualcomm DSPs, then you should start with TF-Lite Hexagon delegate at least now. What are the other important? Just a second. Okay. What are the other important delegates that you should be aware of? The one is something add-in delegates that can be used for accelerating floating point and quantized models on high-end and mid-range XML GPUs. MediaTek neural delegate used for accelerating models on Dimensity NPUs. And Apple CoreML delegate. TF-Lite is also available for iOS platform. And if you don't want to use Apple software, and if you still want to run your TF-Lite model on Apple's neural engine, then this is an option for you, and you will be able to achieve quite good inference results. The only problem will be with quantized models. So, and you remember the slide I demonstrated you at the very beginning. So, and I told you that you can use different options for accelerating your models, and right now you can actually recognize them. So this is a standard CPU backend. This is TF-Lite GPU delegate. This is Android Neural Networks API. This is Hexagon add-in and MediaTek neural delegates. And the last thing that I want to say here is that besides TensorFlow Lite, there also exists PyTorch mobile library. It was introduced by Facebook around 1 year ago. And I know that many of you are actually huge PyTorch fans. So if you want to export and run PyTorch model on mobile CPUs, this option is for you. You can do this in case of CPU inference. The results are good. Operator coverage is also good, and there are no major issues here. The problem comes if you want to accelerate your model on some hardware, and here, bad news. PyTorch Mobile can accelerate models only through an API. This support is experimental, and well, it's actually not usable right now. So you'll run into issues while converting the models, while trying to accelerate them on actual devices, and this is something that is not ready. And what we should also mention here is that with TensorFlow Lite, the situation was pretty much the same 2 years ago. But during the last 2 years, TF-Lite evolved rapidly, and lots of issues were fixed, and right now it's actually usable and it provides very good results. And we really hope that Facebook will be able to do the same with PyTorch Mobile, and that in 1-2 years we'll be able to tell you that, okay, if you want to run something on Android smartphones, just pick up PyTorch or TF-Lite, whatever you prefer. But unfortunately, we cannot say this right now. So this was pretty much all about mobile machine learning libraries. And right now we are moving to the second important topic, to optimizations that are required for on-device inference. So these optimizations can be split into two different parts. The first one is architectural optimizations. It's pretty much about using smaller convolutional filters, using fewer feature maps, processing images at lower scales, and so on. And these topics will be mainly covered during the next challenge presentations and presentations of the top solutions achieved in each competition. What I really want to talk right now is about different inference types. So I just curious if you really ever thought of what is the exact inference type that you are using when training your neural network, training your deep neural networks on some standard deployment hardware or with standard libraries. So what is the exact numerical format that you are using, for instance, when training your model with TensorFlow or PyTorch? If you don't know the answer, and if these 4 names tells you pretty much nothing, then you should really concentrate on the next few slides, because this information is very, very, very critical for randomized inference. So whenever you train your model with TensorFlow, PyTorch, or some other deployment libraries, you almost always get floating point 32 model that is providing an accuracy of 7-8 digits after decimal point. Why not using more precise options? Because they are not important for deploying inference and training, for deployment training. Using less precise options like floating point 16 format, usually they lead to problems with gradient updates, and therefore they are rarely used in practice. So therefore, if you're not enabling some special modes, some different modes, then you will get floating point 32 model. And as I mentioned, FP32 provides good accuracy, and it is critical for training your neural network. But this accuracy is actually excessive when you want to to perform inference. And which is more importantly, FP32 format is not supported pretty much by any NPU. So you cannot just run FP32 model on NPU, DSP, or some other specialized hardware, except for GPUs where this option is available. Instead, you need to use FP16 floating point format. So it offers an accuracy of 3 digits after decimal point, and this accuracy is enough for the majority of tasks, for instance, for role classification, recognition, for the majority of image processing problems, and for the majority of natural language processing tasks. So in this case, you won't see the difference between the results. And FP16 format, inference format, is faster, it consumes less memory, and it is supported by all GPUs, it is supported by many NPUs. And the good news is that FP32 to FP16 conversion happens automatically when you are using mobile libraries. So you do not need to do any extra conversion, any extra modification. No, everything happens. You need to just to enable the corresponding option, to make sure that the corresponding option is enabled. That, for instance, in TF-Lite, there is an option of use and set allow FP16 format, and you set this option to true, and in TF-Lite GPU delegate, you just, for instance, use set precision also allow true. And in this case, your original floating point 32 model will be automatically converted to FP16 model and executed using this format. And in this case, you'll chain speed, and you'll get a decreased RAM consumption. So never ever try to use FP32 format unless this is really required, unless its accuracy is really required for a task. So FP16 format is good, but what if we go further? And what if instead of 16-bit floating point values, floating point models weights will use integer models and 8-bit integers? And this is possible, and this is called quantization, quantized inference, and model quantization. So in case of quantization, we are converting our original floating point model to int8 format, and int8 format is these are 8-bit integers. In case of unsigned inference and signed models, they align between 0 and 255. In case of signed, they align from -128 to 127. So how this conversion actually happens? So your original floating point weights, they can pretty much lie between -2 billion and 2 billion. In practice, they align in much more narrow interval, their zero-centered interval, and you are first identifying what is the interval in which the majority of weights are located. And then in the simplest case, you can even linearly map these weights to 0 to 255 interval, to your new interval. And which is more importantly, you are mapping each floating point weight to an integer. So floating point, after this mapping, floating point variables weights are no longer allowed. And in this case, yes, originally you had floating point interval from Rmin to Rmax, and after performing the mapping, you're getting new weights lying between 0 and 255, and all weights, they are actually integer weights. And therefore, yes, if originally the distribution of your weights was continuous, then after performing quantization, it becomes discrete, because each weights located in some vicinity, they map to exactly the same integer value. And if you are performing the quantization, you're also getting back your all weights are also restored back to only one value. So this is a very general idea of how quantization works. In practice, there are several different tricks. There are several optimizations. There are also some particularities referred to integer-only arithmetics. We'll not cover it right now. For you, right now, it's just important to understand how, in general, quantization works. And let's now talk about advantages of quantized inference. First of all, there are lots of NPUs that can accelerate only integer models. For instance, NPUs found in Exynos chipset or Hexagon DSPs from Qualcomm, they cannot run floating point models, only integers, only integer models. And therefore, if you want to accelerate your neural networks on these platforms, you need to quantize them. You don't have any other option. Besides that, after quantization, your model becomes smaller, the inference becomes faster, and RAM consumption faster, power efficiency improves, and so on. So only advantages. And I guess that some of you already understand that if we are gaining so much, we should also lose somewhere. And of course, we are losing, and we are losing in accuracy. Because this drastic bit weights reduction from 32 or 16-bit floating point weights, floating point variables weights to 8-bit integers weights results in quite heavy precision loss. And besides that, don't forget that if originally, for instance, if you had a floating point model, image classification, and it was for each class it was producing the probabilities lying between 0 and 1, and this your floating point probabilities, then after conversion, it will actually output integer values, lying between 0 and 255. And the good news is that quantization, it actually works quite good for classification tasks and in general for threshold-based problems. So in this case, sometimes there is even no accuracy, sometimes the loss is very minimal, so for classification tasks, no problems. For image processing tasks, it works also if the task is simple and mainly residual learning based, which means that you originally have some image, and for instance, you want to add some details, some missing components, some missing texture. And in this case, it's possible to achieve more or less good results. So don't expect that there won't be any performance loss. No, there will be some drops in the accuracy, in the precision, but this drop will not be extremely heavy, and it will be possible to get some usable results. Image quantization will not work for more complex tasks. Performing heavy image manipulations, it will almost never work. Well, it will rarely work for natural language processing tasks, at least right now. And besides that, in some cases, you won't be able even to pass your input data to a model in case of vision-based models, in case of vision-based tasks. For instance, if you want to process data coming from your smartphone camera, then usually this is 10-bit or 12-bit data. And the resulting 8-bit model will not be able actually to accept this data because it cannot accept anything that which bit cannot accept tensors which bit width is higher than 8 bits. So, and this is pretty much the main limitation of quantization. So again, for a quick summary, if you have classification model, quantize it, and most likely there won't be any troubles. If you have some simple image processing model, you can try to quantize it, but always check the resulting accuracy. And in case of more complex tasks, in case of natural language processing problems, if you want to quantize it, be aware that most likely the resulting accuracy will be very low, so the drop might be huge. And always check the actual outputs of the quantized model so that you do not get surprises later. So now we understood the benefits and limitations of using quantized inference. Then the question is how to quantize the model. So you have originally the floating point 32 architecture trained with TensorFlow, PyTorch. Here we'll consider only TensorFlow, and now we want to quantize it. TensorFlow offers, in general, 4 different options. The first option is dynamic range quantization. It will not help. After applying this option, you will pretty much get floating point model with quantized weights. And during inference, these weights will also be restored, mapped to floating point values, and you are pretty much again getting full floating point architecture, full floating point model and floating point inference. And in this case, you won't be able to run this model on integer-only DSPs and NPUs. The second option is called full integer quantization, and its name is also a little bit misleading, because after performing this quantization, the inputs and the outputs will be still quantized, and some operators might also be, the inputs and outputs will be floating point, and some operators might also remain floating point operators. And in this case, if you have an integer-only hardware, you will have problems with accelerating this model on this hardware. And the option that will definitely work is the third one, integer-only quantization. In this case, yes, the entire model will be fully quantized, including inputs and outputs, and you'll be able to accelerate this model on any int8-only NPU. There is also another option called quantized aware training, and as you might guess, it requires to retrain your model. And during this retraining, TensorFlow will automatically compute quantization statistics and apply some additional optimizations. And in general, this is the best option that you can use for getting quantized model, but again, it requires retraining. So for different options, if you want to accelerate your model on dedicated int8 NPUs, then you need to use the third option or the fourth option. So, and the last inference type that I want to mention is int16 inference. It's same as in case of int8 inference. You're also using integers, but here you're using 16-bit integers, and therefore the dynamic range becomes much larger. And because of this, the majority of problems related to accuracy are solved. The only problem with this inference type is that right now it's not really supported by TensorFlow Lite. TensorFlow Lite offers only one option, and by using this option, you'll get a model that will not run on almost anything, including CPUs. So in this case, I mentioned it just because int16 is something very interesting, and in some sense, it's a future of on-device inference for complex computer vision tasks, for NLP tasks, and for some other tasks that require high precision. But this is a feature that we don't have right now. This is a feature that might be available like in 1-2 years. But you should already be aware that there exists some format, and it might help you to solve the accuracy problems and accuracy issues. And moreover, this format is already supported by several mobile NPUs. So right now we also understood how to, what are the different inference types and how in general we should optimize our model for on-device inference when it's retrained. And then the good question is, what is the hardware that can be used for this inference? So when we are running neural networks, so as you know, many vendors created their own solutions. And when running neural networks, what do we really need? Well, in general, we need very fast matrix and vector operators, because all convolutions or fully connected layers, this is pretty much about matrix and vector calculations. We also need to have some hardware that is very power efficient, because when running neural networks on general purpose hardware, power consumption is just huge, it's dramatic. And also with neural networks, we generally have a restricted set of different operators and layers. So in general, the hardware should be quite specialized. And all vendors, when they realize that they need to run their models fast, when they need to also think about power consumption, they introduce their own solutions for accelerating neural networks. These solutions have different names, different branding. In some cases, they are called DSPs, and in some cases, NPUs, CVPRs, TPUs, and so on. What you need to understand here is that this naming tells you nothing about the exact performance of the hardware. So we cannot say that DSP is better than NPU, or vice versa, that NPU is better than DSP. This is pretty much just marketing information, marketing branding. That's it. And moreover, the majority of current NPUs, their design is largely based on DSP architectures, on DSP hardware, because DSP The idea of DSPs is also that they have some hardware blocks for multiply accumulate operators, and they can process multiple data in parallel due to some specific instructions. And this is exactly what was needed for neural networks. And therefore, yes, many custom AI accelerators were derived from DSPs. There were also some accelerators that were derived from GPUs and TPUs, from GPUs and FPGAs. But yeah, in general, do not be confused by different naming. It's just, in the simplest case, you might just assume that these are all very customized DSPs designed for, fine-tuned for neural networks, and you're just using these DSPs on all mobile devices. And again, when first looking at this different naming, and here I just presented the first accelerators presented by Chvendra. As a matter of fact, there are many more options. You might also get confused of what are actually which hardware can be used for which inference, and so on. So in the next 5 slides, I will pretty much clarify everything, because it's actually quite simple. If you are running neural networks on Qualcomm chipsets, then you have hexagon DSPs. Hexagon DSPs can accelerate quantized neural networks, only quantized. They are not compatible with floating point models. And to access these DSPs, you can use either an API or already mentioned hexagon TFI delegate. And these DSPs can be found in these chipsets. So whenever you want to accelerate your model on Qualcomm chipsets, make sure that this model is quantized and that you are using the appropriate option for accessing DSPs. If you want to run your original floating point model, then you need to accelerate it on GPUs. You can do this either with TFI GPU delegate or with an API. And yeah, in general, this is also a good option. And for Qualcomm, this is the only option to run floating point models. MediaTek chipsets. In MediaTek, you can find 3 generations of APUs. APU is AI processing unit, is abbreviation for AI processing unit. The 3rd generation APU supports both floating point and quantized models. You can access it either through an API or through Neuron TFI delegate, and it can be found in almost all chipsets from the Dimensity series. 2nd generation APU, it also supports both quantized and floating point inference, and it can be accessed through an API. So just select an API option, and your model will be accelerated on the CPU. And it can be found in Helio P90 and P95 SoCs. And the 3rd generation APU supports int 8 inference only. It's accessible through an API, and it can be found in these chipsets. So simple. Huawei chipsets. In high-end and mid-range Huawei SoCs, you can find NPUs with DaVinci architecture developed using in-house Huawei design. These NPUs can run both integer and floating point models. They're accessible only through an API and can be found in these chipsets. You can also find NPUs in older Kirin SoCs in Kirin 970 and 980. This NPU was developed by Capricorn, and it supports only floating point inference. And this NPU is also accessible only through an API. Samsung chipsets NPUs are accessible only in 2 models, in Exynos 2100 and in Exynos 990. But on Exynos 990, you'll be able to accelerate only some models, only some particular architectures. These NPUs are support only integer inference and can be accessible through an API. For all other devices and for all other Samsung chipsets and devices, you can use just GPU acceleration. You can use either add-on delegate that is supporting these SoCs or an API or TFI GPU delegate. And then you'll be able to accelerate both integer and floating point models. Finally, if you find a device with Unisoc chipset, with a Unisoc SoC, then there are 2 chipsets that you can pretty much get access to. This is Unisoc Tiger T770 and T710. The first one has an NPU that supports quantized inference only. The second one has NPU supporting both integer and floating point inference. And both NPUs are accessible from an API. And finally, you can also find Edge TPU in Google Pixel 4 device. It can accelerate quantized models only, and is also accessible through an API. And you'll be surprised, but that is it. This is pretty much the entire classification of AI accelerators available in smartphone SoCs. So you can just check the previous slides if you didn't understand something, and it already provides the entire picture of what do you have and what do you have if you want to run accelerate model on mobile devices. And we move to the next topic, to benchmarking. So we know right now what are the options, what is the hardware that can be used for running neural networks. Now the question is, what is the performance of this hardware? And the performance, we check the performance with AI benchmark applications that was already mentioned. It was available in our computer vision lab. It was first released more than 3 years ago, and it pretty much evolved in parallel with TensorFlow Lite and an API, incorporating the changes, incorporating the new functionality, and so on. And this benchmark is using TensorFlow Lite models. It is accelerating them through an API and through custom TF-Lite delegates. It contains 14 sections, 46 tests that represent lots of different computer vision tasks, from classification and OCR problems to image super resolution, enhancement, and even some natural language processing architectures. And this benchmark tests floating point performance, integer performance, CPU performance when running floating point and quantized models, single throughput inference time, memory RAM consumption, initialization time, and accuracy. And when running this application, you'll also see the visualization of the results. And at the end, besides seeing the device AI score, you will also be able to see detailed results for each particular test for each particular architecture. So if you press on this arrow, you will see the results for each model when it is accelerated on CPU, when it is run on with acceleration on NPU or DSP. So you'll see the runtime, you'll see the accuracy, and in general, it can provide you quite a lot of information if you want to analyze the performance of different models on different devices. And besides that, in the settings, in acceleration settings, you can also available different acceleration options and run all tests either with an API or with some delegates, some custom delegates with GPU delegates and so on. So we are quite out of time. Therefore, I will be very brief here. So first of all, that I should say is that floating point inference and quantized inference, it should always be benchmarked separately. Because usually on many devices, actually different hardware is responsible for this. And therefore the results, therefore you should not mix the results obtained with one or other different type. Because if you want to run some models in your own devices, then for you, most likely only only one inference type matters. Well, if you have a floating point model, then you care only about floating point results. If you are running quantized models, then you care only about quantized results. And here on this slide, you can see the results obtained for 9 different architectures on the majority of chipsets that can provide acceleration either with GPUs or with NPUs. And as you might see here, well, there are pretty much 2 major takeaway notes from here. First of all, that yes, with some specialized silicon, it's possible to achieve very good acceleration. At the same time, the presence of NPU does not guarantee you anything about the actual performance. Because, for instance, you can see here that some older generation NPUs and APUs can provide actually much worse results even compared to GPU acceleration. So in general, if your device has NPU or APU or DSP or whatever, it tells nothing about its performance. This performance can be both very good, it can be very terrible. It depends on the exact architecture and the drivers that were developed for this platform. And another thing that you should understand that for floating point inference in general, we can get quite good results even on GPUs. So you can see here that, for instance, well, of course, we need a very powerful GPU, but if its performance is really good, then it will also be able to accelerate neural networks quite efficiently. And for instance, some GPUs can deliver much better results than NPUs or DSP or NPUs or APUs. But again, it depends solely on the architecture of GPU, of NPU, and APU. And I leave this slide for you because you can just check it later and go and analyze the results of different chipsets, analyze the problems for each NPU, GPU, or DSP, and so on. And here are the results for quantized inference. Here the situation is pretty much the same. So again, as I mentioned before, the exact naming of your AI silicon tells nothing about performance. DSP can be more powerful than NPU, and at the same time, it can be less powerful than NPU. DSP can be more powerful than APU and less powerful than APU. So it solely depends on the architecture. So, and another thing that I want to tell about int8 inference is that in case of quantized only models, GPUs are not that efficient as in case of floating point architectures. First of all, because they are GPU design is optimized for floating point inference that is needed in games, in rendering, and so on. And you won't get big advantages when switching from floating point to int8 format on the majority of devices with the majority of libraries. And besides that, usually DSPs and NPUs designed for int8 inference, they contain several very specific optimizations for this inference type only, which allows to achieve much better runtime, much better power consumption, and much better results in general. So for int8 inference, DSPs and NPUs are usually critical, and whenever you can run something on DSP, you should try to do this. And besides that, this was just a table where I summarized the results. You can find the results of actual devices, of actual mobile phones on the project website. And as I mentioned to you, different devices have different NMHL version, and therefore do not be surprised that some devices might show much better results than the other ones, even if they share the same, if they have the same chipset, the same hardware. Because NMHL is something that also matters. And besides that, you can also check the results of pretty much all mobile SoCs, not only that are providing acceleration, but also for some older SoCs, and you can just compare the results. You can analyze their performance and just how to read this data. This is an important question. So here we have a processor. Here we have its CPU configuration, and here we have AI accelerators used for quantized and for floating point inference. If the same hardware is used for both inference types, it's mentioned only once. Here we can see the library that was used for accelerating neural networks. If you press on it, you will see the description, but in general, N stands for an API, E stands for add-in, and H stands for hexagon delegate, and G stands for GPU delegate. So this is abbreviation. Here you can see the overall the aggregated results. And since you are all developers, this is actually not what you should really care about, not about these numbers and aggregated numbers. You should really care about pressing this view detailed results button. And after that, you will see the runtime of all models, of all architectures, quantized floating point, that we're running on CPU, that we're running on accelerators. You can see the runtime. You can compare what is the advantage of using, for instance, NPU or DSP compared to CPU inference. You can also see the runtime. You can also see the accuracy of the computations. So here it is measured as Albandro error, or number of digits accuracy in terms of number of digits predicted correctly. So, and the accuracy is another very important topic that was not covered in this talk, but make sure that when you are developing your models, and accelerating them on end devices, that the outputs of these models are correct, and there are no issues when performing on-device inference. Because what I can tell you is that in almost all cases, now you'll get slightly different results from what you're getting on your desktop environments because of different optimizations. The question is, like, what is the difference? What is the difference between these two results? So in some cases, the difference is very small. So for instance, you can see here that the accuracy is 4.8 digits and it's unnoticeable. In some cases, the accuracy might be quite low. It can be go beyond 1 digit. So in any case, you need to check. For any architecture that you are planning to deploy on smartphones, you need to check what are the actual outputs produced by this model when you run it on different hardware. And again, if you are developing your model and if you're interested in what is the estimated runtime of this model on some particular hardware, you can go to this ranking table, search the architecture that is closest to your model. For instance, if it's image-to-image mapping model, then you can select UNet or VDG model or some other model. If it's classification, then you can select one of these models. Just select the architecture that has the largest intersection in terms of operators, and then you can just see what is the runtime of this model on different phones, whether there are some issues with accuracy, whether there are some acceleration problems, and it will already provide you with a relatively good overview of the results that you will eventually get. And the last topic that I want to cover today is power consumption. So if you check the previous table, you will actually find that on CPUs you can get quite good performance. Then when running models on the recent, especially high-end chipsets, for instance, you can run Inception v3 at more than 6 FPS per second, 6 frames per second on Samsung Exynos Ultra CPU, which is actually enough for many tasks. And then the question is, so if we try to run Inception model continuously, for instance, let's pick up Samsung Galaxy S20 Ultra device with Exynos 2100 chipset, how long will it be possible to run it on this device? And the answer is 2.9 hours. 2.9 hours, and the battery goes down from 100% to 0%. And these results were obtained when all radios were turned off, when the screen was dimmed. If you just turn on the radios and increase the screen brightness, it will go below 2.5 hours, 2 hours and a half. And the answer, well, these results are quite discouraging, because if you are performing, well, for classification, you might even for classification, you might actually need to run this model continuously. For instance, if you're tracking some objects on the video, if you are running some AI scene recognizer, a new camera, and in this case, the resulting power consumption will be enormous. And if you're trying to run some image-to-image moving model, for instance, if you want to run image super resolution models that upscales your videos to, for instance, by 3-4 times, then the results would be even worse than here. Then the battery will go down from 100 to 1% in less than 2 hours. And I previously mentioned to you that when NPUs were designed, one very important, well, it was about the speed of an inference, but another important topic was actual power consumption, because we want to the corresponding silicon to be very power efficient, so that we can run this model continuously and they will not consume lots of energy. And now let's think about a good question is whether NPUs are much more efficient than CPUs or not. And we did the corresponding tests, and here you can see the results of this test. So we run the Inception v3 model on the Exynos 2100 phone, and just a second. Okay, it's on several different high-end SoCs and measured power efficiency of different hardware. So we checked the number of frames that can be pretty much classified using 1 watt of energy on different silicon, on CPU, on GPU, on NPU. And here you can see, for instance, the results obtained on the Exynos 2100 chipset. And as you can see, the power efficiency of NPUs is really great. In case of Exynos device, it is actually okay. I will answer the question, your questions after the end of this presentation. So the power consumption of NPUs of dedicated silicon is really great. It is very low, and it is significantly better than in case of normal CPUs, GPUs, and of normal CPUs and GPUs. And for instance, you can see here that the advantage is actually around 40, you get a 40-50 times advantage when switching from CPUs to NPUs. And this is like very important if you want to run something on mobile devices, because battery drain is something that is very, very critical. And Exynos chipset is not the only one that is so unique in terms of power consumption. If you will look at the results obtained on Snapdragon 888 SoC, then the results would be the same. Actually, the gain in terms of power consumption here will be even larger. So in this case, we are getting 50-60 times advantage in power consumption when switching from CPUs and from CPUs and GPUs. And you can also see on the previous slide in here that GPUs, as I previously mentioned, GPUs can provide very good runtime results. Sometimes the runtime can be as good as the runtime of NPUs or APUs, but they are not really power efficient. So yes, you'll get 3, 4, or 5 times advantage when switching from CPUs to GPUs, but they will pretty much never be as power efficient as NPUs. And here you can see the results of Kirin 9000 chipset. Again, here we have the same situation. Here we can also see the power consumption of floating point and integer models that are running on the same NPU. And yeah, for integer models, as expected, the results are better because where instead of 16-bit computations, we're using 8-bit computations. And this also results in better power efficiency. And here are the results for Dimensity CPU, for Dimensity chipset. Again, here everything is the same. NPUs are much more power efficient than CPUs and GPUs. And here you can also see that intent inference is more power efficient than floating point 16. So in this case, these models are running actually on slightly different cores. Therefore, these results are not that representative than in the previous case. So what you need to understand by looking at these slides is that if you want to run your model once, probably it doesn't matter what silicon you are using. Especially if you want to run some classification model, okay, you can just run it on CPU, and in almost all cases, you'll actually get quite good runtime. And if you want to perform inference only once, this is a good option. If you want to run your inference continuously, then if you are not using NPUs or DSPs or APUs, power consumption will be dramatic. And the only way how to decrease it is to optimize your model for special AI hardware. And on this slide, you can also see the aggregated FPS and performance per watt achieved by several architectures. I should already say that these are the results only for one architecture, so they are not representative. For different architectures, you will be getting slightly different results. And during the next few months, we'll publish a more detailed power consumption analysis, including lots of different architectures, lots of different chipsets, and their results will be representative. On this slide, you just need to understand, by looking at this slide, you just need to understand that NPUs are very efficient, are very power efficient, that almost all recent NPUs, they actually provide quite similar power consumption results. So by looking at these FPS per watt values, you can see that actually everything is quite close. In case of Exynos, yes, the power consumption is slightly higher, but this is partially because it also provides the highest FPS rate. And as you know, any additional gain in performance usually heavily affects power consumption results, and here this is the case. But overall, all current generation NPUs are very power efficient, and if you want to run your models continuously, you need to use them so that the battery is not discharged in 30-50 minutes. So, and yes, besides that, you can actually test power consumption of different components with Pinout Benchmark V2 version that will be released in several weeks from now in the Google Play, will be made public. And this functionality will also be present in AI Benchmark V5. So with AI Benchmark V5, you will also be able to check the power consumption of different models on different hardware. And you will see a graphical representation of these numbers. So we already just almost came to the end of time allocated for this talk. Just several final notes. I hope that after this talk, you really understand what are the main components, what are the main steps needed to export your model from device inference and run it efficiently on different hardware. So you understand that you need to train your model, export it using different inference formats, and then you can run it with different acceleration options. And in the next tutorials, you can run the resulting models with AI benchmark and check its performance, its runtime on different devices with different acceleration options. So this is not something that is not doable, that is labor intensive. No, for each architecture that you develop in the future, especially if you develop some energy efficient or some runtime efficient models, and since you're attending this workshop, I'm pretty sure that you do. If you are planning in the future if you're planning to develop some efficient architectures, then always try to check the runtime on the actual hardware and report these results in your paper, because in this case, this will give quite a lot to your results compared to the situation when you run your models on some desktop CPUs or GPUs, and you say that, okay, on Intel GPU with 24 cores, you achieve a runtime of 10 milliseconds. So this means actually nothing if you try to run this model on actual mobile NPUs and DSPs. And with this option, with this AI benchmark application, you can actually check the runtime on real devices. In the next presentations, the majority of vendors will go into detail. And if right now I just gave you a very brief introduction and a very brief overview of what happens on different platforms, what are the possible options, then in the next talks, all SoC vendors will go into more detail and will pretty much teach you what options should you use on any particular chipset, on any particular platform, how you can squeeze pretty much all power from every single SoC, from the SoCs, what are the acceleration options, what inference types should you use and when. So if you are planning to design efficient model for mobile devices, then definitely do not miss these presentations. They are super important, and you won't be able to find lots of information anywhere else except for these talks. And finally, if you have some questions in the when either converting your models or running it on some devices, you can visit AI Benchmark Forum and post your questions there. You can just explain your issue, and we are trying to answer the questions timely that you have. For instance, you have here some questions about runtime, about issues when running models with an API on Snapdragon and Exynos chipsets. So if you have any problems, if you didn't find the answer, and if you are struggling, just come to the forum, post your question, and we'll most likely provide you with an explanation of the situation that you see. Finally, you can find some additional information about on-device inference in our previous AI benchmark papers. They are slightly outdated. Nevertheless, there is still lots of useful data there. This year we'll release an updated paper with the contents of this talk and with lots of other useful material that will help you to understand the properties of mobile accelerators, mobile AI accelerators, and their results. So thank you for your attention. Here are the links. And as for the Q&A session, I don't even know if we have time for it, because we're already 3 minutes out of schedule. And let me just check. Okay, good. So I think that we should probably switch to our next speaker. And then if you have some questions, you can ask them either during the break or after the end of our today's session. You can post them on the forum, because if we I expect that if we now go into Q&A sessions, and then it can also take another 10, 20 or 30 minutes. So I guess it's better to stay on schedule. And right now we will, just a second, I will disable my screen. I will, just a second. So right now, we'll have just a second. Let me switch from. Okay, good. So right now there will be a talk from Dr. Alan Lu. The talk title is Edge AI Technology from Development to Deployment. And Alan Lu is Senior Director at Computing and AI Technology Group at MediaTek. And in this presentation, he will talk quite a lot about MediaTek Edge hardware, about its performance, about some optimizations that are needed to run models on this hardware. So, Dr. Alan Lu, welcome to our session.
Thank you, Adrian. Yeah, for the excellent talk. Yeah, since I'm from an industry perspective, so my talk actually will not as technical intensive as Adrian's talk, but I will explain more like a technology trend and why we are doing it. And so let me share my screen. So
yeah, just
you can see it, right?
Yes, sorry for interrupting. I saw Dr. Alan Lu presentation, and I can tell you that there will be actually lots of useful information, and not just what he already mentioned. So there will be lots of very interesting details in this talk. So don't miss it.
Oops, hold on. Let me. Good morning or good evening, everyone, depending on your time zone. My name is Alan Lu from MediaTek. It's a great pleasure and honor to have the opportunity to share MediaTek's experience of developing and deploying AI technology on the edge device. Let me start with the hottest topic here in Taiwan these days. It's about how the pandemic is changing our life. For those of you living in other countries may experience this change since last year. We are repeating your experience right now. Everything goes virtual. From basic needs like distance learning, working from home, online shopping, and this virtual experience extends to conference, concert, and sports, and so on. This is not something new. We had distance learning, working from home, and online shopping before the COVID-19. This pandemic is accelerating this digital economy. I believe this will become a new normal even after COVID-19 is under control, because we never know if there will be another pandemic sometime in the future. And indeed, there are some advantages of digital life. For example, lots of working class report that they save significant commuting time and therefore have a better productivity working from home. Company also quote to save real estate expense by letting more employees working from home. Of course, we are also facing frustrating moments of this digital life experience. For example, poor video audio quality, long latency, privacy, or do not have the vivid look and feel experience compared with the live face-to-face communication. But luckily, technology advance can help to solve some of the problems. These are the opportunity for us in the high-tech industry. I list some of the critical technology like 5G, multimedia, plus AI. I will elaborate in the following of my talk. This is an important slide. It illustrates two factors that drive communication and computing technology. That is the number of connected devices and the data generated by the connected devices. The number of connected devices versus time is shown on the left-hand side, and data generated by the connected devices is shown on the right-hand side. You can see that both of them grow exponentially. In the PC era, there were about hundreds of millions connected devices, and they generate quite limited data. The mobile phone is the real killer application, both in terms of number of connected devices and the generated data volume. Particularly after the smartphone became the dominant connected devices after 2010, the data it generates grew by 30 times in a decade. Nowadays, we can see more connected devices, what we call IoT, including transportation, smart home, manufacturing, and retail devices. And they generate more and more data. By and large, multimedia data generated by the fixed device or mobile device, such as a smartphone, tablet, PC, still accounts for a significant percentage of data to drive the communication and computing technology forward. We'll take a closer look at those multimedia content. This slide shows the evolution of mobile communication technology. Each technology generation lasts for a decade. 4G starts around year 2010. We are at the beginning phase of 5G. The three numbers in this row denote target per channel data rate, communication latency, and aggregate license bandwidth. The bottom row is the target application of each generation that we are mostly interested. We can tell that starting from year 2010, multimedia traffic, including video streaming and call, online gaming, and social media become the dominant applications. This is because that the per-channel data rate, latency, and aggregate bandwidth can support these applications. Conversely, this application not only drive the communication technology forward, but also demand higher performance computing platform. We expect this trend will continue with more new applications such as AR, VR, cloud gaming, intelligent vehicle application such as self-driving car, smart city, transportation, etc. This slide is to refresh our memory and project what 5G could be. A decade ago, a mobile phone with a tiny screen, and we can play Angry Bird and MSN is called the flagship phone. Nowadays, the mainstream phone can record 4K video, play heavy load online game, and enjoy rich and instant social media. We need to stretch our imagination for the coming decade, how the 5G will shape our life or our children's life. For example, 8K multi-view panorama video, cloud gaming together with AR, VR, augmented social media and shopping experience. This may appear to be fantasy now, but not far from reach. Something more exotic will appear in the 5G era. Let me share MediaTek's experience in edge AI technology development and deployment. I will use two examples from smartphone and TV respectively, which correspond to MediaTek's two leading product lines. Then I will show some demonstrations. In MediaTek, we use the following terminologies to convey the AI technology to the general public. Perceptions means extract features from image or video. It corresponds to feature extraction, face detection, and recognition, etc. The most common application in smartphone is face unlock. The algorithm and computing complexity is relatively low. Construction means image segmentation or instance segmentation. The common application in smartphone is image or video bokeh and face beautify. Even though the algorithm and computing complexity are higher, the current mainstream smartphone can implement it without problem. The next two levels are picture quality and video quality. It uses AI algorithm to generate pixel-level image or video. The algorithm and computing complexity are orders of magnitude compared with the previous AI algorithms. The end result of the picture or video quality are also significantly better than the conventional camera in the low light and high dynamic range photo scenarios. The same AI technology is applied and landed in the TV products, but at different applications. I won't go through the detail. Instead, I will show the demonstration in the next 2 slides. This slide demonstrates that use AI algorithms at the pixel level to reduce the noise in the low light and high dynamic range photo scenario. You can tell the difference with and without the pixel level AI algorithms to handle the noise and the details under this challenge condition. The low light photography becomes the selling point for flagship smartphones these days. This slide demonstrates that use AI algorithms to enhance the resolution at the pixel level. The left-hand image is using the conventional algorithms. The right-hand image is using the AI super resolution algorithms. Even though it seems hard to tell the difference for the normal eyes, but if you look at the edges between the building and the sky, you can see that the conventional interpolation-based algorithms has more artifact and fuzzier boundary. On the other hand, the AI super resolution shows cleaner image and details. The AI super resolution is important for 4K or 8K TV because it needs to play low resolution content from the broadcasting or network streaming video. Those contents are still predominantly at low resolution, such as 720p or 1080p. MediaTek rolled out the first worldwide first AI super resolution TV in March this year, and win a market success, get very good feedback from the customer. With the performance improvement on the edge device, now we can discuss how this changed the cloud and edge co-work model. The conventional cloud and edge approach is a server-client model. The device provides raw data to the cloud. The cloud consists of big storage, computing server, and analytics capacity to consume the raw data and generate decisions to provide to the device. And there are several problems. First of all, the exponentially increased data is created and processed outside of data centers. Sending all the raw data to the cloud will overload the storage, computation, communication, analytics servers, and will result in poor service quality. This happens often when a massive device are sending data to the cloud server at the same time. Secondly, our future world will be always on sensing and tracking, like our Face ID, smart speaker, smart camera, or a self-driving car. The cloud-centric approach will cause unacceptable latency and privacy issues. And thanks to the mobile phone technology continuously driving communication and the edge computing performance, the edge device can now locally analyze the data and make a real-time decision. It only send processed data and action to the cloud. The cloud can collect and analyze the processed data and provide global information to edge device. This cloud and edge collaborative approach can avoid the access communication latency, the poor service quality caused by data congestion, and preserve the local privacy. Let me use the self-driving car as an example to explain the cloud and edge collaborative approach. The vehicle needs to analyze the data from the camera, radar, and LiDAR to make real-time decisions how to drive the car. It will be a disaster to wait for cloud's decision to control the vehicle because of a communication latency. However, the vehicle can feedback the real-time traffic condition to the cloud. The cloud server will analyze the collective real-time traffic conditions from all vehicles and providing the global routing information to each vehicles and benefit all. This cloud and edge collaborative approach can apply to our smart speaker and camera at home, or at the video conference meeting with instant caption and translations in the office. 5G and AI are the key enabling technologies, together to provide high quality of service and real-time solution to fulfill our expectation or enrich our experience of the digital life. One critical piece of technology to deliver the digital life is the silicon SoC, or system on chip. Allow me to use MediaTek's Dimensity series as an example to explain the building blocks of current 5G plus AI SoC. There are three major function blocks. The first function block is modem, with 5G communication providing multi-gigabit downlink and uplink, and can operate at multi-mode with dual SIM cards. It provides the communication link for us to download the video and upload our photos to the social media. The second block is the general computing platform, consists of multi-core CPUs and GPUs. In this particular Dimensity SoC, it consists of 8-core CPU and 9-core GPUs. It handles everything from web browsing, running app, user interface, playing game. The third functional block is the AI and multimedia function block. It consists of a specialized AI processing unit, or APU, to perform the computation-intensive deep learning and machine learning operations. The multimedia part include the hardware and software such as a high-resolution camera and display, video and audio. All these functions are implemented in tens of billions of transistors and packed onto a single centimeter by centimeter silicon chip. It is quite amazing achievement thanks to the Moore's law. Let me recap what we have already gone through before diving into more technical discussion. We talk about the applications such as social media, video, and gaming keep driving the technology forward. We expect this trend will continue with new applications. We use a neural network complexity as the index. The line shows that the complexity increases over time with a slope around 2.5 times per year based on our observations. We also talk about the Moore's law, help to integrate more functions into SoC. Moore's law used to be transistor counts double every 18 months, but getting slower in the advanced node. We put a line with a slope of 1.3 to 1.6 times per year. You can see there's a gap between the application demand and what the Moore's law can offer. We'll discuss this technology improvement to bridge the gap in the next part of my presentation. This improvement fall into two categories: hardware architecture improvement and software, including algorithms, complexity reductions. It's a combination of process improvement, hardware architecture improvement, and software algorithm complexity reduction to enable new edge AI applications. What are the fundamental constraints or challenges to improve the performance of each generation of edge AI SoC? It is the memory bandwidth and thermal. As we put more and more transistors into the centimeter by centimeter silicon chip, almost all the functional blocks need to access external memory. The memory bandwidth will be completely congested and become the performance bottlenecks. Likewise, even though we can pack more transistors into the centimeter by centimeter silicon chip, the thermal generated by the transistor's dynamic power and leakage power will surpass the heat dissipation capability of the package and reach a performance limitation. You may wonder why not use more silicon area to solve this problem. For example, instead of a 1 centimeter by 1 centimeter silicon chip, we may use 2 centimeter by 2 centimeter to offer 4 times of a computation capability and use more external memory to solve the memory bottleneck. But there's an important non-technical constraint for edge AI device, that is the cost. Edge AI are bounded not only by memory bandwidth and thermal, but also the cost. Even though you can afford to buy a smartphone with 4 times the price, you probably don't want to carry a smartphone with 4 times of a size for the heat dissipation or a bigger battery. To address the thermal issue, we need to improve the power efficiency at the system level. One method is to use heterogeneous computing processors and dispatch different characteristic workload to different processors. For example, when we use our smartphone for face unlock, it happens almost instantaneously. This is a short burst workload of low complexity. Require a fast start, face recognition, and done. CPU would be a good candidate to perform this task. On the other hand, when we are doing video control with virtual background, this is a continuous workload may last for tens of minutes or hours. GPU of a better power efficiency would be a better choice for this workload. For heavy workloads such as a pixel level video quality enhancement, APU would be the only choice to fulfill this function for a given power budget. This heterogeneous computing method can go to finer granularity based on workload to further save power, such as a big little core using the CPU and APU. Heterogeneous computing is nothing new, and its concept is straightforward. The real challenge is how to dispatch the workload. If the workload is misplaced to the wrong processors, we will end up with a slow but yet power waste application. MediaTek's NeuroPilot scheduler is an adaptive scheduler which dispatches the workload to CPU, GPU, APU dynamically and maximize the performance and energy efficiency. The other important design consideration in SoC architecture is the data flow and the control flow. In the conventional SoC architecture, the data exchange between the all processor engines such as APU, modem, audio, camera, all goes through external DRAM. And the control flow is initiated and controlled by the CPU. It creates 2 problems. First, the performance bottleneck, because external memory bus is congested, just like a traffic jam during the rush hour. Second, it is power expensive to move data in and out of the external DRAM. It could be 10 to 100 times more expensive compared with internal data exchange. The solution also seems to be straightforward. This is to have direct control and data paths between different processing engines. This reduces the DRAM traffic and offload the CPU control burden. It is very similar to build lots of interstate highway instead of a single shared road. The benefit is overall system performance increase and latency reduction, and the power efficiency improvement by avoiding exchange data through the DRAM. This is a general principle to reduce the DRAM access, not only apply to inter-processor data movement, but also apply to intra-processor data movement. This is particularly beneficial for data access intensive processors like CPU, GPU, and APU. We cannot use the hardware without the software. We will move one step up at the platform level. The definition of the platform here is the hardware system, plus the software SDK, machine learning toolkits, and the AI frameworks. This is MediaTek's Edge AI platform. We called it NeuroPilot. User can develop edge AI application on the top of a neural pilot. There are two reasons that MediaTek built our own neural pilot edge AI platforms. First of all, edge AI devices are severely constrained by power. NeuroPilot middleware and ML kit provide platform-aware optimization to squeeze the last drop of performance out of processors. Secondly, edge AI devices are very diverse in terms of CPU, GPU, and APU performance. And edge AI products cover high-performance smartphone, TV, all the way to small IoT devices, and running at different operating systems. NeuroPilot platform provides a cross-product platform and reduce the time to market to minimize the design risk. Let's take a closer look at the NeuroPilot. The stacks on the left is to perform the inference task and for the deployment purpose. The neuron software layer is essentially an external interface. It converts or compiles different format of neural network model or API or delegate and translate into internal intermediate representation and perform the initial graph partition and optimization. NeuroPilot support open AI frameworks such as TensorFlow, TF-Lite, PyTorch, and customized AI frameworks. It also supports Android NN API, MediaTek's Neuron Delegate, and TVN. The middleware layer performs hardware-dependent tasks and optimization on the heterogeneous computing platform, such as auto-scheduler, to dispatch different characteristic workload to different processors. We talked about this in the previous slides. And DVFS to dynamically change frequency and voltage of each processors to further reduce the power consumption. The vertical blocks provide toolkit to assist the offline training tasks. These are essential core tools to get the best performance on the edge AI device during the developing phase. The ML kit provides NAS, which stands for Network Architecture Search. It search and find the suitable network topology for the specific edge AI device given the baseline network. The pruning and quantization tools reduce the footprint of the selected network, not only save the memory and bandwidth, but also reduce the computation latency and power by a significant factor. To explore and promote NeuroPilot platform used on different applications for the edge device, MediaTek sponsored two challenges this year. One is Mobile AI Workshop at CVPR 21, and the other is the Pair Challenge at the ICMR 21. The first challenge is Learn-Based ISP, translate raw image to DSL-like photo. This corresponds to image quality category presented in the previous slides. It's a hot research area and has important applications in smartphone and smart camera. The next speaker will talk about this topic. The second challenge is about dense object detection focused on pedestrian, vehicle, scooter, and bicycle detections. It's very common in Asia countries. We'll present this topic in ICMR 21. My final slide is the vision of MediaTek to bring 5G plus AI to everyone to enrich the digital life. There are more than 2 billion devices with MediaTek SoC inside every year, including smartphone, tablet, TV, smart speaker, set-top box, and infotainment devices. We combine the core technologies of communication, multimedia, and computing plus AI to give every device intelligence so that the device can see the world, listen the world, including our language, all kinds of sound, and can provide us the service intelligently and make our life better. Thank Thank you very much for your time and patience. Oh, sorry, one more thing, MediaTek is hiring. As you may know that MediaTek is doing pretty well in the smartphone, TV, and Chromebook IoT. AI is regarded as a strategic platform technology to support all the product line. We are actively recruiting talents around the world. If you are interested in joining MediaTek, please scan the QR code and forward your resume to our HR or me. Thanks again, and that's all for my talk today.
Thanks a lot for your insightful talk and for lots of interesting information. We also here for you. We have here for you a number of interesting questions. So I think that you can also see them in the chat. And the first question is, what are the areas and what are the tasks that MediaTek can now not accelerate with?
You mean? Can you repeat the question? Cannot or can accelerate?
Cannot accelerate.
What area?
Yes. What are the applications? So yeah, in which areas you cannot accelerate something?
Right. It's primarily for the new application, like for example, in the NLP or some of the new models that in the current platform we are not supporting very well. But in the next generation, actually, we are planning to put all those new model in our next generation accelerator. Yeah.
Yeah, well, I think this is a typical situation with pretty much all SoC vendors right now.
Yeah, that's right.
Okay, we have another two questions. The first one is, just let me check it. Well, as far as I understand this question, it's about how to make, how to use Edge AI for deployment of the same AI solutions across different AI accelerators and different products.
Oh, okay. Well, actually, that's a very, very good question. Yeah, because in MediaTek we have the different product lines, so we need to consider that the AI technology can be used cross product lines, and there are two actually contradictory requirements. The first one is that of course, we want the technology to be very general and, like what you said, to be a unified technology. But the other requirement is we need to get the best performance from the hardware. So these two, sometimes they are contradictory. And so what we do is like, one method is to decouple the software and hardware. So the one layer, actually, as I showed before, that the one layer is actually focused on the software graph partition optimization, and the other layer is focused on the hardware dependent optimization. So together we can actually realize the two different requirements. And of course, the offline tools for platform-aware optimization is also very crucial. We actually spend lots of the time in technology to improve our offline tools so that it can optimize for different hardware platforms. I'm not sure if this actually answered the question. Yeah.
Well, I think that it's a good answer to this question. So if I think, yes, thanks a lot for very detailed information and for detailed answers to these questions. And right now, we then move to the next talk. It will be delivered by Min-Hun Chen, Senior AI Engineer at MediaTek, and he will tell us about the Learn Smartphone ISP challenge that was already mentioned today by Dr. Alan Lu, and he will present this challenge and present the results obtained in this challenge. So, Min-Hun Chen, welcome.
Hi, thank you. Can you hear me? Just want to check.
Yes.
Thank you. That's perfect. Let me share my screen. Let me share my screen. You can see that, right?
Yes, we can see it.
Oh, sorry. Cool. Okay. So let's begin. So hello everyone. This is Min-Hun Chen from MediaTek AI Taiwan. Today I'm going to present the summary results and top solutions for the Learn Smartphone ISP Challenge in the MAI workshop. First of all, let's have a flashback for the main objectives of this challenge. So image signal processing is an essential part in the camera imaging pipeline, especially for the mobile devices. However, traditional ISP designs separately for different functions like demosaiking, denoising, and so on. And some post-processing techniques are also adopted, but they are usually not able to recover the lost information from traditional ISP pipeline. Therefore, we are interested in developing an end-to-end ISP pipeline that can unify all the functions and directly convert the raw data into RGB images. However, mobile devices have limited memory budget, and the supported operators and neural network modules also constrain the designs of neural networks. Therefore, to develop an efficient and practical solution for mobile-related tasks, one needs the following major components. First, a high-quality and large-scale data set that can be used to train and evaluate the solution on real, not synthetically generated data. And second, an efficient way to check the runtime and debug the model locally without any constraints. And finally, an ability to regularly test the runtime of the design neural network on the target mobile platform or device. And we provide all the above components in this challenge. And it's worth noting that different from previous AIM workshop in ECC 2020, we consider efficiency constraints and evaluate on real mobile device. So the first component is the dataset. In this challenge, we provide a raw to RGB dataset collected by a 100 megapixel Fujifilm camera and the Sony IMX586 mobile sensor, resulting in more than 24,000 raw RGB image pairs. And for more detail, feel free to check our paper or GitHub repo. And next, the second component is about local evaluation. So when developing AI solutions for mobile devices, it is very important to be able to test the design models and debug all the issues locally on available devices. It'll be more convenient to do so. So for this, we provided the AI benchmark application in this challenge that allows to load any customer TensorFlow Lite model and run it on any Android device with the supported acceleration options. So users can run their models on smartphones, CPUs, GPUs, APUs, and so on, or other kind of like computing processors. And for more detail, feel free to check the website of the AI benchmark. And finally, let's talk about the last component, the target platform evaluation. And in this challenge, we evaluate participants' models using real mobile devices with our MediaTek Dimensity 1000 Plus platform. This platform contains a powerful APU capable of accelerating floating point and integer models. And it's worth noting that the 16-bit inference support is essential for this test, as the raw bare data has a high dynamic range. So, and you can see the performance was ranked first by AI Benchmark at the time of its release. So the overall pipeline of this challenge is like this. First, the participants train and develop their models, and then upload the models to the runtime validation server connected to a real mobile device. And then the models are parsed and accelerated using MediaTek Neuron Delegate with Dimensity 1000 Plus platform APU. Finally, the results, including fidelity and runtime, will show on the leaderboard website. And we also provided more detailed introductions for the Dimensity 1000 Plus platform in our website. So what's Neuron Delegate? And MediaTek Neuron Delegate is like an API specifically designed for MediaTek AI processors to accelerate TF-like models. And it has several advantages over default Android API, including first, it can update AI operator support frequently, and the update will not be restricted by Android OS. And it also reduces unnecessary communication time, so it can quickly access to the computing processors. It can also leverage MediaTek NeuroPilot framework with APU, and also support MediaTek 5G platform. And there are more details in our GitHub repo. So by following the instructions in this repository, you can also build neuron delegate in your local system. Here we show an example case that uses a common and popular model, DeepLab V3+. So the results show that MediaTek APU can greatly accelerate models better than CPU and GPU. And you can see that the acceleration is even more obvious for quantized models. So let's go back to the challenge. In this challenge, we consider the balance between fidelity and speed. So the final score function contains both with a weighting parameter alpha. And participants need to consider both factors in their model designs to get high scores. And for more detailed formula, you can check the report paper. And to encourage the participation and lower the bar for participants, we also provide a comprehensive GitHub starter code base, including the whole pipeline. So by directly following the instruction in this code base, participants can start training from scratch and get a TF-like models that can be used for the final real mobile device evaluation. And the baseline model is an UNet-like architecture called PUNet, where participants can choose to build their approaches upon. And this code base is already released to public, so everyone can utilize it for any research related to general road to RGB pipeline, not just for this challenge. And here we show the overall statistics about this challenge. In this challenge, there are more than 200 participants and 9 teams got into final stage. And this table shows that the final result, which are also shown in the report paper. And it's worth noting that the last one, ADS, was ranked second in the PRM challenge at ECCV 2018. However, since it didn't take the runtime and efficiency into consideration, so the final score becomes not that competitive in this challenge. And then we're going to introduce one of the 2 winners. It's called DHISP from Dahua Technology, China. And the title is called SmallNet for an end-to-end ISP pipeline. Their proposed SmallNet has the fastest speed, and the tanh function in the first layer and pixel shuffle layer play important roles to keep good fidelity. And they use popular L1 loss and BGG19 perceptual loss for training. The other winner is AI ISP from Industrial Technology Research Institute, Taiwan. The title is called CSA-Net, High-Speed Channel Spatial Attention Network for Mobile ISP. And their proposed CSA-Net has the best fidelity. And the main component is called double attention mechanism, including spatial and channel attention. And they use Charbonnier loss, VGG19 perceptual loss, and SSIM loss for training. And they will give a presentation about their approach with more details after this talk. And there are also some other great solutions, so please check the report paper for more details. So in summary, the goal of this challenge is to design an end-to-end deep learning-based ISP pipeline with the consideration of fidelity and efficiency balance. And for MediaTek, we focus on developing edge AI technology, including AI algorithm, software, and hardware. So for this challenge, we provide the Dimensity platform with APU for better efficiency. And we also provide Neural Pilot framework with Neuron Delegate as an user-friendly and platform-aware toolkit. And finally, all the QR codes that are listed here in case you missed them previously. And again, we are hiring worldwide, including multiple positions for computer vision, multimedia, artificial intelligence, and machine learning, with the aspects of algorithm, software, and hardware. So feel free to check the upper right QR code or contact our HR for more details. Also, feel free to contact me using the middle QR code if you have any other question. Thank you.
Thanks a lot for the presentation and for providing pretty much all details of this challenge. And so are there any questions for Chen? Okay, I do not see any questions. Therefore, thanks a lot. And as was already mentioned, we'll now have a talk from one of the challenge winners. So I think that you should unmute yourself. Can you please unmute yourself? You're muted right now. You need to unmute. Just a second. No, oh, okay, so you're unmuted, great.
Can anyone hear me?
Yes, we can hear you and we can even see the slides.
Okay. The topic of today's talk is CSANet. In this talk, we will discuss how channel and spatial attention can be used to help ISP task in mobile devices. Image signal processor, ISP, is a specialized device, and its main function is to map raw image to RGB ones. However, there is always a big gap of photo quality between a smartphone and a professional camera because the smartphone's ISP is limited by its hardware limitation. Therefore, the object of this study is to replace a smartphone's ISP with a neural network. Moreover, we would like to learn a model to produce high-quality images like DSLR and to meet the required image metrics and the runtime constraint. Thus, we propose CSANet, which emphasizes inference speed and high PSNR image quality. Recently, researchers have found that CNN can be used to compensate the images. In the following, we take PyNet and AWNet as two examples. PyNet was the first work to show the low-quality image can be enhanced and restored by a complicated network. However, AWNet uses the attention mechanism and the wave transform to restore raw image to high PSNR RGB ones. As for the attention, it is used to make CNN learn and focus on the important information rather than on unuseful background noise. In the following, I would like to talk about the design strategy of our proposed network. In the beginning part, we use a sharded convolution layer and a conventional convolution layer, both with ReLU activation function, to perform feature extraction and downsize the input raw image. In the middle part, there are two dams with skip connections. The details of them will be discussed later. The skip connections are used to avoid the vanish gradient problem and to keep the similarity of the learned feature maps from different blocks. The two dams are used to enhance the spatial dependencies and highlight the prominent objects in the feature maps. In the last part of the network, a convolution, transverse, and a depth space layer are used to upscale the size of the feature maps. Finally, a conventional convolution layer and the sigmoid function are used to restore the RGB image. Now we talk about the double attention modulo, DAM. In the DAM modulo, a spatial attention and the channel attention modulo are concatenated together to recalibrate the input feature maps. In the spatial attention design, it is simplified to a depth-wise dilated convolution to extract long-distance spatial dependencies. In the channel attention design, it is basically borrowed from squeeze and the excitation network. Please refer to the paper for the details. Now let's see the reconstructed image of our proposed method and compare them to others. From the top, the first row is the ground truth image captured by a professional Fujifilm camera. The second row is the reconstructed images from CSANet, and the third is from AWNet, and the fourth is PUNet. If you see these images carefully, you will find that our method has a better capability to recovering colors than PUNet. We also did a ablation test to evaluate the effectiveness of attention module. We can see that one channel attention module performs as well as 4 residual blocks. Furthermore, using both channel and the spatial attention modules gives an even better image quality at a reasonable cost of runtime. Here is the validation score we got from the online platform of ISP Challenge this year. We can see that our method has achieved less 100 milliseconds inference time per image, but still had the comparable PSNR to AWNet. In conclusion, our CSANet won second place in the ISP Challenge, but won first place in PSNR score. That's all of my talk. Thank you for your listening.
Thanks a lot for the presentation and for information about your architecture. So anyone has some questions about the architecture, about the results, about some other things? Okay, if there are no questions, then thanks a lot again for presenting the solution that demonstrated the best visual quality and the best numerical results in this challenge. And right now, we are moving to the next invited talk that will be given by Gilberto Rodriguez. The talk title is Imagination Technologies Approach to Overcome the Challenges of Deploying AI in Mobile. And Rodriguez will tell lots of interesting things about imagination NPUs and other hardware and how it can be used for on-device inference and what are the general strategies to achieve better performance on it. So Rodriguez, welcome.
Thank you, Andre. Can you confirm that you can see my screen?
Yes, yes.
Okay, thank you very much. Thank you, Andre. So yes, I am Gilberto Rodriguez. I am Director of AI at Imagination Technologies. And today I want to explain you how Imagination overcomes the challenges we have in AI deployment in mobile devices. So I will be introducing you a little brief about Imagination in case you haven't heard about us before. And then I will be talking about the challenges and opportunities that there are there for AI deployment in mobile. And then finally, I will explain you what we as Imagination are providing to the mobile community for AI deployment. As Andre said during the meeting, please, you can put any questions on the chat because the talk should take about 20 minutes. So there will be another 10 minutes if we want to have a Q&A at the end. So Imagination Technologies, we have embedded our technology in over 11 million devices. We develop hardware IP that is used by our customers and partners to deploy silicon in multiple devices across the world. And we are a significant patenter. We have thousands of patents, and we're in the top 10 patenter last year in the UK. We have also been top 1 performer in AI benchmarking 2019. We'll explain a little bit more further. But we also have a dominant player in the GPU market in mobile with more than 30% market share in GPU graphics in mobile and over 40% in automotive as well. And we've been playing for many years with the major semiconductor companies around the world. We are based in Kings Langley, our main headquarters are in Kings Langley, but we have all the design centers both in Western Europe and Asia, as well in North America. So we do have three major areas of product. One is our GPU that has been deployed in multiple markets. We have also an Ethernet packet processor that has been successfully deployed in automotive with multiple use cases as well. But today I will be focusing on our network accelerator, our AI compute, and I will be touching in our Series 3 and Series 4 architectures. But let's start talking about what is AI mobile and what's happening. There are, as the other speakers have been mentioning, there are many things that are driving more AI in mobile. AI is already there, but there are new trends happening. There are more sensors. So even existing sensors are growing. We have microphones and cameras, but the resolution and frame rates of our cameras are increasing. And then we also have LiDAR coming into mobile, and we have other connected devices like smartphones, smartwatches connected to the phones. There are networks that are increasing, partially because the data is bigger, but then in some situations because the models are more complex. Even though the models are being optimized for mobile, some models are just complex by nature to be able to achieve the tasks they want to do. With this, there are more applications that want to be deployed in the mobile using AI. And then we want customization for the customer. You can now customize your AI use for what the end user wants to do. And overall, the customer is expecting that improved performance. AI was a nice play to have there, but now we expect it to work first time and very quickly. But there are challenges to get all this working. As my colleagues have been explaining of the other speaker, there are limitations, and two of the critical ones are the limited bandwidth you have in the system and the limited power. With that will come limitations about the area as well. There are other challenges about having security. You have multiple sources of data being trying to be extracted from your phone and different applications using different kinds of data to process. And the people creating the models want to protect those models so other people cannot steal them. And also you want to have quality of service. They will have a certain application that you want to prioritize. As you might be doing face identification, you might want to prioritize that versus some task that is running on the background. Then there is an increasing number of network models that have been deployed in different frameworks, and you have to have means to deploy them in your mobile phone and different methods to do that. But with every challenge, there are opportunities. So for this system limitation, what are the things you can do about it? So you can minimize the bandwidth. There are techniques to compress your model or compress the weights. You can take advantage of local memories to keep the data local, so you are not keeping using external memory bandwidth. And you can use low bit depth, as has been explained in the previous speakers, and I will be talking about. Using low bit depth can significantly reduce the power and increase the performance. There are techniques to reduce the power. One of them is just as basic as doing layer fusion. So every time you are executing an operation, rather than sending the data back to memory again, you do multiple operations in a single pass. You can do clock gating in your hardware. And overall, you're trying to minimize the data movement in and out your compute engine. You want to have separate areas to support security between different users. So you will have different memory regions and different registers to control how the data is being accessed by the different users. And you will need to prioritize the workloads depending what you want to do and how critical is the task. And then to be able to support all the different models, you need to support extracting and importing data from all the different frameworks. And you have to be able to optimize the features and the operations of those models. So out of these challenges, there are many things that optimization as a whole in this industry have been overcovered. I will be explaining a little bit approaches of having cascaded network. When you want to do face identification, you have to do first a detection and then a verification. You want to have a low precision network, but you're starting with a floating point network that you need to optimize for deployment and quantize. And there are new techniques now to do quantization aware training as well that allow you to do this optimization with maximum accuracy from floating point to integer. There are other things that you can do. You can take advantage of sparsity. You can create a network or layer that are optimal for mobile, where you might have object detections post-processing that are more suitable for mobile devices. And then you have to support new networks. And this is where you can do a reduced set of operations where you map your network to do subset of operations that you can actually accelerate on your network processing unit. And then you can, this allows you to do multiple layer perception networks, for example, or recurrent neural networks. So all these are things that we have kind of achieved to certain levels. There is a study that one of my colleagues, Dr. Ana Salazar, presented back in 2020 on how even complex networks like face identification, where you have to do first a face detection, followed by a face verification to get a final identification of your object. He was doing a study internally with our team how we could convert a network from 32 bits to 8 bits without even doing quantization aware training, but just looking at the histogram analysis, doing a profiling and selecting the right exponent. We could achieve the same level of accuracy with only adding an extra level of positives. He was analyzing 45 faces from our internal team, and after quantizing both the detection and verification, there was only one extra false positive. And that was doing 8 bits. When she was doing the analysis with 16 bits, it was a perfect match between doing floating point and integer 16 processing. So why would you do it? When we analyze the data in our older generation 2NX, if we were processing the data in 16 bits, we will need for the R phase 260 megabytes per inference. But if we were doing this in 8 bit, we only needed 95 megabytes of data per inference. This meant that we could go from 60 inference per second to 123. And another way to see the advantage is that you will reduce the power. With our 3NX generation, the benefit was even higher because in this case, we can do 4 times the performance in 8-bit versus 16-bit. So from starting on 16-bit, going 60 frames per second on R phase in 2NX, in 3NX now going in 8 bits, we can do 248 inference per second, which allows you to reduce so much the bandwidth and increase the performance. There are other techniques then that you can use to optimize your network. One of the challenges is on quantization is you have to go from a floating point network and you have to train your quantized network, and there are multiple techniques. And those techniques were in the past depending on the type of network. An analysis that my colleague Savox was doing and presented early in this year in 2021 is that you can use the transfer learning and using the distillation technique to train a quantized network. So you will have your floating point network and you have your quantized network, and the floating point network is training the quantized network to achieve maintain the accuracy with the minimum number of bits. And the results are amazing. So he was proving that for something like MobileNet, that we were having an original network of using 32 bits, we could quantize and have a network that uses in average only 7.2 bits per tensor from the original 32 bits of data weight, and pretty much no change in the accuracy. And it was applicable across the range. So overall, we could demonstrate that 8 bits was enough to do inference of all the common network that you will see deploying a mobile phone today. There are many more references. Some are in our internal website, and some of them you can see some of the videos of these presentations from my colleagues, so you can contact us if you wanted more details. So how are we taking this at ING to deploy AI in mobile? So as I said before, in our 2 generations away, 2NX made it to the top quantity score with our 2NX generation with our partner Unisoc in one of the funds. And we achieved this by paying attention to these system limitations. We have a high density graph execution engine. We our AI engine aims to execute the whole inference in a unique IP. We were in a previous talk that we're talking about heterogeneous system that is typically needed in many systems, but in our engine, we try to do the whole inference in one go to avoid data transfer between different IPs and having to synchronize across them. We have a very advanced memory management system that allows us, and I will explain this a little bit better, take advantage of all the possible locations where the data might reside. We do weight compression to reduce the size of the model, reducing the bandwidth and reducing the power. We have a wide range of bit depth, and each layer and each tensor can use different bit depths and different exponents. And then I will be explaining as well a tiling technique that we have a patent pending algorithm. Then we have support for secure zones for multiple users, and we have quality of service for deployment, so you can have your higher priority tasks always executed on time. And then in terms of deployment, we have the Android NNN API support, but we also have the offline approach in which you could pre-process on networks, especially you wanted high priority things that are embedded in your phone, at the same time that you want to enable generic third-party application running in the phone. So one of the techniques is taking advantage of local memories. The majority of data when you're processing the network is intermediate data and weights. One technique we use very efficiently is taking advantage of a local buffer to which we can map the network and temporal data. And what we can do with this is significantly reduce the bandwidth that you need. In the right side, you can see how in YOLObit 2, depending on the memory size, you could go from 200 megabytes of megabytes of bandwidth, the external bandwidth required, down to less than 100 megabytes using an internal OCM. And what will happen is you will have in your SoC a certain site, and then our compiler and mapper will take the advantage of that memory to put as much data as possible, reducing the DI bandwidth. Beyond the local OCM, you will normally have one of our NNA engines, local internal memory, and then you might have other system memory where you might be allocating weights, temporal data, and then you can dynamically allocate where this resides sent to our memory management unit as well. More recently, at the end of last year, we launched our series for NNA. And this was for looking to even higher performance and executing in low latency. We have now created clusters of cores of logic, as you can see in the image down to the right, where we have local logic with the local memory. Each of them is a full inference engine. And we can have multiple of them working as a cluster and taking advantage of a very high internal bandwidth and local memory to use them. And with this cluster, we can process up to 100 TOPS in a single cluster. And we can achieve two things, as in the graph on the right. We can achieve very high performance, but at the same time, we can reduce the latency pretty much to 1/8. This is especially beneficial for big networks. If you are processing a 3 megapixels camera or 8 megapixels camera, that's where you will really take advantage of this. So with this Series 4 architecture, we introduced the tiling, the tensor tiling. And what we have done here is typically you will process one layer, as you can see on the right side. I don't know if you can see my pointer when I am speaking. So typically you will process one layer followed by the next layer and so on and so forth. So all the intermediate data typically has to go to DDR. What we did in our Series 4 is split the layers into tiles, and we create group of tiles, as you can see in the bottom. And what we do here is each of the tiles, the intermediate data is kept locally in internal memory. That way we minimize the amount of going in and out of the device in terms of memory, reducing the bandwidth and the power and increasing the performance. And we can also do is each of these tiles can now be executed by each of those individual cores. So we can process in a multi-core cluster. We can process 8 tiles in parallel. So now we're saving bandwidth because we have intermediate data kept locally. We can execute faster because all these tiles are running in parallel. And also the overlap of data can be set across all these tiles. So we have the benefit of double the bandwidth and the performance overall, reducing significantly the power you need. This is one example of what is the effect you will get here. So in this example, I have plots of 1 core only up to 8 cores. And depending on the system bandwidth, the smaller cores will flat out around 30 megabytes of system bandwidth. But with the 8 core, we can keep increasing the performance up to 192. Typically, in a mobile phone, you will be looking more to the left. But even in a 32 megabyte system, having an 8-core system, you can more than double the performance. So you are now able to trade tops, internal memory, and performance depending on your use case and the network you're trying to process. But with the current trend of bigger images being processed on the mobile, this gives you the flexibility to select what you really need in your system. So finally, similar to the other speakers, we have our own tools to deploy networks in heterogeneous systems. We have built our NC SDK based on the open source TVM subsystem, and we have offline TVM compiler and then TVM runtime. Typically in the mobile phone, normally you will have the Android NN runtime, so you normally don't need the TVM, but for the compilation offline process, you can still take advantage of our heterogeneous compile system and integrate into your tools to have a whole solution in a heterogeneous system. And this is pretty much how your software stack will look like. Your driver will be very light version. You will have a Linux or Android operating system. In case of imagination, we have a combined API to deployment on GPUs or NNA or across the 2 devices. And then you will have the TVM runtime or Android NN, depending on your system. So just a summary and takeaways. The use of AI deployment on mobiles is still growing. Having an efficient inference are required to cope with all the required compute. There is an increase in compute. There are those limitations on bandwidth and power in your system. There are many techniques to maximize the performance for a given hardware. Once you have the hardware, there are different techniques for optimizing your model for that hardware. What we have at Imagination is a wide range of IPs that enable you to have an optimal hardware solution that you can take advantage with your software. And this is where it's also critical, and we are monitoring the AI benchmark to make sure that our hardware IP performs very well in the AI benchmarking. So that's the end of my talk. Andre, back to you.
Thanks a lot for the very technical presentation and for providing lots of details. Are there any questions to Gilbert Rodriguez? Okay. Okay, the question is the SDK open sourced?
Sorry, that's a good question. So we are working, we have an open board, one open source version at the moment, just for the 2NX. We are looking to open source part of the code in future generations, but at the moment it's only through our partners. So we are using open source community. We are open sourcing part of contributing to the TVM open community. The NC SDK is not open source yet. We're working a version for that coming up soon.
Okay, I guess, yes, this answers the question. Okay, if there are no questions from challenge participants, okay, another question. What do you mean by memory with bit bandwidth? Do you mean SRAM or DDR?
So
SRAM 2 from DDR.
Yes, so in this case, we consider on-chip memory local to the IP, typically SRAM. When I am talking to bandwidth, I am meaning external to the IP. So we'll have high bandwidth, especially in Series 4, we have logic and internal memories. We limit the internal bandwidth of that. So every time I've been exposing about external bandwidth is external, meaning typically DDR, but it could be SRAM as well, external to the IP. But typically it means DDR bandwidth, so external to the IP. Abdel, does that answer your question?
Yeah.
Definitely.
Okay, good. Then probably some questions from me. Okay, first of all, you didn't mention almost anything about GPUs. And are there any specific optimizations in Power BI GPUs for machine learning inference? And more importantly, is there any option to get them to run something efficiently on them?
So that's a good question, Andre. Thank you for asking. So yes, our software stack works both on the network accelerator and on the GPUs. Our GPUs are very good on graphics, but they also have optimized logic to running network acceleration. But the performance of the network accelerator can be between 10 and 100 times faster than the GPU. And the network accelerator is typically more optimal in bandwidth and power. But yes, GPUs, the same SDK we have for NAS, you can use on the GPUs. The level of performance you achieve is very good for a GPU, but is not as good as the network accelerator.
Well, it's obvious that it's not as good, but sometimes you need GPUs for instance, yeah, for floating point inference.
Exactly. So that's correct. So exactly, Andreas, you are going towards our GPUs can very good at deployment in mobile phone. They're being used, and as said the previous presenter, a GPU can do typically better than a CPU. Especially you're deploying floating point, you will be using some of the GPU, and all the optimization we have been describing before apply to our GPUs as well.
And then one more question: do you have any delegates for accessing your GPUs? Because as we know, like it's hard to access your GPUs when using an API, because on the majority of devices, well, sometimes there are an API drivers, sometimes these drivers are not really that good as one wants them to be. So do you have some internal delegates that can be used to directly run models on these Power BI GPUs?
So the delegates is something we're working at the moment. At the moment, the only way to access publicly, so there are two ways to access our GPUs, and this depends partially in our customers. So NNA API is exposed by some of our customers when they are integrating the GPU. Some of our customers are currently working on integrating our NC SDK into the tool flow as well. One of the things we are planning for the next coming months from the software is having open delegates to deploy directly, probably from TensorFlow Lite and framework like that. At the moment, those delegates are still not there because you can also access our GPUs via OpenCL directly. If you have something that can generate OpenCL code, you could still use our GPUs. Some of the times is not us as imagination, is what our partners want to expose to the end user when they build the software stack on top of imagination.
Yeah, got it. And then one more technical question about, so you mentioned that, okay, you are developing delegates, and you mentioned that it's mainly OpenCL. Are you also planning to use Vulkan API? And if not, what are the reasons?
So Vulkan is another of the APIs. At the moment, the Vulkan is mainly used, so our GPU support Vulkan for graphics. The Vulkan API for AI is not an area we have started working yet.
And do you estimate that with, well, if you use Vulkan instead of OpenCL, will it be possible to significantly improve the performance?
So yes, I mean, the best way to use our GPUs will be using ING-DNN API. That is the one that gives you the optimization already. Something that we haven't done yet is include ING-DNN into the delegates of TensorFlow and this framework. This is our next step. So above OpenCL, you can use ING-DNN. ING-DNN does do the optimizations for you, or you can do Android NN. The other option is the integration directly into the frameworks. And finally, you can use our offline tools to do model preparation and then the deployment using our NC SDK.
Okay, yes, I guess this answers my question. And we have one more question from Abdel. So he's asking about the tiling algorithm, if pretty much you're getting the right results.
So
because yeah, it's actually a very, very good question.
So this is why the NNA, the network accelerator, and the GPU are different. The network accelerator, the way you program it is static and is everything is pre-processed. So the tiling is all done during compilation time, not during runtime. So all the tiling is done by our compiler during the offline process and is based on knowing the internal memories inside the IP. So it is fully deterministic in terms of how it will be split. And the network accelerator has a very deterministic pattern on accessing data to memory. Our IPs have typically zero impact on performance up to 200 clock cycles of latency because we prefetch the data ahead of time. So we don't have challenging during runtime because our memory allocation is totally deterministic. It's not based in cache as a GPU or a CPU. We know exactly at any time where the data resides, and we'll be prefetching the data ahead of time. So it's not the same tiling that you will typically use in a GPU. Our GPU styling is different to our network tiling. And we have these internal discussions across the team. Sadly, the same point is it the same? It's a slightly different technique.
And then another question is about tiling. Okay, with performance, it's clear. And are there any effects on the accuracy of the results, especially if you are using some instance normalization, basically layer normalization techniques? Are there any? Yeah.
I'm not sure I understand your question there, Andre.
Okay, I mean, this tiling, is it somehow affecting the accuracy of the results?
No, so the maths are exactly the same. So there is no change on the maths. It's just a change of the processing, but the maths are identical. What we do is, and obviously there are layers we cannot cross. Typically a tiling group will finish on an activation layer. What we will do is we go backward. So you have to generate an output tile, and we work out all the input parameters that you have to process to generate the output tile.
Yeah, okay. Yes, I got it. Yeah, because we know that with on some hardware, yes, the tiling can lead to accuracy problems. Yeah, and yeah, if you're doing like this, there shouldn't be any issues. Oh, okay. Another question. What happens if input model tensors are dynamic in real-world scenario? Oh, by the way, yes. Also.
So this is a more challenging question. So at the moment, our tiling algorithm can only deal with static shapes. So we cannot deal with dynamic shapes. Okay. So you will need to do runtime recompilation, but you need static shapes to be able to apply our tiling. The whole compilation is offline, so we can currently only deal with static. We cannot deal with dynamic shapes. You will have to do. If you have a dynamic shape, you either have different pre-compiled model that can deal with all the possible combinations, or you will have, once you have the shape, you have to do the recompilation and then running. But the tiling algorithm is based on static shapes.
Okay, yeah, clear. Okay, thanks a lot for answering all these questions. So
Thank you, Andre. And for the audience, I mean, there are very good questions, and some of them I probably cannot answer them perfectly, but I have my group of experts that I'm pretty sure can reply better than me. So if there is any interest, don't hesitate dropping an email to me or contacting us, and we will be happy to help.
Okay, thanks a lot for the presentation, for all answers. And then right now we move to the next presentation, to the presentation of the, just a second, to the presentation of the smartphone image denoising challenge. I will share the screen. Okay, so we have already saw the results of the first learned image, learned smartphone ISP challenge, and the second challenge was camera image denoising on mobile GPUs. Why this task is so important? Because image denoising module is used in every single camera ISP. Mobile, non-mobile. In case of mobile devices, this is especially important since images that are produced by mobile cameras due to very small sensors, due to very simple optics, they contain lots of noise. And therefore, image denoising is one of the most critical tasks when it comes to raw data processing and post-processing of the resulting images. And besides that, yes, we also want to apply efficient denoising algorithms to noisy images that we already obtained with ISPs. I mean that that can be found in the internet, and this refers both to images, to videos, and so on. So, and in this task, in this challenge, we were solving exactly this task. So the goal was to perform accurate noise removal while achieving fast runtime on mobile GPUs. And first of all, dataset. Since there didn't exist any appropriate dataset for this task, the majority of datasets are using either artificial data, so which means that they also supply some artificial noise to some existing images, or the images contain just 10 static scenes that cannot contain various different noise patterns, different noise level, and so on. We collected our own dataset. For this dataset, we captured images, a bunch of images, 20 images for each scene, and then these images were averaged to get a clean photo. And these images were captured in different illumination conditions that were varying from moderate to completely dark. And more importantly, these images were shot both indoors and outdoors in different places. So it was not like indoor shooting. It was not about taking photos of some object located on your table and so on. No, it was about just taking a camera, moving forward, going outside, taking images in various conditions, and then generating the entire dataset. So in this dataset, we had more than 1,000 images of more than 1,000 different scenes, the resolution of which image is around 4 times 3,000 pixels. So this was the dataset. What about evaluation? We used 3 different metrics. The first one is PSNR for measuring fidelity, quality, fidelity scores, SSAM score that was used as a proxy for perceptual image quality, and the runtime of all solutions was evaluated on the Exynos 2100 chipset with Mali G78 GPU. And when running on this GPU, all models were trying to denoise images of resolution 720 times 480 pixels. As for evaluating the runtime of the models, for local evaluation, the participants used a benchmark application, and to check the runtime on the actual hardware, because this is also very critical. They had to upload their models to CodeLab server, and then Samsung Exynos team was running these models on the Exynos chipset and providing the results, and also some more details if the model failed. So in this this slide summarizes the results obtained in this challenge. There are a few notes that I want to say here. First of all solutions were based on the unit architecture, and this is not surprising because unit architecture, due to downsampling layers, they can also efficiently remove noise. Of course, they are removing details, but at the same time, noise is also gone. And when you are upscaling your feature maps obtained in lowest layers, it's possible to upscale only details without upscaling noise. And in this case, UNet is very efficient for image denoising problems. Secondly, all solutions ended up being very efficient. So for the solutions received from the first top teams, the runtime was less than 100 milliseconds on the images of 700 times 480 pixels. And for full resolution images, the runtime was usually between 1 and 2 seconds. We didn't measure it on full resolution images because at the beginning we tried to make everything slightly less complicated for challenge participants. They anyway struggled a lot when trying to develop efficient solution at the very beginning when they didn't yet know the particularities of this GPU. And therefore, yes, the final runtime was evaluated on small resolution images, but it was very good. And for full resolution images, the results are still quite okay. And what about the solutions? The first place was achieved. The challenge winner is Team Notch TCV. The idea proposed by this team is as follows. First, they just started optimizing a standard unit architecture, but they used neural architecture search for adapt its parameters for the target platform. Besides that, they trained a larger model, which outputs were used as targets that was applied to images outside that was applied to images not present in the provided dataset. So it was just trained on the existing dataset and then applied to some random images that can be downloaded from internet. Then the results, then the targets were generated with this model and used to train the small architecture that was developed as the final one in this challenge. And so this is basically a knowledge distillation approach. And the model was trained to minimize L2 loss function. So this is about the first solution. The second solution from team MagVI was also based on the neural architecture. And the main idea presented in this model was to use, in decoder blocks, was to use the concept of group convolutions. The idea is as follows. We take the input feature maps and we split them into two different parts or in more different parts, and each part is processed by a separate convolutional layer, by a separate convolutional block. And then the outputs of obtained after this layers are concatenated. And why this is used? This is used to decrease the computational complexity, because by using these grouped convolutions, you can significantly decrease the number of multiply accumulate operations. So, and the model was trying to minimize L2 loss, and in this challenge, this model provided very good quality of the reconstruction results. In the challenge, there were many other interesting solutions proposed by different challenge participants, and you can find their description in the paper. So thank you for your attention, and if you have any questions, you can now ask them in the chat. Okay. Are training and test images captured by a single Sony mobile camera? Is it straightforward to adapt a trained network to other cameras in the denoising task, or are you assuming fine-tuning to each camera so far? Good question. So in this challenge, all images were captured with the same camera. In overall, in the challenge, we actually used only a part of the dataset that will be released soon. And in that challenge, you'll have images captured by absolutely different camera sensors. Sony, sensors from Sony, sensors from Samsung, sensors released 5 years ago and sensors released just now. So we'll soon release a much bigger dataset with lots of images. And yes, So you are absolutely right, because if you are training the model on the provided data, you'll get a very efficient solution, but only solutions that will work good on the considered sensor. You can still apply it to other images obtained, images shot by different sensors, and it will work. It will provide quite good results, but these results, of course, will not be as good as one would like them to be, because noise properties, because the level of noise is very sensor dependent. And therefore, yes, we'll soon release much bigger data set, and by the way, this data set will almost definitely be used in the next mobile AI challenge. So instead of using the current set of images, we'll use a significantly extended data set consisting of images captured by lots of different cameras, and this will be your next task. This will be your actual goal in the next challenge, to create a model that can deal with this sort of data. Okay, any other questions? Okay, I guess we don't have anything else. Okay, then there is a very good question. So as far as I understand, the presenter Jihong Bang from Samsung, he had issues with internet connection. He's connecting to this session. So if you're here, can you please, if you manage to get to us, can you please write me a message in the chat? Okay, it seems that he was not able to, to get to our stream. And well, it's actually not a big problem, because we already have his slides that he prepared for this presentation. So in this case, after this meeting, we'll publish the recordings. His recordings, he will just record his presentation separately, and we'll release it on on our YouTube channel. So you'll be, the presentation is really great. So it was prepared quite a long time ago, and there were lots of details. He will tell you quite a lot of information about Exynos neural SDK, about different optimization options for their chipsets. So we'll publish it on the. Is the live stream going to be on YouTube channel afterwards as well? Yes, we'll try to publish all works separately and create a separate playlist, and you'll be able to check many of these presentations later. So, and well, as a matter of fact, I don't know if it's good or bad that we don't have right now Jihong Bang, because we are out of time. We're running out of time significantly, and right now we are still on schedule. Okay, just a second. I will add one additional presenter. Just a minute. And right now, since we have still 15 minutes till the next talk, I think that it's time to answer your questions that you wrote during the first presentation, because I saw that there were lots of different questions. So I will try to go through them and provide you with the answers. 1 second. Okay, good. So let's go to your questions that you answered before, that you asked before. So the first question, can we assume a linear relationship between power consumption and runtime? Is there any way to measure it? Well, it generally depends on whether you are telling about the same chipset or whether you are telling about different chipsets. For different chipsets, and whether you are telling about the same architecture or different architectures. So if you are using exactly the same model, then or on exactly the same device, then it's actually hard to say. One more second. Okay, yeah. So if I'm measuring exactly the same model on the same device, then usually yes, FPS per watt values are staying more or less the same. But you should understand that they are staying more or less the same only within some interval. So, as for instance, if you increase the run, if you decrease the runtime by 20–30%, most likely yes, it will be pretty much the same. But if you are going to some extreme values, for instance, you want to increase, you want to speed up the model by 10 times, then at that point the power consumption, it does not grow linearly any longer. So after reaching some performance level, any additional gain in speed will result in a huge addition in power consumption. And vice versa, if you are trying to, if you want to make inference really slow, that at some point it also won't be scaling linearly. At some point you'll get to some more or less constant power consumption level, regardless of the speed. If you really want to run something very slowly. And yeah, this is if we're running the same model on the same hardware. If we're running the same model on different hardware, of course, it's not proportional to the runtime, because it depends on the exact architecture that you're using, on the exact NPU or DSP architecture that is used for this. Because some architectures are more power efficient, some architectures are less power efficient, and in general, as I already demonstrated here on the slide, that okay, for the same model, we actually have slightly different results, and these results were for the latest generation NPUs. If we try to benchmark to check the power consumption of older NPUs and APUs and DSPs, the results there would be much worse. The power consumption of older APUs and NPUs is significantly higher, and FPS per watt value are not that good. So so I hope this answers your question. Then and yeah, I think that you also received an answer from Mika, and his answer was also good. Okay, flow to int quantization is always linear. Okay, Mika answered this question, and he can provide you actually with much better answers than me on this topic, as he is a part of TFLI team. Is it possible for high-resolution input to quantize only higher layers of neural network and leave high-precision calculations in lower layers? I think that Mika also provided you with the answer. So in general, yes, you can do this, but the problem is that usually you want to do this when your hardware supports, usually you want to quantize the models when you have NPUs that can support only int8 inference. So this is like a typical use case, because actually there are lots of different NPUs, especially in smart TV chipsets. The majority of NPUs are integer only. And as you saw, even on smartphones, there are lots of hardware that cannot run floating point models. Therefore, technically speaking, it's something that is possible, in theory it's possible to do, but you won't be able to run the resulting model on NPU. And running only a part of this model, well, it's possible, but usually this is not something that one is looking for. Okay, and next question is, oops. The next question is it possible? Okay. Okay, about mixing and matching delegates. Again, Mika provided you with a very good, with the best answer to this question. Regarding the delegates, again, the answers were provided. Any disadvantage of using Onyx runtime, as it also supports an API? Well, Onyx using Onyx runtime is actually, I would say this is not something that is currently used in production and used in some real applications. So Onyx, the main idea of Onyx is actually that this is an intermediate format for that can be used to transfer your models developed by one framework to models developed to another framework. So for instance, I have already demonstrated to you that you can use Onyx to transfer PyTorch models to TF-like models and vice versa. And right now, all optimizations, all improvements are actually pretty much happening on TF-Lite end. So, which means that TF-Lite is pretty much the first to receive new functionality to get the best on an API, to get good NN-API support. And in this case, Onyx, I mean, it's not something that is really useful here, because with TF-Lite you will definitely get better results. And for Onyx, again, it might be used if you want to run some PyTorch model. You can try to convert it to Onyx and then play with Onyx. But overall, I don't see any advantages here. Okay, next question. Do script dumps first inference performance as filling hardware cache or compiler overhead can impact single inference performance? Yes, of course, they dump the first inference, and not only the first inference, the first several inferences are dumped, and then also the outliers are removed. So this question was pretty much referred to inference results. Another question. What are the reasons for getting different accuracy on different devices of the same model? Very good question. The main reason for this is that, and is actually an NHEL. In an NHEL, you can introduce lots of different optimizations. And with some optimizations, you can achieve much better runtime at the expense of accuracy. And these optimizations, they can be applied for a very wide range of operators, and therefore, at some point, vendors might decide that. Okay, at some point, vendors might decide that okay, the current accuracy is actually excessive, and maybe some degradation is okay, and by just adding this optimization, they can speed up some models by whatever 10, 20, 30%. It depends in each case. So, and by deciding to do this, they also introduce these optimizations to the SNN API drivers, and therefore, after this, the runtime might be improved, but the performance, but the accuracy will go down. And besides this, there are also some issues related just to some problems related just to some issues, implementation issues, because you need to understand that, especially in case of TF-Lite GPU delegate, for instance, it has to work on pretty much all GPUs, all mobile GPUs, OpenCL and OpenGL based. And OpenCL and OpenGL is not something that works like a charm. So there are lots of different tricks how to make it work on different platforms, on different GPU models from GPU vendors, and there are lots of particularities. And overall, with OpenCL and OpenGL, there are lots of different problems and bugs. And sometimes to overcome them, you need to get a very strange construction. And of course, this also might affect the accuracy. And in some cases, some problems are solved, some problems might not be solved. So, I mean, it's not possible to solve, for instance, all issues related to OpenCL, OpenGL on every single chipset. And therefore, yes, for on some devices, you might also get some problems with performance just because of these issues. So yes, I think that I answered not only this question, but yeah, I also answered my own question. Okay, next question. Okay, accuracy. Okay, this was the answer provided by Mika. Okay, yeah, so pretty much the same. Okay. Why are these NPU performances different for different models? Well, honestly speaking, I don't understand. I don't understand what this question is really about. So, Fausto, you can just clarify your question. Because yeah, of course, NPU performance will be different for different NPU designs, and because I mean this is a completely different hardware design. I mean it reuses the same logic, it reuses the same principles, but in general, yes, the implementation is very different, and sometimes it's NPU designs and DSP designs, and yeah, especially NPU designs, they are derived from different even. How to say, from just a second. Okay, from different concepts, from different hardware concepts. And therefore, yes, of course, the performance will be very different for each NPU and DSP. The question was about FPS per watt measurements. Yeah, so okay, the question about why the results are different, why FPS per watt measurements are different for different NPUs, and again, yeah, the answer is because the data, because hardware design is different. Because you should understand that all NPUs, they are not like, it's not like the standard silicon that is just integrated to each every mobile chipset. So again, these the architectures were based on different principles, and in some cases, some architectures were even derived, for instance, from GPU like designs. In some particular cases, there were even these cases that originally just GPU architecture was taken and optimized for an inference. In some other cases, in the majority of cases, it's more about DSPs, but DSP is like DSP pretty much defines the general architecture, the general idea and general principles, how you're processing the data and what set of instructions are you generally using. But the exact architecture, it can vary significantly. And there are some architectures that are more power efficient, there are some architectures that are less power efficient, and overall, yes, this is not something constant. Okay, and I guess that we can now move to the next talk. The next talk will be delivered by Camille Kupri from Facebook. The talk will be about low bandwidth video chat compression using deep generative models. So, welcome, Camille.
Thank you very much. Should I start now?
Yes.
Okay, thanks a lot. So, hi everyone, I'm Camille, and it's a real pleasure to be here with you and to present the work of Maxime, Pierre, and many others, great team members on low bandwidth video chat. So, yeah, so there are millions of people who are in the situation of having a smartphone but suffer from poor network connection, making their video chat experience difficult when even possible. And furthermore, in many countries, data plans are restrictive and costly. So given the huge progress of face animation approaches, we feel that generative models could be very useful to these data saving purposes. So this video gives you an idea of what to expect from a video at 50 kilobits per second and at 5, And what we can achieve here using the first order model of Xiaowing and colleagues using only 4 kilobits per second. And even if we reduce the latent space by 16 times, we manage the quality remains high enough. So it was this observation that motivated us to design the following system. So we first extract landmarks or facial key points of interest on the sender's phone. We compress them and stream them to the receiver phone. Then a generative model reconstructs the face of the sender based on the stream of landmarks plus one reference frame that is sent at the beginning of the call. So this technique enables massive bandwidth savings since our model takes less than 10 kilobits per second, which is 20 times less than the requirement for a decent standard video call. So simultaneously to this work, another work called Maxine, based like us on the first order model, appeared. It is computationally intensive as it employs 3D landmarks and highly dimensional feature deformations, more than 100 times larger than ours. And consequently, the approach cannot be run on device, creating a problem of two-way applicability in a real low bandwidth use case. So if, for instance, I'm in a low bandwidth situation, I could send my landmarks to Maxine, but I would not have enough bandwidth to receive a server reconstructed video of the person I'm speaking to. So that's why I'm saying the bandwidth savings are limited to upload. So let's dive into our approach that we call the hybrid motion spade. So it follows an encoder-decoder strategy that learns to warp the reference frame embedding given the set of driving landmarks. So there is a dense motion that takes these landmarks and computes a motion field that is used then to warp the encoded reference frame embedding. And then there is a decoder that uses spade normalization blocks to refine the generation in key communication areas such as the mouth, the lips, and the eyes. So yeah, we use here spade blocks that are introduced by Park et al. So that are normalization layers that incorporate spatial information from semantic segmentation maps. And they are typically used to generate new images from layouts. Let's zoom to the decoder part to see how we build these segmentation maps. So in our case, the segmentations are obtained by plotting the polygons of the facial landmarks that are extracted using a standard landmark extractor, rather than running a face segmentation network, allowing us to save both power and bandwidth. And we then inject these segmentation maps to the decoder via spade normalization blocks. Some details about training. So we used the Vox Celeb dataset and the Deepfake Detection Challenge dataset. We use the same loss function than in the first order model methods, a multi-scale perceptual loss. We used mobile net like arcade blocks. And for the landmark detector, we tried different combinations. So the key points that are learned unsupervised from the first order model landmark detector. So it looks like this, a set of 10 key points that we denote 10 U as unsupervised. We used alternatively a set of standard facial landmarks, a subset of 20 of them, and a combination of the two. So we noted 10U plus 20L. To compress our networks, we used int8 quantization, and as a result, we have about 3 megabytes models. And the landmarks are compressed using Huffman coding. So using these different landmark variants and depending on the presence of spade normalization, we obtained different bandwidths and different timings. But we can say that all the models are running on real time and that low bandwidth constraints are respected. We know that the use of spade blocks only adds a small compute overhead. And in terms of bandwidth, the overhead is more important, about 6.5 kilobits. per second. So now let's see some qualitative results that run on mobile on real time. So here it's on an iPhone 8. Given a challenging compute budget, the first order model baseline suffers from several issues such as bad TIFF and profile views rendering. And here, using SPADE blocks, we observe improvements in the mouth area in particular. On this second video, we compare different landmark variants. And here we note changes, particularly in the background. For instance, the use of 20 landmarks, it doesn't reconstruct the background so well, given that the reference frame we are using has some hair here at the beginning of the video. And if we look at the zoom here, the 10 unsupervised landmarks results suffer from some head distortions that are visible here. And yeah, given this low computation budget, we noted that using the two sets of landmarks seems to take the best of both in this particular weak computation budget. We recover this observation in the metrics computed on Vox Select 2 videos. So the use of static landmarks instead of the unsupervised ones leads to an 18 improvement in normalization mean error between landmark coordinates. And we also observe this effect on mobile models. And note, in addition, the effect of SPADE blocks on the NME improvement here as well. Right, so last but not least, we picked a particular model, the one using 20 landmarks and SPADE normalization, and run it on different phones. We report here the frame per second on CPU, and in parentheses using the neural engine. And we observe using the neural engine 2 to more than 3 times faster execution. And finally, this video shows the reconstruction of Pierre's face on our app, and here is a reference frame. You can maybe see some chessboard artifacts that we now removed using a discriminator loss. Okay, to conclude, we designed a novel low bandwidth phase video compression approach, the first one that is able to run on real time on mobile. Our hybrid architecture takes advantage of high fidelity to the target image, thanks to the warping principle, and hence enhance the quality of important attributes with SPADE blocks. And there are a number of interesting research directions to improve the quality of the generations. We aim, for instance, to improve large head rotation movements, expression renderings, and battery usage, among others. Thank you.
Thank you, Camille, for the great talk. Are there any questions from workshop participants? Okay, there is a question from Sangbon Choi. As far as I understand, this kind of work purpose of WebRTC.
Excuse me, I didn't really understand the question.
Well, I think you should also be able to see this question in the chat.
Sorry, yeah.
Yeah, I think that the guy was pretty much asking if you are developing this, well, if probably communication for video translation you are using WebRTC, and if you are pretty much.
Yeah, so sorry about my background. That is more on the image generation side than mobile. But I think yes. I think the answer is yes.
Mm-hmm. Okay, and okay, a question from me. So, will the solution appear in Facebook, Messenger, or in Facebook applications? Yes.
Yeah, I'm a researcher at FAIR. So our goal is to make progress in the model mainly, and if the quality becomes high enough, the objective would be to put it in products someday.
So the work is still ongoing.
Yeah, the work is still ongoing.
Okay. Well, it would be interesting to see the follow-up results because the current ones are looking really impressive. Okay,
Thanks.
then thanks a lot for your presentation. And if we don't have, okay, I will have another question to you.
Yeah,
yes, can it work when multiple phases overlap?
So for now it only reconstruct one phase at a time. So we use landmarks that are tracked. So yeah, it's if the landmark detection is performant enough, it should track the same person through the entire call. That's a principle that we.
Okay, then thank you for the explanation. And we're then moving to the next presentation. This presentation will be delivered by Haojin Yang. The title is AsymNet towards ultralight convolutional neural networks using asymmetrical bottlenecks. And Haojin Yang was previously working in, I guess, Alibaba Cloud, and right now in either has a partner institute or in Binance. Unfortunately, I don't remember. Okay, welcome, Haojin.
Thank you very much. Thank you so much for the introduction. Hello, everybody. So to ensure a high quality of the presentation, we actually prepare a video presentation and we upload to the YouTube, and I will just play this video. I'm not sure whether can you hear the speech, or I'm not sure whether I enable the audio deliberation.
Yes, you need to select in the settings. You need to select share.
Yeah. Okay.
Audio.
I will.
Computer audio.
Okay. I will share it again. Okay. Okay. Let's start.
This talk will introduce AsymNet, a novel design for ultralight convolutional neural networks based on asymmetrical bottlenecks. The recent success of deep convolution neural networks is like the jewel in the crown of modern AI waves. However, the current CNN models heavily rely on high-performance computation hardware, such as GPU and TPU, typically deployed in a cloud computing environment. For example, the ResNet 152 first surpasses human performance on image classification tasks. But it requires 240 megabytes of storage and 11.3 billion floating point operations. Another example. The recent pre-trained language models have pushed the definition of large models to another level. Therefore, such networks need to run on powerful servers in the cloud. Thus, the client applications have to transmit user data to the cloud to gain deep CNN models benefits. This constraint strongly limits such models' applicability on resource-constrained devices, such as mobile phones, IoT devices, and embedded devices. On the other hand, the impact of large-scale AI computing on the environment cannot be ignored. For example, the energy consumed to train the GPT-3 model is equivalent to 43 cars or 24 US families per year. Therefore, in recent years, various works aim to solve this problem by reducing memory footprints and accelerating inference. We roughly categorize those works into the following directions. And this paper falls into the class of dedicated architecture design. Image classification models serve as a cornerstone in various applications. These different network architectures have evolved over the past few years. Just like Tony Stark's armored suit, we can see that MobileNet v3 is probably the most efficient and most popular backbone model for mobile applications. The MobileNet v3 includes two very effective design choices: depthwise separable convolution and the inverted bottleneck block. The depthwise convolution layer applies a single 3x3 filter to each input channel to learn the spatial correlation, and then applies a 1x1 convolution to learn the channel correlation. Thus, in the inverted bottleneck design, the first pointwise convolution expands the information flow, increasing the capacity. The depthwise and the second pointwise convolution are responsible for the expressiveness. This speculation is derived based on the analysis of the MobileNet v2 paper. Another strategy frequently used in recent works is the cheap operation for more features. For example, they are used in ShuffleNet v2 and GhostNet. The input feature map in ShuffleBlock v2 is split into two equal channels of narrowed feature maps. One is transformed with a particular bottleneck block without internal dimension changes. The other keeps unchanged until concatenated and shuffled with the altered feature map. In the Ghost block, more cheap features are created by copying features and using depthwise convolutions. Based on the saved computation, the Ghost block can have more convolution layers. The table shows the complexity evaluation results of different types of convolutions of MobileNet models. We observe that the computation overhead is mainly concentrated on the pointwise convolutions. If we want to reduce the computational complexity, the optimization of this part is the first choice. Our proposed idea, in short, is to apply the feature reuse strategy on the first pointwise convolution for effectively saving the computation. And we correspondingly extend the feature flow of the depthwise and the second pointwise convolution layers, where we think they are more critical for the expressive ability. Overall, we keep the computation budgets unchanged. To this end, we propose two slightly different block designs: pruned block and asymmetrical block. We verified ASIM-net on 5 different vision tasks and obtained the following two conclusions. 1. Compared with MobileNet v3, ASIM-net can generally get a better or same level of accuracy. 2. Especially in the interval where the number of multiply accumulation operations is less than 220 m. The performance of ASIM-net is fairly better than that of MobileNet v3. Thank you for listening. For more information about this project, including code and paper, please visit our website.
Thank you for the presentation, for the recorded presentation. Are there any questions? Okay, seems like no questions. Okay, I will ask a question. What speech generation engine did you use?
I'm sorry,
What speech generation engine did you use?
Speech generation?
Yes, yes.
I just search for a open source tool online. So I don't remember. I can send you the link afterwards.
Okay, good.
Yeah.
Okay, no, it actually looks very good.
Thank you.
Okay, so thank you for the presentation. And then, if there are no questions, we move to the next talk. Next talk will be delivered by Jiaxin Li. He is from University of Illinois, and the talk title is Pseudo-IO, Improving Label Assignment for Answer-Free Object Detection. So welcome, Jiaxin Li.
Yeah, thanks, Andrew. And I'll share the pre-recorded video with our presentation. Hello, everyone. This talk is about Pseudo-IO, improving label assignment in anchor-free object detection. Label assignment is important for object detection, which is to assign positive and negative samples for training object detector. So for anchor-based methods like FastRCN, they assign labels for anchors by computing the IOU between the anchors and the ground truth. So for anchors that have a higher IOU with ground truth, they are assigned as positives, and for those with lower IOU, they are assigned as negatives for training the anchor-based detector. However, for another group that is anchor-free object detection, which predicts the final detection results directly from the points to the box and does not require anchor priors. Well, they're more simple and lightweight compared with anchor-based methods. Well, however, they do not have accurate label assignment rules, and they view all these samples instead of the ground truth as training samples, which is inaccurate compared with anchor-based methods, and it constrains performance of the anchor-free methods. So based on this observation, in this paper, we propose pseudo IOU, well, for improving the anchor-free object detector. So for example, like for this object, for this point P inside this ground truth, it assigns a pseudo box that is centered at the point P and has the same dimension to the ground truth. Then it computes the IOU between the pseudo box and the ground truth box as the pseudo IOU value for the point P, which is 0.57 here. And based on this design, we add this pseudo IOU to this anchor-free object detector baseline, which uses ResNet as a backbone with the feature pyramid network. On each detection head, it makes predictions on both classification and regression. Well, based on the positive and negative samples classified by the pseudo IOU threshold. And in the application study, well, it shows that the pseudo IOU improves the anchor-free baseline by a large margin, which brings a nearly 3% improvement on MAP, and make it better than the one-stage anchor-based method retina nights. And also, it is compatible with other tricks like GIOU or centerness for further improving the anchor-free object detector. And also for other experiments on the MS COCO dataset, it shows that pseudo IOU can bring consistent improvements with different backbones. And to further improve the anchor-free object detector without adding extra computational burden for both training and inference. And here are some visualization results. Well, the first rows are some anchor-free baseline detections, and the second row is the same baseline, but which is based on the pseudo IOU label assignment training process. Well, it shows that detectors with the pseudo IOU can effectively reduce some false positives by providing more accurate positive training samples. Well, that is all of our presentation today, and thanks for listening. Yeah, that's all for our presentation, and thanks.
Thank you too. Are there any questions to the speaker? Okay. Looks that everything is clear to everyone. Therefore, thank you for the presentation. Thank you for presenting your paper at the workshop. And then we are now moving to the next invited talk. This talk will be delivered by Mika Rento and Przemysław Szczepaniak from Google. And you remember that I told you something about an API and TF-Lite. These guys are the ones who are working on this topic, and they can pretty much tell you much more detailed information. And if you have any questions about an API, if you want to know a little bit more about how it works and what is the future of an API, then you should check this presentation, watch this presentation, and don't forget that this is pretty much your only option, your only moment where you can ask the questions to an API developers, to the actual teams that stand behind the entire API ecosystem. So welcome, Przemysław Szczepaniak, and welcome, Mika.
Thank you, Andrei. Thank you for kind introduction. I'm Przemysław Szczepaniak. I'm a software engineer at Google, working on Android Neural Networks API. I have a presentation about, is my screen visible?
Yes, yes, yes.
That's great. Right. So I'm going to give a presentation about the recent developments in NN API. And for the second part, I will hand over to my colleague, Mika, to talk about best practices for optimization. So like Andrei explained in the earlier part of the workshop, is an API for accessing dedicated hardware accelerators for machine learning on Android. It allows to access additional compute cores like NPU or DSP, and allows you to get access to additional compute power. And with the right set of models and configurations, you can get lower latency, better power envelope, better thermal output. And we recommend to use an API from Android 10 onwards, due to various issues, problem, and inconsistencies in early NN API implementations. NN API been always released in sync with Android OS. So we always have a single NN API release every year. And that means that if there's any new functionality that we would like to add it to the NN API, it can, in the worst case, take a year. Then it can take up to multiple years for that functionality to be widespread enough to be considered like commonly accessible. So it takes multiple years for the new functionality to be actually usable by machine learning engineers using machine learning. So we would like to address this problem by moving to regular updates outside of desert releases. That means two things. We're looking into updating the NN API specification itself outside of Android release, and we're looking to distribute updated drivers outside of Android release. And so we have a scheme where we're distributing drivers through Google Play services. That basically forms a parallel NN API stack with the updated NN API driver accessible on participating devices. We're looking to have one driver version across devices with the same chipset. So for example, if there's a Qualcomm 888 SoC, we expect to see the same driver across all the devices using that chipset. And the features will be backported for the commercial life of chipsets. So we're expecting to see any new operations being added and deployed on those devices. And we're rolling this out this year with Android 12. So the basis of the current scheme of updatability is a support library and an API driver. The support library is Android specific term. It basically means a library, something that you compile for your application that allows you to backport features from the newer Android versions and have them available on larger set of Android OS devices. So it basically allows you to backport functionality from your Android. And we're doing that with the NN API driver by creating an in-process NN API driver that talks directly to hardware interface. It has almost no dependencies on platform itself. It's a self-contained NN API runtime compiled with driver code in the form of shared library. It exposes the same API as NN API runtime, allowing to use the existing code with minimal changes, and allows to reuse existing NN API driver implementation by doing a minor refactoring by switching to what we call canonical types that provides abstractions away from the existing driver implementation. And the first driver will be released for the Qualcomm 888 series devices. So the support library driver, like I've mentioned, exposes CAPI. That is exactly the same, basically a subset of platform and an API exposed by runtime. There's basically a copy of a runtime in form of compatibility layer. It's a special version of runtime that is meant to expose a set of the devices implemented using canonical types. And we expect vendors to write a code, convert existing code to switch from idle types to canonical types. And as long as the set of the dependencies it uses is reasonable, it should be fairly straightforward transition. So for devices that will get updatable driver, there will be really two versions of an API on the device. The fixed version on the ROM that is been tested for the OEM approved features. It's been roughly tested by OEM. And the second updatable one, which can be used for access for latest features. An application can choose between those two. The updated driver will be distributed through Google Play services. So in order to make use of it, an application will have to create a dependency on the Google Play service. And Google is responsible for driver testing, distribution monitoring, rollbacks, and so on. And drivers will be updated without any changes to the client application. So this is slightly different from most of the schemes that exist right now that requires a participating application to recompile to get access to the new functionality or updated driver. So this is not required. And the changes for loading support library driver already exist in TSI's GitHub in the code for the NN API delegate. So the application is expected to ask Google Play services for list of available support library drivers, ask for a specific one, and it will be loaded in the application process and can be passed to the NN API delegate that will then make use of it to provide hardware acceleration. We are also working on making changes to NN API specification between those releases. So introducing a new concept or new of a feature level. So previously, NN API devices exposed feature level that they implement, which corresponds to the Android OS level functionality. We're extending that and introducing a runtime feature level, which can be updated independently from the Android API version and defines a set of the features that is available by either the platform runtime or the support library driver. We will be developing the specification in the ASP, Android open source project master branch, which will be used as a single source of truth for what is the NN API specification, and all the feature levels being defined will be available there. If someone would like to participate and try to make use of it, we start an early access program. The changes to client application should be fairly minimal. A dependency on the NN API support library GMS for client, a few lines of code to fetch and enable the library, and the configuration to select the appropriate accelerator. There's a link here that leads to the form for sign up for early access. So that's it. I will hand the presentation over to my colleague Mika.
Thanks a lot, Shemek. So I'm indeed a colleague of Shemek's. I work on NNAPI. In addition, I also work on a new product we announced at I/O, which is called TF Lite for Android. So we're also going to distribute a version of TF Lite pre-installed on Google Play Services devices. And I also work on what we could call automatic acceleration. So way of managing acceleration across the Android ecosystem. Let me also start the presentation. Just a second. Maybe Shemek, can you just pull up the next slide though?
Sure.
Yeah, maybe I'll ask you to try. Sorry about that.
Sorry.
Right, so actually, Andre and other speakers have talked a lot about the differences between different Android devices. So if you think of sort of customers for ML on Android and NNAPI specifically, those can fall into two major buckets. One is OEM applications, so applications that are built for a specific device and delivered with that device. And that works like for those applications, these device differences are something that is part of the development cycle maybe, but it is not really a deployment time issue. However, for third-party applications, which want to run on all kinds of Android devices, this is a major issue. So we've been talking a lot about hardware acceleration today, and the reason is that you can enable new use cases. So let's take some of the examples around, for example, video processing. Those might just not run acceptably on the CPU. To be able to run those experiences, you want to run on the GPU or on an API. However, there are differences between Android devices in terms of performance, in terms of also stability. So things like crashes, hangs, or whole system effects, as well as accuracy or correctness, as Andre was also talking about. So in practice, people who deploy hardware acceleration at large scale on Android tend to do two things. They need to be able to monitor the behavior of their feature on a device. They need to get telemetry from that monitoring, and they need to be able to turn on and off features based on the outcomes of these. So this is what several Google apps also do, and one of my teams runs part of this infrastructure. This is quite a lot of things to run for a third-party application developer. So what we're trying to do is that we are slowly bringing out most of this machinery in a way which is easy to use by anybody. Next slide, please. So as part of indeed TF Lite for Android, we will be bringing out a fully productized version of this, where from the developer's perspective, the main thing they need to do is to be able to define what correctness means for their model and opt into using telemetry and allow listing as part of a Google Play Services module. And we will support not only NNAPI, but also GPU. Because as Andre was saying, the GPU delegate is one of the biggest benefits of the Android delegate, of the TF Lite delegate ecosystem, as it provides coverage of roughly half of the Android ecosystem, whereas NNAPI is still on a much smaller percentage. Next slide, please. So the first part of this is the first step that we are actually taking is that we are just managed to open source the part is called the mini benchmark. Wasn't meant to copy the name of AI benchmark, but it has some similarities. So the mini benchmark adds an ability to include correctness checks in TF Lite models. So like AI benchmark runs accuracy tests as part of its running. This is meant to do something quite similar, but in a production app. So we are using a fairly small number of golden input-output pairs to detect whether a certain accelerator can run correctly. We are typically doing something like 5 images for things like labelers or detectors or segmenters. Segmenters might even be able to do a couple of images only. And we are reasonably confident that we can pick up like at least material regressions in accelerator backends by using a fairly small set of images. And the reason we are confident, we are using like as much of the model outputs as we can. So for example, rather than doing top 1 or top 3 or top 5, we are actually like calculating a KL divergence over all of the classes for a mobile net, or for a segmenter, we will look at all the pixel outputs. And in our sort of testing of this approach versus the known good and known bad drivers, we have been able to typically detect issues that were detected in larger scale accuracy tests. And from a model developer or application developer or application deployer, creating 5 inputs is much more feasible than having a complete accuracy data set. And the other one is that the size impact is small enough that you can ship this in a production app. So we use JPEG compression, and adding 5 JPEG compressed images to a TF Lite model typically somewhere between like 50K and 100K, depending on the input size. And typically that is something like 5% increase on the model size. So that's how we are checking for correctness. Shimak, next slide, please. And the other side is checking for stability and performance. So as part of this code base in TF Lite, we have a safe sort of runner that runs benchmarking in a separate process. This allows the application to be fully shielded from any adverse effects that might be caused by trying to use acceleration. I don't want to like dig into all the bugs that we have, but I'll give an example of something that is quite hard for applications to manage on their own without something like this. Is there are historically GPU drivers that if the compilation shader compilation takes too long or uses too much memory, they will just exit the process, which is super hard to capture in terms of telemetry because it just looks like a successful process exit. Whereas here, by running all of that code in a separate process, we are able to catch those kinds of issues. This is also meant to be like embeddable in a production app. So the size impact in a best case, this might be 80K, when the app is already including a lot of the dependencies in this, but also so somewhere between best case and normal case. But we are shipping this in a couple of products. So we think it's acceptable for a production mobile app or SDK to include this. And then we also, one of the issues with benchmarking on Android is getting the code to run in a way it's representative for real applications. So the runner uses core affinity to get this roughly the same behavior as a real app would get. Next page, please. And I put some examples from running some of those open source validation tests on a couple of devices I had, just to pick on some of the examples of why we are doing this. So the first one is running a face detector model on Pixel 4. This is a fairly large single shot model using integers. And we can see that we are getting best performance on NNAPI. We are seeing like a 4 millisecond inference time compared to maybe 90 milliseconds on the CPU and 17 milliseconds on the GPU. So this is a good example of where NNAPI gives you a real benefit for the model you're running. Whereas the two other examples are on a Blaze face model, this is one variant of something that Google Meet uses to do background blur. in open source as part of TFJS. Is here, this is a model that was developed for GPUs. It's a floating point model. And we can see that the GPU delegate actually gets the best performance at 2 milliseconds per inference versus 8 milliseconds on NNAPI and 25 milliseconds on CPU. And the last one is sort of a different example of why we are doing is that this is running on an Android 10 device, so a couple of releases ago, where I think the NNAPI test suite didn't have like a representative example of something like place phase. And we see that we actually are getting incorrect results on the NNAPI backend. So here, even though we would be getting a 2x improvement in latency, but we cannot use NNAPI on this device for this model because we are getting incorrect results. Here also the GPU delegate does provide the best latency. For now, in terms of the reason, one reason still to use, by the way, NNAPI is that NNAPI is pre-installed, whereas GPU delegate is not yet. So we are planning to have the GPU delegate as part of the TF Lite for Android product, which would make that also pre-installed. We're not quite there yet. But by signing up to the EAP, you'll be able to sort of get this as soon as they start coming out. Maybe last page. So we want to also highlight a few other best practices about NNAPI. So one way of looking at what we just talked about is that if you want to use NNAPI, you do need to test somehow whether your model runs well on it, either by using a mini benchmark that I described or having your own testing procedures. And of course, there are apps that don't run on all Android devices, and testing is much more feasible. I think we touched upon somewhere in talking about AI benchmark, the idea of first frame versus steady state. So definitely all of these acceleration technologies incur an initialization overhead of some kind, including NNAPI. So if you are using NNAPI, it is quite important to use compilation caching so that you can do as much of that extra initialization once rather than every time. And Shemek mentioned that really NNAPI is recommended from 10. On 9, we had some hang issues. It's a good example of why we started building some of this infrastructure. Two more things. One is that there was also a discussion on the chat about asynchronous. NNAPI does actually support asynchronous execution. And this is sort of feasible to get through by delegate-specific methods in TF Lite. And we do see like a significant improvement on certain vendor devices by using shared memory and sync fences to talk to NNAPI. Just as a warning, not all drivers implement this yet. So, and when they don't, it's a slight de-optimization. Just want to like give people realistic expectations on the amount of improvement they get from those features. And then finally, NNAPI does include CPU implementations of the operations, but from Android 10 roughly, those implementations are meant to be reference implementations. So they are a tool for especially driver development so that people can compare CPU implementations and hardware implementations. They are not competitive with an updated TF Lite. So if you are using NNAPI, we would recommend using the higher level framework, TF Lite or something else as your CPU fallback path rather than letting NNAPI handle CPU fallback. All right, I think those were the main points that we have prepared to talk about, and we are more than happy to take questions.
Okay, thanks a lot for the presentation and for actually telling me very useful information. So if there are any questions, you can write them in the chat. And while, yes, there are still no questions from the speakers, okay, I will ask some questions. So first of all, yeah, you mentioned that updatable drivers were launched together with Snapdragon 888. What about chipsets from other vendors? So is this something that is about to happen, or?
So I'll just be transparent that we cannot talk about unlaunched products, especially with partners. But we are talking to multiple other SoC vendors who are interested because they suffer from the same problem that if they have their own stack, they need to convince people to embed it in their applications. And if they only do platform, their implementation lags behind. So it is a general problem for all SoC vendors.
Okay, and for the existing chipsets, this functionality won't be available. For the chipsets presented in the past.
Yes, I think here, since we actually have like a joint announcement, so with Qualcomm, we are not planning to support previous chipsets. However, some other SoC vendors are open to that discussion. It depends a bit on how their internal development cycles go, how much cost it is to support earlier chipsets. So it's not, for Qualcomm, we are not, but for other chipsets, that might well happen.
Okay, good. We have some questions from the guys. The first question is about, do you have support for transformer architectures, for instance, for batch matmul operators?
So we don't have full support. So batch matmul is supported through unrolling in TF-Lite. We also are missing cumulative sum, which some transform models use, not all. So let's put it this way: there are some transform models that will run on current NNAPI, and some that will require new ops that we are hoping to introduce in the upcoming releases.
Okay, thanks for the answer. Okay, there is also a question from Abdel, good question about the complexity of NNAPI certification, and that using TF-Lite delegates is actually much easier for vendors to optimize and implement. So can you address this situation?
So I think in terms of becoming more complex, I think we would love to, like, in our other discussions with the vendors, to get feedback on specifics on which parts are hard and see if we can make them easier. Definitely, I know that the re-architecting we did will have caused some pain in terms of having to re-architect the drivers. However, it should also reduce the complexity from the vendor side, because they actually need to implement less, because we are now taking over sort of a larger chunk of the stack. In terms of TF-Lite delegates, the main a reason why a TF-Lite delegate would not be feasible for third parties is if the hardware doesn't have a safe access point outside NNAPI. So in many cases, these NPUs, for example, they do need, or DSPs, they need a HAL, and that HAL can hopefully be NNAPI. So the security issue is one reason why TF-Lite delegates might not be suitable for all hardware-software combinations.
Well, I guess this answers the question. Okay, then a related question: are there any? Do you have in plans any major NNAPI updates? I mean, in terms of revising the entire architecture and revising the way how communication happens, how an NNAPI drivers communicate basically with an NNAPI. I mean, it's more about architectural.
Yeah. So let me try. So I think if we think of NNAPI, there's two large parts. One is how do you actually program it, which is this sort of sets of ops, very close to TF-Lite or ONNX, or that we think is viable. We know that there are compiler-based approaches in the industry. We don't currently have plans to switch to those, though we keep an eye. So the op spec, we hope to keep because we think it is sufficient to serve like majority of needs. In terms of architecture, we actually implemented several improvements in Android R and S in terms of making sure that sync fences and hardware buffers work well. So I think what we really hope to work together with vendors is to make sure that those are plumbed through as far as possible, because those will indeed enable low overhead in an API usage, because there will be like just the path from triggering an inference to having something running on hardware is potentially much lower with sync fences and hardware buffers. And we have seen this with some vendors who have been able to reduce the overheads about 5x. But this is something that we need to work together with the driver implementers to make sure that it's plumbed through. So it's not so much re-architecting as it is making sure that we are able to take into use the hardware buffers and sync fences.
Thanks for the answer. Then we have another question about, good question about non-API support running different ops on the same model on different hardwares. It's more like about partitioning the model and executing it different accelerators.
Short answer is yes. So if you give an API a model where, let's say that you had a mixture of integer ops and floating point ops, it could split that between a GPU and a DSP or a TPU. There are also drivers that do this. So some vendors have implemented drivers that can multiplex models over many of their IP blocks. These not necessarily very performant. It depends on how many switches you have between IP blocks. If there are many switches between IP blocks, the overhead will probably dominate and you will lose your benefits. If there's a very small number of switches, then this is actually useful. It's also, just as a very, like a simple example is, something that is fairly common is that you have a TF-Lite model, which includes some post-processing that runs on the CPU, whereas the rest of the model runs on NN API. And this is something that can perform quite well. The similar splits of models can also run quite well across other sort of multiple accelerators.
Okay, thanks for the answer. And probably the last question from me. So is there anything else that the workshop participants and those who will be watching us later need to know about NN API in the next Android version? Are there any additional changes, or is there any additional operators that were added?
Shemek, I'll ask you because you're much closer to the platform than I am.
So currently, we're focusing on providing the updatability, the driver updatability and specification updatability, and we're not providing any new functionality. We do provide minimal new functionality in the Android 12. I think we're adding support for reusable execution context that helps with reusing the same buffers for the execution. That brings some benefits for some models. And we also added support for padding, for explicit padding for buffers. But for the time being, we're not introducing any new functionality. We're focusing on providing the updatability. It's more important for us to be able to do so. And when we'll have working updatability schemes, we'll be able to introduce new operators, new data types with it will be significantly easier to do that.
Oh yeah, updatability is something that everyone was looking for quite a long time. Okay, if there is nothing else, if there are no other questions, then thanks a lot for presenting information about new functionality, about updatable drivers, and about how to check the models, check perform sanity checks of the models that you plan to deploy on different hardware. And yes, thanks a lot. And okay, now we will move then to the next talk, actually to the presentation of the quantized image super resolution challenge. Okay, 1 second. So the third challenge that we had was quantized image super resolution, and I don't think that this task actually requires an introduction because the importance of this problem is pretty much known for everyone. We want to apply super resolution models when to upstream media data available in various social media channels. And for instance, we also want to exchange this data on YouTube because there are lots of videos captured in low resolutions. There are lots of videos captured a long time ago, and the quality is not okay. Besides that, right now you can find super resolution models in many telephoto camera solutions, which means that usually they use a hybrid approach of utilizing both optical zoom and using super resolution model either on top of it or to perform gradual shifts to perform gradual zooming, to perform continuous zooming. And in this challenge, we were solving exactly this problem. The task for the participants was to perform accurate 3 times image super resolution. Another task was to achieve a real-time performance on mobile NPUs and actual smart home NPUs. And finally, the model had to be fully quantized. This is what I mentioned in the introductory talk, that in this case, we had to get a fully quantized models because the models, if the model had floating point inputs, outputs, if it had floating point operators inside it, then the model would not run on integer, on the NPUs. And for the dataset, we use the standard diff2k dataset. Probably everyone knows quite a lot about it since it was used in numerous previous challenges. It consists of 1000 diverse 2K resolution images with lots of different contents from people to cities, natural objects, natural sceneries, and so on. The evaluation of the solutions was performed based on 3 metrics: PSNR scores for measuring the fidelity results, the quality of reconstructed images, SSAM scores as a proxy for perceptual quality, and the runtime was evaluated on the Synaptics VS680 HASOC with VeriSilicon NPU. And upsampling was performed from VGA to Full HD resolution. And this is something actually quite close to what we need in production, because there are lots of VGA videos. You can find lots of VGA videos on YouTube. And of course, when using high resolution screens, when using recent devices, we want also to improve their quality. And this also applies to various video streaming services and so on. For local evaluation, the participants used a benchmark application for testing their solutions on the target platform. They had to upload their models to Codelab server, and then Synaptics team, it was running these models on the actual hardware. Because this was a very critical part in this challenge, because participants were not able to to access this platform directly, and therefore this option was selected. And besides the runtime, Synaptics team also provided the participants with the detailed feedback regarding the objects that are not supported, that are partially supported, that should be changed, and so on. And on this slide, you can see the overview of the results obtained in this challenge. The first thing that I should mention here is that only 5 teams were able to outperform the standard bicubic upscaling algorithm. And the main reason for this was quantization. This is what I also talked in the introductory talk. When you're performing image quantization, performance loss is inevitable even for image super resolution task. And for instance, in this column, you can see the degradation, accuracy degradation obtained after quantization. With additional tricks, the accuracy degradation is not really huge. So it's around 0.2 to 0.3 dB per SNR. But if you just quantize the model as is without actually adding any additional, without adding any structural modifications, without just taking your model and applying post-training quantization tools, then you might get results like this. that the performance will drop by 4 dB, 9 dB, 13 dB. And this is one of the takeaway messages that if you want to do quantized quantize image processing networks, then always check the accuracy of the resulting models from the very beginning. When you develop the model, you train it, quantize it, check what is the performance drop of this model. Because you might end up in this situation when you need to redesign, when you need to add some additional tricks, how to maintain the quality of the obtained solutions after quantization. The other thing that should be mentioned is that the performance of top solutions was really great. So they were able to achieve 23, 24, 25 FPS on the target Synaptics platform. And this is also, it's pretty much close to real-time performance. With some additional optimizations, it's possible to go over 30 FPS, but these optimizations were not considered in this challenge. And besides that, I should also mention that technically speaking, the best results were obtained by team MCG, but unfortunately, at the beginning, this team also struggled on quantization, so the results were pretty much the same as with these teams, and it was able to fight quantization problems only after the official end of the challenge. And so overall, we had several very interesting solutions that significantly improved over bicubic upscaling baseline, and I will now go into more details about these solutions and architectures. So the best official results were obtained by team SSR research, and here the main model was based on, again, on the group convolution concept that was mentioned in the image denoising challenge that I mentioned for one of solutions proposed in the image denoising challenge. So again, how it works, you take your input feature map and split it into several parts, and then you apply convolutional layer. You apply convolution to each part separately, and then the outputs of the convolutional layers are stacked together and passed to the next layer. And again, this is used to significantly reduce the number of multiply accumulate operators. And as a result, the complexity of the model will also go down, and its runtime will be improved significantly. And this was the main idea behind the proposed architecture. Because of this, this team was able to add several quite large blocks to this model, and at the same time get both good fidelity results and good runtime. And the model was trained to minimize Chebonier loss function, and standard post-training quantization was applied to it. The next solution, this is actually the best performance solution that was submitted after the official baseline. You can see this architecture, and it used actually a very interesting idea. So image upscaling, it used several standard, just normal convolutional layers, and additionally residual connection, where the authors additionally performed image upscaling. And as you know, upscaling operation is usually quite expensive, especially if you are using like bicubic upscaling, nearest neighbor upscaling. Well, nearest neighbor is slightly better, but anyway, upscaling is quite expensive. And here the guys proposed to do the following. They just stacked the input image scale times. In our case, it's nine times, since the model was performing 3 times upscaling, and then applied a depth to space layer on top after performing this stacking. What will you get after applying depth to space? You'll actually get an image upscaled by 3 times, where each pixel will be repeated 9 times. So you'll get blocks. Upscaling will be basically performed by repeating these pixels multiple times, scale time. And the main idea here is that by combining stacking plus depth to space layer, actually you don't need to do any computations at all. These are just purely logical operators, and if they are supported by the corresponding hardware, then you are performing upscaling almost for free. And because of this, the authors were able to add several convolutional layers one by one, more convolutional layers than can be found in some other works, because in this case, because this upscaling operation was not consuming lots of computational budget, and it was possible to spend it on adding extra conv layers. And the model was also trained with a one-loss function. And originally, this is what I told you, that originally there were issues with quantizing this model. The issues were mainly connected to the final layer of the model. Because if you are making this layer, if you use an integer layer on top of the model, then when quantizing, TensorFlow Lite can also scale the outputs. And therefore, even if the original model was outputting the correct values, they will be scaled. And for instance, instead of for pixels that originally, which values were originally 200, they will be changed to, for instance, 180 or 50 or whatever. This depends on the actual architecture and the actual data that was used for post-training quantization. And to fix this issue, to avoid this problem, the easiest way is to add some linear operation on top of the model. For instance, you can add ReLU operation. And after applying, well, not linear operation, but actually pretty much thresholding operation. Oh, yes, it's also linear operation. And after adding this, the scaling will no longer be applied. So the outputs will be, the model will produce the outputs without skewing them, just as they were obtained before the last layer. And this was the main trick, how to achieve good numerical results after quantization. Here is a solution proposed by North Terminal Evaluation team. And the main idea here was to use also one additional skip connection and to use several residual blocks for doing a major image processing. And the others additionally use space to depth and depth to space layer to reduce the amount of computations. And this solution was very small, very tiny, but anyway, it was providing quite good results, and it was trained to minimize L1 loss function. And the solution submitted by Team Along was following pretty much the same idea. It was using skip connection for upsampling the model, and this upsampling was actually performed by nearest neighbor resizing. And again, several skip connection blocks, and then the others applied pixel shuffle layer on top of the last convolutional layer, and combined the outputs of the residual block with the outputs obtained after applying image upscaling. And the model was trained with L1 loss and fine-tuned with L2 loss function. And right now I provided pretty much a very brief description of the solutions. If you are interested in how to get good quantized model, and if you are interested in going more into the architectural changes approaches developed by different teams, and check this paper, you will find a much more detailed information there. So thank you for your attention, and I think that it's now time for questions. If there are no questions, okay, we'll just wait a few more seconds. And if there are no questions, then we'll now move to the challenge winners. The first two solutions will be also presented separately with more details about the architecture and the training of these models. Okay, one good question from Fausto is what architectural details should be considered when developing a quantized model? First of all, residual connection and skip connections, because they allow you to propagate your input data and the features from the previous data without actually performing without applying any quantized operations on top of them. So skip connection, it's basically you're just copying the features obtained before to the next level, for instance, to the output of the model. And especially in this particular challenge, you saw that almost all participants use skip connection between the input and the output. Because in this case, the skip connection allowed you to preserve your original image, basically. And you did not get any accuracy degradation caused by applying quantization operators, caused by quantizing the weights. You're just taking the input image, you can upscale it, and you're getting, and then basically the remaining part of the model pretty much tries to learn the difference between this upscaled image and the target image. So it learns to reconstruct the missing texture, the missing components. And in this case, yeah, it's possible to do this with by using just quantized, by using only quantized layers, quantized operators. But yeah, skip connection is something that you need to use almost everywhere and every time when you are trying to develop a quantized friendly architecture. Because if you're not using quantized, if you're not using the skip connection, then the accuracy drop will usually be very significant. Okay, so if there are no more questions, let me check. And there are no more questions, then we are moving to the next talk that will be delivered by Mustafa Ayazoglu from Aselsan Research, and he'll present the winning solution called extremely lightweight quantization robust single image super resolution for mobile devices.
Hi, everyone.
Hi, Mustafa.
To fit into the tight schedule, I saved my presentation as a video, so I'll be sharing that video.
Yes, sure.
Can you see?
Yes, we can see.
Good. Okay, let's listen together. This talk will be about our winning entry, which we call XLSR to Mobile AI 2021 Real-Time Single Image Super Resolution for Mobile Devices Challenge. Before going into the details of the model, let's briefly talk about the problem. Given a low-resolution image, try to obtain its high-resolution counterpart. Note that the problem is ill-posed. This is due to the fact that the high-frequency components of the high-resolution image are lost during the downsampling process, which leads to loss of texture, details, and sharpness. The problem has been studied for decades, first within the traditional computer vision setting and later on with deep learning methods. This timeline shows a few deep learning methods offered for the problem with the number of parameters. As it can be seen, current trend in deep learning methods for single image super resolution problem is increasing the number of parameters and hence increasing the performance. So from a pragmatist point of view, the mainstream methods face with a challenge. Can they run on mobile platforms in real time? The immediate answer is usually no. This is due to the fact that the model size is usually huge, the hardware has limited amount of memory, the latency of the model prohibits its real-time application. Furthermore, the underlying hardware might have some limitations on silicon for mathematical operations. The solution for the challenge is designing new models considering hardware limitations, efficiency, as well as performance. This is indeed what Mobile AI 2021 Single Image Super Resolution Challenge is intended for. The challenge required a single image super resolution model as a TF-Lite file with full 8-bit integer quantization. Furthermore, the underlying hardware has its own limitations. Element-wise operations, reshaping and transposing are not optimized. Per-channel quantization is not supported. Multiple long skip connections slow down the entire model. With all these constraints in mind, we proposed XLSR, our winning model for the challenge. Next, we will go into details of our design choices and elaborate more on the model. At the heart of our model, there is the building block, which we denote as G-block. G-block is inspired from the architectures designed for classification problem for mobile devices such as ResNex, ShuffleNet, and DeepRoots. And we avoided depth-wise convolutions since they perform poorly under 8-bit quantization. Since skip connections and shuffling are not optimized in the given hardware, we combined group convolutions with one-by-one convolutions to form our building block. Here, the idea of using one-by-one convolutions is to allow interchannel information flow. Next, we need to focus on the model quantization and quantization friendliness. Note that unlike classification models, super resolution models are not robust to 8-bit quantization. So why do models work under 8-bit quantization? Many of the existing methods use linear activation at the output and train the model with the hope that at the convergence of the model output would be bounded, which is usually the case due to the training dataset, which enforces this indirectly. However, intermediate activations are unconstrained and can contain outlier values. When quantized, these outliers dominate the activation, zeroing out most of the comparably low values, and hence effective signal energy reaching to the output layer drops. To regulate the activations, we propose a subtle change in the network which will make it more robust to 8-bit quantization and yet fast to execute. We change the model output with clipped ReLU function. This subtle change, when combined with model training, indeed helps creating more balanced intermediate activations and hence a quantization-friendly model. More elaborated discussion on this topic can be found in our paper. Here we can see an experiment comparing our model with and without clipped ReLU function. As you can see, the model with clipped ReLU function is very robust to 8-bit quantization. Other than the building block and quantization issues, since element-wise operations are not optimized, we didn't use any scaling and avoided addition operation. Instead, we use concatenation where needed. For quantization calibration, instead of using the entire training set, we used a subset of it and observed that a suitable subset, the 8-bit quantization performance increases. Indeed, after the challenge deadline, we kept experimenting with this subset and observed that 0.2 to 0.3 dB PSNR increase in our model's performance without changing or retraining the model. To compare the model with the existing methods, we reported unquantized model PSNR on standard datasets. As it can be seen, the model can achieve comparable results with VDSR and even surpasses it in Div2K validation dataset, though having almost 30 times lesser number of parameters. For quantized model, XLSR is the winning entry for the challenge. We further compared our method with quantized versions of FSRCNN and ESPCN. The result of quantization of our model and the other models can also be seen in these images. Note that shifted and dull colors in other models' output, while our model produces sharp and correct output. Thank you. Any questions?
Thanks, Mustafa, for presenting your solution. Okay, yes. Are there any questions to this team, to Mustafa, about some additional architectural properties? Okay, no questions, which means that everything was pretty clear. Okay, thanks a lot for the presentation. And now we are moving to the second solution. So, and it will be presented by Somsai Du. Yeah, I hope I correctly pronounced your president. Okay.
Okay. Can you hear me?
Yes, yes.
Okay. Hey, hello, Android. Hello, Android. Hello. Hey.
Yes, you can present the work we see.
The room app says that I have to exit the app and restart, and I can use the share the screen. So can the next speaker speak first, or just wait me 1 minute?
Okay, yeah, it's fine. We can wait for you.
Sorry for mistake.
No problem. Okay, so I now am going to share the screen. Okay, so yeah, sorry for this delay because Zonsai tries to connect for the third time to the workshop to the current Zone streaming. Hope the third time will be successful. Okay, great. Can you please also unmute yourself because we don't hear you.
Okay, can you hear me? Okay.
Yes. Awesome.
I apologize for my mistake. And since the last previous speaker has introduced a lot about the background, so I will just focus on my the idea behind my design. I'm Du Zongcai from Nanjing University, and I'm going to introduce the method for 8-bit quantized image super resolution. Okay, there are multiple diverse applications using this technology, such as HDTV and underwater detection. Existing deep learning methods have achieved remarkable success, and many works focus on how to make the models lighter and faster. Among them, information multi-destination network and LatticeNet are two most famous architectures. However, there are still two problems remains to be solved. The first one is that they are still too large to deploy on mobile device. The second one is that the 8-bit quantization for mobile super resolution has not been investigated over the past few years. For example, if we directly apply PTQ to the pre-trained models, the PSNR will drop 5 dB. We solve above two problems through two stages. In the first stage, we want to get insights from the efficient super resolution and want to figure out what kinds of operators we can utilize. So we decompose the current state-of-the-art lightweight super resolution networks into meta nodes and get their inference time. To our surprise, all the tricks such as attention mechanism, fusion strategies don't work on the target Synaptics mobile device. So we decided to choose the cheapest operation like 3+3 convolution and ReLU to construct our base architecture. In the second stage, we want to figure out what kinds of network really makes sense to the 8-bit quantization. The straightforward idea is residual learning. This figure shows how it works. The top subfigure is learning without residual, and the output activation of convolutional neural network ranges from 9 to 129. The bottom subfigure shows learning with residual, and we set an anchor value for each pixel. So the output activation of the convolutional neural network ranges from -2 to 2. Apparently, it's much more easier for quantization. As for residual learning, it can be divided into two types. The first type is image space residual learning. It interpolates the image space, the input resolution image to HR space. The latter is the feature space image residual learning, which adds the shadow feature maps to deep feature maps. We found that image space residual learning is much better than feature space residual learning, since it forces the whole network to learn small residuals. However, if we review the table of meta-node latency, we can find that just one single nearness label interpolation operator cannot satisfy the real-time need due to floating point coordinate mapping. We further propose a method that achieves the same functionality by repeating the input and taking advantage of the depth-to-space layer. In this way, the floating point calculation is avoided, and as a result, it's more efficient. Finally, we construct our model. The main branch of our architecture is consequentially stacking convolutional radial layer, and another branch is repeating for global residual learning. The whole network is really simple, and only highly optimized operators are adopted, such as convolutional lawyer and radial lawyer and radial operator. This table shows the results. We can see that our methods outperformed other participants by a large margin and get the highest score. This table shows the operation study, and we can see that with our methods, the 8-bit quantization network achieves nearly the same performance as the original floating point network. And the PSNR drops only 0.13 dB compared with the floating point network. Also, we can see that our method can achieve more realistic details. Okay, that's all. Thanks for watching, and thanks Andrew for accepting our paper and our results after the official deadline. And I sincerely apologize for my mistake. Okay, that's all.
Okay, thanks a lot for your presentation. Well, your work actually demonstrated very good numerical results, and it was actually one of the best ones. And together with the previous work that was presented by Mustafa, this were pretty much two solutions that can be right now used for on-device, for inference, for super resolution on very constrained hardware, and pretty much even in production. So these are very interesting works, very interesting results we obtained, and they will definitely make an impact for the future works on the same domain. So are there any questions to the speaker? Okay, so if there are no more questions, then we're moving to Abdul, who will actually tell you now more about the platform that was used for benchmarking in this challenge about Synaptics Fias 680, smart home SoC, and about different optimization methods. So he'll pretty much introduce you all basics related to smart TV, smart home platforms, and Synaptics hardware. Hi, Abdul. You're welcome.
Hi, thank you,
To
Andre.
start.
I'm sorry, I'm a bit blurry, but this is the best I can do with my light here.
Okay, so we had to solve image to blurring tasks instead of image resolution.
Exactly. Okay. Let me share my screen. Can you see it?
Yeah, yes, we can see it.
Okay. So thank you for presenting the two winners of the official winner, Mustafa, and the other paper. Very interesting architecture and very powerful model. So thank you for that. So today I'm going to present a bit the hardware and software that we Synaptics are doing. I'm going to try to be faster than I initially scheduled, because I see that we are quite late. So let me go straight into the subject. So very fast. Synaptics, we are a company.
Well, just a moment. I think that you still have time, because we'll just shift everything a little bit. So you can just tell everything that you plan to tell from at the very beginning. So you won't be constrained. It's not like in 5 minutes we'll just tell you to stop presenting. To stop a presentation. So yes, you have your 30 minutes. So yes.
Okay. So previously, Synaptics was known as the touch company, with the touchpad. and but for laptops and for touchscreen controllers on smartphones. But since then, we have diversified significantly over the last 5 or 7 years, and we are now a semiconductor company with a very broad portfolio of product lines. So we do wireless, Wi-Fi, display driver, as I just said, capacity sensing, AI, a lot of audio for real voice, speed capture, a lot of also optical imaging, and me specifically, I'm working a lot on AI and on image and video, but also on audio application. So our product will you can meet our product in a lot of different markets, from automotive to multimedia to PC and peripherals to smartphones. So it's very broad. But today specifically, I'm going to focus on our flagship product, the VS680 multimedia system on chip, SoC. So this is the most powerful Synaptics SoC to date. Even though this is a 6th generation multimedia SoC, it is the first one to have a dedicated NPU, neural processing unit. Beside the NPU, the VS680 contains a quad-core CPU, Cortex A73, running at 2 GHz, an Imagination GPU, Series 9 and PowerVR, and an NPU that can achieve up to almost 7 TOPS. So this SoC is designed for products like set-top box or smart displays or even smart camera, because we have dedicated ISP in the SoC, and we can connect external cameras. So this chip has the capability to receive and process video streams, process video in real time using these neural network models, making usage of the NPU, and we are able to send those video out to a display. So this is achieved both through the CPU, GPU, and NPU processing, as well as some dedicated hardware that are optimized for the application. So this slide gives a deeper look at the hardware architecture. So beside the GPU, CPU, and NPU, I'm going to describe it a bit more, we have a video encoder hardware component, audio island, we have peripheral, and we have, more importantly, the DDR access. All those hardware components share the same bus, the XI fabrics. And this is a very important notion, because everything can be integrated in an application using a single pipeline. So video can come from a camera, be processed by a video encoder, apply some AI models on top of it. All the data are shared via, are going through the DDR and have fast access to each of those components. So the NPU is a very silicon IP that we integrated into our SoC. It's very powerful for 8-bit models. So we chose to have high performance with the sacrifice of a bit of the accuracy, in order because we know that a lot of AI models can be quantized to 8-bit efficiently. So the most important factor in the NPU is the convolution cores, the NN core. So we have 22 cores that are able to run convolution and depth-wise convolution. Next to it, we have the tensor processor, which are able to run fully connected layers, transpose, multipling, element-wise operation, and also activation function. If And as you know, most models contains more than convolution and fully connected, so element-wise layers. So we have one parallel processing unit, which is basically similar to a GPU shader, but much less powerful than a full GPU shader. So this PPU is able to run full OVS OpenCL 1.2 operation. We also have support for OpenVX and can support almost all AI layers for at 8-bit, 16-bit, or floating point 32-bit. In order to make use of this SoC, software is very important. And we designed the Synapse toolkit specifically to help the developer port their model to our SoC. So the Synapse toolkit is supporting Android, which is our main OS for set-top box, Linux also for some customers, and it is really an open full stack solution, but it's built on industry standards like TensorFlow or PyTorch. We are able to import a lot of AI model formats, and we can support a wide variety of AI use cases like image recognition, voice, audio, graphics enhancements, etc. So in the slides, I'm going to focus more specifically on the super resolution challenge. So why is it important in the context of set-top box market? For example, super resolution can be applied to do upscaling to 4K. As you know, most video content right now are still 2K, so HD or full HD, 720 or 1080p, or even some of them are simple definition, 480p. But right now, most TV sold are 4K. So AI upscaling really, as we found out, is really able to achieve much better qualitatively upscaling than traditional computer vision methods. So that's why we invested a lot in this technology. We developed our own Synapse super resolution model, but is able to run this upscaling to 4K at 30 frames per second in completely secure mode. And this is something that, so security is very, very important notion. I don't have the time to address this in this talk, but the Synapse toolkit is able to run any model in a secure way without relying on any software stack. So this super resolution model that we have now in production has a really a very nice VMAF score. So VMAF is the Netflix metrics. It's a bit different from the PSNR and SSIM, but we've been using it in the SR challenge. But as you can see, so the matrix is 100 at the maximum. So we have a very nice for 2x VMAF of 93, which is almost as good as the original image. So hopefully you can see the difference between the hardware scaler, especially on the eye and the beak and the fur of the. You can see the difference between the two. In the next two slides, you're going to see that it's even better on some images. Hopefully, through Zoom, you're able to see the difference between the AI upscaling with our SR model with our traditional computer vision scaler. So this table presents the result of the model contribute to the SR challenge. So I took the liberty to include the results for two of our own SR model. So the first one is the production model, but I just show here the results. So this is what is achieved by our own production SR model. So with this model, we are able to achieve a score of 189, which is quite good compared to the rest of the channel. I'm going to explain why. So in terms of PSNR and SSIM, we are almost on par with Assumption Research. So the winner of the contest, Assumption Research, Mustafa. We have a PSNR of a bit less for the first one, and a similar SSIM. But where we outshine the other models is the inference time. So we can run this model in less than 9 milliseconds. We developed a new model, the QDO.ai, which brings the performance in terms of PSNR and SIM almost as good as Assumption Research, Mustafa, but we are still at 15 milliseconds. So we are still in the budget of full real time for this model. So the reason why we developed this new QDO.ai model is because even though so here we're talking about 3x upscaling, so from low resolution to full HD, but our use case is upscaling to 4K. So it can be 3x, it can be 4x or 2x, and if you do, for example, 2x to 4x, we are closer to 25, 26 milliseconds. So while we can still support this in real time on our chipsets for 30 frames per second, we only have a budget of 33 milliseconds. So we decided to have a dedicated hardware engine in the next generation of SoC. That will be the VS6780. So we designed this QDO.ai model completely in hardware. So the next generation chip will have an integrated AI upscaling processor that will be able to process in a completely secure way the input video. This will do inline upscaling, so it will be much more efficient in terms of power and memory compared to the NPU. And it will be able to support 12-bit video as input, as opposed to 8-bit video for the NPU. And even though it will not be a general purpose NPU, it will not have support for all the layers that can be supported by our NPU. We will have some configurability, like the number of convolution, the depth, the type of the convolution, depth-wise or not, etc. So this explains a bit the architecture of the new QDO.ai. So we have a skip connection, but actually makes use of our online scaler, so the hardware scaler. The main branch is an AI model, and the second arm will be the inline scaler. This enables us to process at 60 frames per second, not even 30, 2K image to 4K image. And most importantly, it enables us to do that in a secure way while keeping the bit depth of the input video. So our internal display pipeline is 12 bits. So it is important for us to not degrade this quality. Now I'm going to talk about a bit the software stack that we have developed. So part of this software stack is provided by our silicon, by our IP provider, VeriSilicon. So we distinguish between online conversion and offline conversion. So online is the ability to parse and load an open format like TF-Lite at runtime and just in time compile it to run on the NPU. So we support RMNN through some adapters. We support TensorFlow Lite in two ways, either through the NN API or through a TF Lite VX delegate. So VeriSilicon has created this VX delegate. VX stand for OpenVX on top of a new open source engine that I'm going to talk about, the Team VX open source engine. And we can also support PyTorch on top of the NN API. So on top of, below those framework, we have an OpenVX driver and compiler that will generate a binary graph that is optimized for the VS680 NPU. So Team VX, just a short, small slide to give the link. So this is published on GitHub. It's developed actively by VeriSilicon, and it actually has a much better performance than the NN API delegate for various reasons. The advantage of NN API is that it is you can use the NN API on the platform without having a security issue, because it's designed to be as a HAL, on Android, and any application can make use of it, while the TensorFlow delegate means that you have to access the NPU driver directly, and this is not allowed for any application. So there is a strong difference here. So even though you can achieve better performance, you have to be a vendor to use it really. This slide presents the offline conversion. So offline means that we generate the binary graph ahead of time. So the machine learning application can be in various formats. So we support TensorFlow Lite, TensorFlow directly, or NNX, Caffe, or PyTorch. So we have how Synaptics Toolkit is able to import this model, to optimize it optionally, to quantize it if needed. I mean, if the TF Lite, for example, model was not already quantized, we support post-training quantization. And then we generate OpenVX source code that is then run on top of a simulator that generates an executable binary graph. So this binary graph is completely optimized for the NPU. And we can support encryption and signature of this binary graph so that it will run on secure data. So the ability to run to do this graph conversion ahead of time on the host means that we can add optimization, and we can avoid a data copy, which for some model means that we can save some very precious milliseconds. For example, in the case of MobileNet V2, per comparison, sorry, on our own CPU, so on Cortex A73 CPU, we need 28 milliseconds to run this model with the standard benchmark model tool from TF Lite project. If you use our TF Lite NN API, we are down to 5 milliseconds. Using offline, we can go down to 2 milliseconds. And the difference is even more impressive for some model like PoseNet. So PoseNet, we go down from 8 milliseconds in the case of NN API to 3 milliseconds. So using the Synaptics Toolkit brings a real advantage here, but this has to be done with a specific application. We cannot support this kind of application for generally, because it requires direct access to the driver. One interesting application is the body pose. So we are supporting the Google Blaze pose model for body detection and landmark detection. And this is running very fast using our offline conversion. 5 milliseconds is, so we can do a lot of models inference at the same time on the same video, because we have, for example, we have a budget of 30 milliseconds in the case of 30 frames per second. So you can do place pause in addition to classification, in addition to something else in real time for the video. So all this is supported by the Synapse toolkit. So the Synapse toolkit is it provides basically the ability to optimize a neural network model developed in a standard framework and deploy it to the hardware. So we can easily take any model, for example, in this case, an image enhancement model that is developed in TensorFlow, and then we will be able to optimize it and create something that can run in a video processing pipeline in a secure way. So we have productized already this in our set-top box, and we meet actually the highest content protection security standards required by our service provider. So the service provider, the IPTV service provider, requires a very high security model. So this is very important in our case. Going to go fast on this slide because most of the attendees knows about that. Maybe some words about the tooling. So Synapse toolkit is basically a framework that will import any model, that will optimize it, and then create this EBG, this executable binary graph that is optimized for NPU. We have tooling that is based on Docker and Python that enables cross-platform support, and we can also do HTTP client-server architecture to create accuracy report for a given model. I'm going to go. Well, I can go back to the slides after the meeting, but I think what is important is that the Synapse toolkit for an operator or customer is easy to use and enables the porting of any AI model onto our platform. And that is all for my presentation. I will take any question if you have. So we have a question from, okay, a lot of questions. First from Mustafa, is the NPU a SIMD architecture or a SIMT architecture? It is actually none of that. It's really composed of three, as I said. So let me share again my screen. It is composed of three main components, actually four. So we have dedicated internal SRAM, static RAM, 1 megabyte. We have the NN cores, which are really convolution engines. So it's convolution, programmable convolution. You load the weight and you execute that. And you have the tensor processor that can execute static operation like transpose, element-wise, or activation. All the rest can run on a PPU, which is similar to a GPU shader.
Okay, and I guess we have some other questions to you. Some good questions. So first of all, it's about tracker, and connections, about using models with recurrent connections, do you think there will be well, I mean, it's clear that actually that with recurrent connections, you can get slightly better results. The question is whether you will be able to deploy these models on Synaptics chipset, on Synaptics platform.
We are actually, the QDO AI, we are able to deploy that. Yes.
And you have already tested some solutions.
Sorry, Andrea.
Have you already tested some solutions? Do you have already some?
Yeah, actually, the QDO AI model has a SQ connection. It is actually working on the VS680 in real time.
Okay, there are some other questions. For instance, can you share your model design paper patent for super resolution? If not, could you share some suggestions which are missing from challenge methods?
Okay,
I think, yeah, okay.
We have a patent on this model architecture. So, but one thing that I can share is that our model is based on the Luma channel, the wild channel. We have found that the wild channel is the one that is most important in the case of AI upscaling super resolution. So you don't, I mean, our video pipeline is based on YUV format, right? We don't, the standard video processing is based on YUV, not RGB. And we found out that focusing our AI model on only the Luma channel, the wild channel, is more than enough for the desired accuracy. So we optimized our model to use, I mean, our convolution engine. We have multiple solutions in the NPU. We can run 3x3 kernel, 5x5, 7x7. So we chose what fits, what has the most powerful, the least inference time for each of the component of our models. Yeah.
Okay, thanks for the answer. And another question is about whether you're using 12-bit convolutions when performing 12-bit AI scaling.
So we will in the next generation chip. So we cannot do that for the current NPU because we can only support either 8-bit or 16-bit convolutions. But in the next generation, we will support natively in hardware 12-bit, yes.
By we, you mean VeriSilicon?
Excuse me?
By we, you mean VeriSilicon, right?
By the NPU? Sorry?
No, by we, you said that we will support, you mean
no, it will be a real Synaptics development. So we are not going to use the NPU. Yeah, the new super resolution engine will be completely owned by Synaptics. We will still use an NPU, so the NPU is going to stay, maybe a bit less powerful because we don't need that. But we decided to implement this the image upscaling and other stuff completely directly in hardware.
Okay, and so then for which task will be an NPU used?
For everything else. So it can be object detection.
Maybe you can, yeah, okay, yeah.
So yeah, the NPU right now it's used for super resolution, but it is also used for object detection, face ID, speech processing. There is a lot of application that our customers are interested in. So by freeing the NPU time from the AI upscaling task, we are able to support a lot of different applications in parallel. That's the idea.
Oh, that's great. Okay, and another question, does the inference time take into account the DRAM access latency?
Yes, that's the effective inference time. Yeah.
Okay, and good. So let me check if there are some other questions. Okay. no more questions. And yeah, anyway, in the presentation, there was lots of material. So thanks a lot, Abdel, for presenting.
Thank you. Yeah. Thank you. Bye-bye.
The details about the platform. And right now we have, I guess, a 5-minute break. Okay. Okay, let it make a 15-minute break till, till 40 minutes. Let's just have a 15-minute break, and we'll get back. The next presentation from Huawei will start at in 15 minutes at 12:40 instead of 12:30. And now you have 15 minutes to relax. Okay, see you all in 15 minutes. So it's 12:40, which means that it's time to continue the workshop. And right now we'll have a presentation from Emilia Tantar telling about Huawei's solution related to deep learning on mobile devices and also on non-mobile devices. And the title of the talk is AI Development from Hardware to Software, Challenges and Opportunities.
Thank you, Andre, for the kind introduction.
Yeah.
Happy to see you here. I will just start sharing my screen. We'll see if everything goes well. Second. And so today's talk is about the AI deployment. We all know that hardware without software, it will involve a lot of challenges. And besides the challenges and opportunities of deploying from hardware to software, we'll also highlight some of the challenges and opportunities we witness and we see for the future. The talk will be structured in several sections. First of all, an overview of the consumer products by Huawei, the Huawei NPU in the mobile SoCs, a short view on Huawei High AI Foundation platform and device, an example of an AI application, including mobile office, and then challenges and opportunities. It will be concluded with a summary of the talk and some key takeaways. So an overview first, what is Huawei's strategy? Huawei's strategy evolves around 1 + 8 + N. 1 being the smartphone that you see here in the center, 8 being devices like speakers, AR, VR, lenses, watch, earphone, vehicle terminal, PC, pad, or TV with HD. And then when we go to N, it's all the other seamless scenarios that appear in the user's life. And the strategy is around all scenarios seamless with an AI life. Here, and also in today's talk, we'll focus on 5 scenarios. This is the core of the Huawei's strategy around the connected objects. The first scenario is the mobile office, and I will have a small example for mobile office, which can be handy for today's long day of talks and summarizing. The second one is smart home, so connected objects which are in a home. Then Huawei tackles smart traffic, sports and health-related applications, and entertainment. So these are in a glance what are the strategic directions and the focus on 5 scenarios. This aims to provide better user experience for consumers based on solutions with which they are familiar. So going a bit how the 1 + 8 + N product is shaped. It's shaped around having as differentiator AI solutions. Among the 1 + 8 + N devices, they are not all having the same requirements. For example, if we take the requirements for an AI solution for a mobile phone, for pads, they require high peak performance. And if we take the watches and headsets, they require low performance, but always battery drainage is an issue, and we need high energy efficiency. PCs, on the other side, they require slightly lower energy efficiency because we have solutions for that. They can be plugged. The watch, on the other hand, it also requires more vector computing. Therefore, for the tensor vector ratio, for the watch, this is lower than that of the mobile. The operator specification requirements, they are lower, and the required inference framework is lighter because of the functionalities which we can embed in watches. Generally, different devices, they differ in terms of memory, tensor vector ratio, energy efficiency, and also in terms of inference framework. and of course, operator specifications. What Huawei proposes is a Huawei DaVinci NPU. It's not from this year, it has quite some years, and the Huawei High AI Foundation. They provide different AI computing solutions to meet these differences. We'll speak later about the inference API, the IR API, and the fact that we can dynamically have heterogeneous scheduling of the resources, basing the computation on NPUs and XPU, being CPU, GPU, and so forth. So the base layers, the Huawei DaVinci NPU hardware, then we have the High AI Foundation, which has all these components that I named, and the interface with the devices is realized through a Huawei High AI DDK, it's called. If we go on a specific mobile SOX application, so Huawei NPU, there are some key specifications, and there was quite a steady evolution. As Andre mentioned it in the introductory talk, Kirin 970 was present as the world's first mobile AI NPU at that time. And then Huawei invested intensively in on-device AI development. In 2018, so that's 1 year later, with the world's first dual-core mobile AI NPU. And then in 2019, the Kirin 990, the Huawei DaVinci ARC version 1. What I could tell more about the evolution is related also with DaVinci, so it went through different versions. Now in 2020, we have the Kirin 9000, which is based on Huawei DaVinci Arc 2.0, so this is the version number. This 990 and 990 5G, they used the self-developed DaVinci NPU, and that improved performance and energy efficiency. So when we start having this hardware plus software, that's supported with energy efficiency. And there is also the microcore, Huawei DaVinci Microcore 1.0. This is to support environmental awareness with ultra-low power consumption. So the architecture has better performance. And just to give you a rough idea how this is shaped, I have here a small picture of the Huawei DaVinci architecture NPU. You could see that this is a simple diagram. It has an efficient 3D computing unit. What you see here is the cube. And then you have, in addition, vector unit and scalar computing units. They were added to meet different operator computing requirements. The computing units, they are connected to each other through RAM to meet high bandwidth computing requirements. And as we have also some tests which were performed in the attached table. Here we have the Huawei High AI DDK version 500, which provide excellent performance in energy consumption also. So this is a Kirin 9000 with the High AI DDK V500. And you see here the model name, ResNet 50, MobileNet 1, DLAP V3 official. They were tested first on floating point 16 bits and then on integers 8. That's, I think here we have DLAP V3 official, which was not yet tested. It's not yet tested. It's not because we know of any results. We didn't have the time to prepare it for today's talk, having also on int 8. So you can see the DL framework which was used. We used Caffe, TensorFlow. Then we used on DeepLab again TensorFlow when we passed on integer in int 8. we used again Caffe and TensorFlow in the same order as they were for the floating point. You can see how the performance goes, and frame per second, and here you have the power consumption. This is again, this is a simplified view. What is to be noted is the RAM, which is for the communication, and the cube, which is used for tensors. So that's quite interesting when we do complex calculations, especially for images. Then if we go for the Huawei DaVinci NPU architecture core, it enables all-day low-power operations. So you can use it on any type of operation, and it enables to scale to more products. The main advantage and the main characteristic that I wanted to highlight here, it was the fact that it is a scalable architecture. You can see here that it's miniaturized microkernel architecture. It requires very low computing power consumption, and it enables AI computing capabilities on more power constrained devices. Here we have the microkernel, microcore 2.0 on the Kirin 9000, and we see that it uses only 1/10 of the industry average power consumption. So this is the power consumption. What you see, the average, is based on the average power consumption of the actual application. If we consider different environments, of course, they will lead to different results. Not substantially different, but will not have exactly the same values. This equation based, and it is based on the specific application which is tested. This is for illustrative purposes. So the low power consumption hardly affects the service duration for the phone, and it provides more intelligent environment awareness capabilities. So here we can see that we can scale it, and we can use it for low power operations, and that provides good performances. If we are to go a little bit more on the Huawei High AI Foundation, the foundation adapted. So at the beginning, the Huawei High AI Foundation, the version 1.0, started with TensorFlow, with Caffe. Later, it was adapted in version 2 to include also CoreML, Caffe 2, MindSpore, this is on Huawei technology, Paddle, and Onyx. As a computing software stack, which was designed based and extended on Huawei NPU, the Huawei High AI Foundation, it supports models of mainstream open source frameworks. So we start Caffe, TensorFlow, PyTorch, and they can run efficiently on Huawei NPUs. There are more third-party frameworks. Currently, the Huawei High AI Foundation is already at version 5. So there are several other which have been added. The fact that it can also connect to third-party frameworks, this is for inference. It can be done through the IR API, which is hardware independent. And then we have the application algorithm developer. So if you are an application algorithm developer, you could use the offline model generation tool. So you generate the model offline, and then you can use it, and you can make the inference, which is here abbreviated OMG. And this is provided by Huawei High AI DDK. It generates model formats, so formats that can be identified by hardware. This is for inference. And this allows to achieve best performance and energy efficiency gains. Application algorithm developers, like yourself potentially, can also invoke third-party frameworks. So this allows the third-party framework to invoke, as previously mentioned. You see here the connection, the IR APIs, which are provided by the foundation, and you can construct different models and run them on Huawei NPUs. You have here an offline model file generation, so you can have it in a file, you can export it. There is hardware-related graph optimization. I will speak about it a little bit later. One example of usage is, for example, Alipay and Taobao application. They use many AI models in their services, but they perform the inference invoking Alibaba's MNN. So that's the Alibaba MNN framework. This has completed IR connection here with Huawei HiAI Foundation. Therefore, if you would like to have your AI models in services, they can fully utilize the computing capability of hardware on Huawei phones, for example, things which is not usually easy for service developers. So you can see here it's transparent to algorithm developers. They have this call to IR API. I would think here all the main information is resumed. I would go a little bit more on what is provided to developers. So the Huawei HiAI Foundation computing software stack supports various operator specification because there are various typical computing requirements. Here you can see that in total it's more than 300 operators. There are some examples. For example, for neural networks as operator category, you have more than 60 plus convolution pool, format. Of course, there are quite a few, the classic ones, sinus, cosinus. So it's more than 50 plus which are supported. Array, essential for doing tensor and vector, especially on the vector side operations. There are 50 plus, concatenate, reverse, batch to space. For image, there are 5. This will grow, of course. There is crop and resize, resize bilinear. And in terms of control, you have 30 plus. So the logic operator, logic and, logic or, logic not. And these are some examples. In total, there are 300 more operators. I would think that in terms of operators, you could see the evolution between the versions. Now we are already at version 5.0. So that means we already overpassed the 300 by far. But you can take as order of magnitude 300. This is the last table. So you can take that as a number. In terms of computing stack, one important part is that it supports flexible heterogeneous computing, and it performs automatically heterogeneous segmentation and segmentation based on the capabilities of each computing units, and it computes each segment on different computing units, of course. So this is deployed afterwards. Here you have in the figure a typical network. So this is a random configuration, graph configuration of the network. And you can consider the red and blue branches. They can be a processing that requires, like in the red, a large amount of scalar computing, or blue, a user-defined operator. So what it happens, the heterogeneous processing engine will do a scheduling of these tasks. So it will match the platform capabilities and operator specification, and it can allocate the red nodes, for example, to CPU. Some of the heterogeneous in blue will go on the GPU. So this will be allocating according to the specific task and specific segment capabilities also. So this is completely automated and does not require caller attention. Of course, if you'd like to further fine-tune it, you are more than free to do so and encouraged. But this is automatically done, and there are automatic scheduling algorithms which adapt dynamically. Even when they are allocated to CPUs and GPUs, this computing is always optimized. So the performance is optimized by the Huawei High AI Foundation. This is for illustration purposes. Some example, so these are run by Huawei colleagues. On Kirin 980, which supports the dual NPUs, there was an extension of the capabilities, and it was noticed that image recognition efficiency was improved by 3 times and 4,500 images per minute with a ResNet 50. So these are some punctual examples. Here you have the network AlexNet, VGG16, ResNet 34, and you can see on CPU and how it performs using the High Foundation NPU CPU in terms of performance and energy efficiency. So we can see an improvement. 25 times was the performance acceleration on this specific example, punctual examples. And we observed also energy efficiency improvement. There is capability of multi-platform compatible quantization. So when you do discretization, there was an important improvement there, but this is more on the way quantization works. So I'll not stay too long on this one. In terms of application, there is one which I found it might be interesting because we are all after a long day of talks. So here what we have is one way to create a PowerPoint presentation where we can annotate. So if you take screenshots, supposing we are not in a virtual environment, but we are really in a room, there is an intelligent identification. So I'll try to run the example. You can select some of the images you made pictures of, and it does a correction of the angle, and then it generates a PowerPoint with super text resolution. So you can annotate where you had some questions, so you'd like to add for your reference more comments. So this is not to encourage you to reuse this. This is for no purpose intended for that. You should use it for your own notes in order to add parts which are valuable to you. So it does document correction, super text resolution, so that you can understand better the text. As you would imagine, it has an engine document correction, super text resolution to improve the quality, and of course OCR to identify text. There is the case, it's available. So if you'd like to look more and play with the different cases, feel free to do so. There is a developer, Huawei.com, and you can follow. Cautious of the time, I think we still have only some minutes left. I would like to highlight some information about high AI, some challenges we see. Compared to some years ago, the image processing needs to extend from image, what we used more on the mobile phones, to video. Everybody's expecting that video is processed. And currently, typically algorithm on the mobile devices, they replaced many traditional processings. For example, photographing scene classification, portrait segmentation, or partial image enhancement. They have been deeply embedded into the current mobile phones photographing process. Everybody's expecting that, so the customer expects that. And they sometimes need to run serially, sometimes in parallel, and are increasingly complex to use. In particular, the current application of AI in image processing has been rapidly extending from a single image to a video, as noted before. And high frame rate video processing, it requires, nevertheless, an order of magnitude higher performance. Therefore, for example, in this application scenario, software and hardware, they need to be flexible and they need to be efficient together. It can't be done by only one of the components. To meet these complex processing requirements, what we have observed from the customers, we need to have hand-in-hand hardware and software working together. Here there are some of the examples. I will not stay too long on those. You all realize this is a real challenge we are facing. And another one is the increasing computing requirements for mobile in terms of consumption also. So from the perspective of different product forms and application, AI software and hardware computing require joint optimization. We already mentioned that optimized hardware architecture, but also optimized framework. More pixel level processing requires the computing platform to support higher peak performance computing power. Then power sensitive IoT scenarios. There we really need extremely high energy efficiency for watches, for all wearables. IoT requires that, because that was one of the drawbacks in the past. And we need to work with the optimized framework. Application developers, they need support to transfer more operators and more flexible invocation. So data transfer efficiency, new network or structure to support. There are also new emerging models and algorithm structure. They require fast support. And the data input for the multi-dimensional models, and there are large feature maps in computing processes, they all require an efficient and optimized data transfer within the system. So that's on both sides, but more on the hardware side can be done in the chip. Only the collaborative approach could bring both performance and energy efficiency. Also, it is considered that open the computing capability of the platform to developers. This needs to be done more easily because developers, they need to have a seamless interaction with the environment. There are opportunities. There are, I will just mention two of them. One, with the strict power consumption requirements. Once we arrive to meet that, and we're all working on that, a new intelligent experience storm will emerge in IoT. This is for the user, so the user will have a different perception. If we take the example of interacting with vacuum cleaner or any other home device vocally, if we are demanding energy consumption requirements, you say to the vacuum cleaner, open mango, open the door, you say to the vacuum cleaner, sorry, just clean this stain. The fact that you have this and you have the favorite music, we are so used with that. We consider this is something given, but the energy consumption, it still remains in the back as one of the major problems that we are working currently. And if we take on the ability to understand, this requires microampere level standby power consumption and the high identification rate for the neural network algorithms. Again, that requires also natural language processing. In Europe, that's especially a challenge because you have Europe, which is facing so many different languages, and the system needs to adapt. And it needs to adapt to the various environment, and it needs to adapt to noise reduction, which in different languages signifies different types of noise. And then we have a basic inside NLP natural language processing capabilities, echo suppression, milliampere level standby power consumption improves the recognition rate to recognize this is really the person which should or has the right to open the door. And then having also NLP going hand in hand, that will make a true seamless experience and an experience storm for the user. Other opportunities are the interconnection between devices. This communication without boundaries, automatic device switching, intelligent experience, color adjustment, skin beauty. There are many capabilities, and you all are aware of that, so I will not stay that long. We know that AI has become a basic capability. It's like electricity. For consumer electronics, it's in the background and is continuously changing the user experience. Higher peak computing power and higher energy efficiency, they depend on collaborative optimization of software and hardware. And advances in device interconnection and software that will bring breakthrough, seamless experience, especially on IoT devices. The platform Huawei AI Foundation proposes will continue providing leading solutions such as NPU hardware architecture, heterogeneous computing, adaptive scheduling, quantitative search tools, and better experience to the customer, consumer business customers. There is a need of more advanced and more inclusive CPU benchmarking, and we are more than happy to salute the effort done by the benchmark so needed on the market. And this unified evaluation system, if we could see them extended to server energy efficiency, because work from the cloud to the mobile, that will be also an important advancement we see. And I would like to thank you, and I do hope I didn't pass too much on the 30 minutes.
No, it's actually good. It's almost on time. And thanks a lot. The presentation was really interesting, especially an example about Office. This is what I in particular liked about taking photos and then these photos being automatically rescaled and created. And yeah, the presentation, the slides that are made out of these photos. Okay, right now we have time for questions. Are there any questions to the speaker?
I do hope we will not take advantage of the time of the next speaker. I see that we used all the 30 minutes.
Well, it's not a problem. Okay.
So the application which was provided, maybe in case you are using, please pay attention to the copyright. So you can use it for your own purpose to take notes, but it's intended only for that.
Well, and this application, it's not available publicly.
Yes, it is available for developers. So you can play with it.
Okay. Interesting. Well, you should make it available for general audience.
Might be. I will have to look. I thought it's a nice example because we had a long day.
Yes. Well, it's really useful, and I mean, it really encompasses lots of different processing tasks, lots of different actually machine learning models that are used for doing all these operations. Well, maybe you are using also some classical tasks, but they can be easily replaced by machine learning tools. And yes, this is actually a very, very nice example. Okay, so if we do not have any further questions, then we move forward. And right now we have the presentation of the learned smartphone of the video super resolution on mobile GPS challenge. So this is the next challenge that we had in the May workshop. And in this challenge, you already know what is the task here. The task is to upscale video. And I already told you about image super resolution in the previous talk, about the use cases where we need it, with about image super resolution and use cases when we need it. And right now, I will talk about video super resolution, and here we have pretty much the same use cases. We also want to enhance low quality video coming from different streaming services like YouTube, Vimeo, and so on. We want to improve the quality of telecommunication services. For instance, right now, if we look at the quality of Zoom streaming, well, it's not that good. We can see that there are lots of corruptions, lots of details are missing, and of course, we want to make this video faster, and especially if we can maintain the same bandwidth, if we are not increasing the bandwidth and just using the same one, and after getting image, after getting video stream, we are just upscaling it to high resolution to add the missing details. And the video super resolution is now also used in smartphone cameras, smartphone video cameras, for improving the quality of recorded data. And this was the task of this challenge, to perform accurate 4x image video super resolution. And another goal was to achieve a real-time performance on mobile GPUs. In this competition, we used RED's dataset that contained several video sequences. The resolution of the target sequences was HD resolution, 1280 times 720 pixels, and the frame rate of this video was 24 frames per second. How the solutions were evaluated? Numerical evaluation was performed based on PSNR scores. So we pretty much measured the PSNR values, PSNR metric between the reconstructed video frames and target ones, SSA metric, again as a proxy for perceptual score. And the evaluation was happening on the OPPO Find X2 smartphone that had Adreno 650 GPU from Qualcomm. And the models were upsampling video from 320 times 180 pixels to HD resolution. Okay, just a second. Okay, no problem. I muted you. And for performing local runtime evaluation, the participants used the AI benchmark application, and for checking the runtime on the target hardware, the participants had to upload their models to Codelab, and then it was tested by our team. And then the participants were provided with the corresponding runtime. Here you can see the results obtained in this challenge, and I should tell from the very beginning that this challenge was quite complicated, because video super resolution is more complex than image super resolution in general. Because here you need to deal with video sequences, you need to deal with video data, and the second problem is that the resulting models had to perform upscaling of not a single frame upscaling, but upscaling of several subsequent frames. So like this happens in real videos. And more importantly, all solutions had to demonstrate real-time results on this GPU, because we are solving a real-world problem and want to get the results that can be usable. And 4 teams entered the final, were able to submit valid solutions, and in all cases, the solution proposed by all teams achieved real-time performance on this GPU. And in particular, they were all able to process video data under 200 milliseconds. 10 frames. This is for processing 10 frames, which means that you need less than 20 milliseconds per frame. And the last solution, it was actually, we'll show you the architecture. It was very efficient, but unfortunately, it was not supported by NPU due to additional staking layer that right now GPU delegate cannot handle it. And what solutions did we get? And I should also mention that all submitted models significantly outperformed the default bicubic upscaling baseline. So from PSNR of 26.50, we increased the results to PSNR of around 28. So it's like 1.5 dB increase, despite the fact that all models were performing video upscaling in real time. And now let's talk about the solution. The winning team that achieved the best numerical and visual results was using a bidirectional recurrent neural model with feature instruction blocks. What is the idea of using using recurrent connection? The idea is that when upscaling the current frame, we're also using features from the previous frame and from the next frame, and features that are also used to upscale the corresponding frames. And in this case, we can also reuse information, not only information about the current video frame, but also temporal information. And usually this kind of data can help the model to achieve better visual and numerical results. And this is what was used by the solution. And besides this, the authors also used the standard feature extraction blocks as you saw this in some previous presentations on image super resolution, they are widely used in different models. And the model was trained to minimize all those functions. The second solution was presented by Team ZTAV and VIP, and it will also be presented after the current talk. The authors used based their model on several residual blocks. Each block consisted of 2 convolutional layers, and the parameters of each block were optimized with neural architecture search, so that the model shows both good runtime and good fidelity results. And the model was trained with L1 loss. And a more detailed description of this solution will follow after the current presentation. The third team, Rainbow, also based their solution on residual blocks, and as a matter of on several blocks, and actually as baseline blocks, this team used information multi-distillation blocks, MDBs. This is also a quite standard approach for many super resolution tasks. And this team and the model was trained with L1 loss function. And as the final solution from team North Terminal Vision was using, again, a very small, a very tiny model consisting of 3 residual blocks and depth space layer on top of it. And the model was trained with L1 loss. And what should be mentioned about this model is that despite the fact that it was very small, very tiny, it demonstrated quite good results. So it was not considered, it was like, numerical and visual results were almost indistinguishable from the other solutions. They were slightly better than the ones presented by challenge winner, who used residual connections, but at the end, the quality of the results were not drastically different. And therefore, even with this small model, it's possible to achieve very good upscaling results. And more detailed information about the solutions and about the task can be found in the challenge paper. So thank you for your attention. If you have any questions, you can send me in the chat. And okay, so if there are no questions, then we're moving to the next talk, to the presentation of the second solution from ZTE Corporation. The paper is called EVSRNet, Efficient Video Super Resolution with Neural Architecture Search, and it will be presented by Shaoli Liu. Okay, good. We can see your presentation. You can now start delivering the presentation. Unfortunately, we cannot hear you.
Can you hear me?
Yes, you. Okay, yeah, good. I can now hear you.
Okay. Hello, everyone. I'm Liu Shaoli from ZTE Corporation. Today, I'm going to talk about EVSRNet, Efficient Video Super Resolution with Neural Architecture Search. This work is done by myself and my colleague. It's really my pleasure to introduce our work to you. As for video super resolution, the goal is to restore high resolution frames from their low resolution counterparts, as shown in the picture. As for our MAI real-time VSR challenge, the goal is to develop an end-to-end deep learning-based VSR solutions that can achieve a real-time performance on mobile GPUs. All solutions are evaluated using the following metrics: PSNR, SSIM, and the runtime on the target OPPO Find X2 smartphone. So we should focus on both quality and efficiency. Next, I will introduce our method in detail. It contains 5 steps. By considering lessons from previous work, we think RN is a good VSR model, but it's time-consuming. So we defined to simplify it by NAS. We first read RN carefully. Like most existing VSR model, it contains 3 sub-procedures: feature extraction, nonlinear mapping, and restoration. Because most deep learning methods focus on the first 2 steps. So we decided to design our search space on the first 2 steps and fix the last step. By experiment, we decided to use FGNAS to do search. This is a factor and search space. For more detail, please refer to our paper. After NAS, we obtained 4 models by changing the hyperparameter of FGNAS. In order to find the best model, we trained it and tested it on the reservoir set. Because model 1 gets better score, so we decided to use it as our change model. In the last step, we remove the reset operation because data switching between CPU and GPU significantly affects the efficiency of network for inference. It has minimal impact on PSNR, but it can greatly improve the efficiency. Showing the picture is our pipeline or our method. We also show some qualitative results. In detail, as you can see from the picture, our method can reconstruct a structured image very well. Another result. The table shows the result of MAI VSR challenge. As you can see in the table, our method is fast and outperform other methods by large margins. This is the conclusion. We propose a real-time video super resolution network VSRNet. Our method is fast and can be easily deployed on mobile devices. In the future, we will further study the characteristics of video super resolution and add some high efficiency units to achieve a better balance between quality and efficiency. That's all. Thank you.
Thanks a lot for the presentation, and we have one question for you. Is the middle block a recurrent module?
No, we are a single image method.
Okay, yeah, this is basically answers the question. And yeah, okay, good. If there are no other questions, then thanks a lot for the presentation. And we are moving to our next speaker, to Jay Tsai, and he is a research scientist at OPPO, and he will present video super resolution models that are used on OPPO devices, and will also tell you about how to accelerate them on OPPO phones with which frameworks and how to do the optimizations. Welcome, Tsai.
Hello, Andrew. Can you hear me?
Yes.
Okay, great. Okay, I'm going to share my screen. Okay. Can you see the screen now?
Yes, we can see.
Okay, thank you. Thanks, Andrew, for the introduction. Hello, everyone. My name is Jie Tsai, and I'm from the OPPO US Research Center. And my topic today is learning to see the world clearer. And in this presentation, I will introduce the video super resolution and our OPPO VSR solution and our OPPO AI platform. Okay, and OPPO is a Chinese consumer electronics and mobile communication company and headquartered in Guangdong province. And our products include smartphones and smart devices and audio devices and other electronic products. And OPPO has entered more than 14 countries and regions market in the world. And our smartphone ranked number 4 in Q1 this year in global smartphone share market. And we have more than 300 million users in the world. And in 2018, OPPO established 6 research institutes in different cities. And we mainly conduct research in different areas, include AI, AR, standards, AI, software, hardware, and 5Gs. Okay, next, let's go into the super resolution. The super resolution aims at recovering a high resolution image or videos from the corresponding low resolution counterparts. And the video is one of the most common multimedia in our daily life. And thus, super of low resolutions has become very important. And meanwhile, with the popularity of high definition and ultra high definition display devices, super resolution is also attracting more attention. And there are 2 major challenges for real-world VSR on mobile device. First is, unlike the most academic super resolution dataset only includes bicubic and Gaussian blur degrees. Thus, it's widely known that super resolution method won't perform well if the degradation model from real-world things, which includes a variety of degradations. And the second challenge is AI models are computationally intensive to be deployed on mobile device. And here are some examples of the degradations. The first is the blur, like Gaussian blur, motion blur, and box blur. And the second one is noisy with, for example, the Gaussian noisy and salt and pepper noisy, and camera, also the camera sensor noisy. And the third one is the blocking artifact caused by lossy compression. And the last one is the different level of JPEG compression. So how to solve the real world degradations? As we all know, deep learning is the data-driven problem, and data is the food for AI. So we use the different combinations of data augmentation. First is the different level of Gaussian noisy, and the second is a different level of Gaussian blur, including the anisotropic and isotropic and anisotropic versions. And the third one is the different level of JPEG compressions. And the first one is the different downsampling method, nearest bilinear and bicubic. And we also use the real-world LR and HR pairs, which include the real-world downsampling. And last is the random shuffle with the above 4 method, which means we use a different order of the data augmentation method. And the second challenge is the AI models are computationally intensive to be deployed on smartphones. And this ESR is a benchmark method for the image super resolution. And the name is Enhanced Super Resolution Generative Adversarial Networks. And for ESR-GAN, first it introduces the residual in residual dense blocks without batch normalization as a basic network block unit. And second, they borrow the idea from realistic GAN to let the discriminator predict relative realness instead of the absolute values. And most of the methods followed by ESR-GAN achieved state-of-the-art performance. And basic VSR is a generic and efficient baseline for video super resolution with minimal redesigns of existing blocks, including the optical flow and the residual blocks, and it outperforms existing state-of-the-art performance with high efficiency. And another important technique for video super resolution is the alignment. The spatial alignment plays an important role for VSR because it's a response to align highly related but misaligned images or features for subsequent aggregations. Early work performed alignment by computing the optical flow and warping the images before restoration. And the second is the deformable convolution. For example, it uses the EDVR to align the different frames at the different feature levels. But however, as far as I know, the image warping and the deformable convolution are still not supported for mobile device. And here are more examples of about the state-of-the-art super resolution method for image and video, but they all have the millions of parameters, and they all have about 600 to 6,000 flops, and also they all takes about several seconds to inference on the on GPU. So it's impossible to directly deploy those methods on mobile device. And for our OPPO SR, our model only have 100K parameters and 20G flops, and it takes about 4 milliseconds to inference on NPU. Okay, and another challenge for mobile is the AI operator constraints. And in our OPPO SR, we only use the 6 operations. For example, the convolution, and second is the deconvolution to upsample the super resolution, and space to depth and depth to space operation to downsample and upsample. And then is the activation. It's just a simple reload function. And the last is concatenation, which used to fill the feature maps from different levels. And in addition to model structures, loss function is also crucial for VSR. Here are 5 loss functions we use to train our models. First is L1 and L2 loss, which measures the pixel-wise differences between 2 images. And they also called mean absolute error and mean squared error. And I will talk about the remaining 3 loss functions later. And PSNR is also an evaluation matrix, and it also can be used to do a loss function. And the PSNR is only related to the pixel-wise MSE, and it caring about the difference between the corresponding pixels instead of the human visual perception. So it often leads to the poor performance in representing the reconstruction qualities in real things. And PSNR is usually use L1 and L2 loss to minimize. So it often suffer from the blurry result, as it doesn't consider creating high frequency details. And SSIM is also evaluation matrix, and it also can be a loss function. And the SSIM loss measuring the structural similarities between images based on independent comparisons between in terms of the luminance, contrast, and the structures. And the SSIM evaluates the reconstruction qualities from the perspective of human visual systems. And multi-scale SSIM supplies more flexibility than single-level SSIM in incorporating the variance of viewing conditions. And the last is the perceptual loss, which measures the difference between images using a pre-trained image classification network, for example, VGG16 or VGG19. And the perceptual loss could restore the high frequency content for perceptually satisfaction. And next, I will talk about our OPPO AI platform, which includes the OPPO AI unit and the OPPO AI boost. And first is the OPPO AI unit, which provide an AI algorithm API for application developers that can help them design simple and efficient AI applications to run on mobile device. And the second is the AI Boost, which designed for the AI researchers, so they can quickly deploy the models to the OPPO edge devices. And this is the structure of our AI units. And our OPPO AI unit provide different AI SDKs. For example, the computer vision, video, audio, and AON for application engineering. And AI units has already support lots of algorithms. For example, OCR, face detection, object classification, image video restoration, and pose gesture estimation. And this is the structure for AI Boost. AI Boost is built between the AI unit and mobile chips, and it provides SDK or API for applying the AI researchers to easy benchmark, deploy, and accelerate their AI models on different edge devices. And this is the overall structure about our framework. First is when the video stream coming, and we extract the video to different frames. And our solution is our first version VSR is a single frame solution, and for each frame it's decoding to YUV format, not RGB format, and the Y format is going to the super resolution model, and the model is running on Qualcomm or MediaTek chips, and then the output of the Y channel is filled with U and V channels, and then displayed on the screens. And our VSR is a maximum support 700p input videos, and here's the running times, and as the 700p as the example, the pre-processing takes about 3 milliseconds, and the model takes about 8 milliseconds, and the post-processing takes about 7 milliseconds. And the overall is about 20 milliseconds per frame. And the power consumption is about 90 mA. And OPPO VSR is first launched on OPPO Find X3 in March this year, which is called O1 Ultra Vision Engine. And our VSR support to super solve any video which is less than 720p to double its super resolution, which means super solve any video with factor 2. And this is how to turn on the VSR features. First, you go to the settings, and then you click the display and the brightness, and then you scroll down and go here. You can see the O1 Ultra Vision Engine, and turn the video image sharpener on. And here is a 1-minute demo to show our result. And the left part is the input video, is a low resolution input, and sorry, the right part is the LR input, and the left side is the HR output. And you can see the video is sharp, and the character is more clear. And this is another example. And at the bottom is the running time is about 10 milliseconds for this video. And here you can see the face, and here is more clear, and you can see also the detail is also enhanced. Okay, and our OPPO VSR is supporting the following apps, which including the TikTok and different the video apps, and also our own apps like the photos, browser, and the videos. Yeah, thank you so much. Yeah, it's all of my topic today.
Thanks a lot for the presentation and the videos. Yeah, sometimes it's easier just to show the video than talking quite a lot about the efficiency of your model and its perceptual quality, because in this case the video just clearly demonstrated that the performance of your solution is just amazing. Are there any questions to the speaker from the audience? By the way, on which device this demo was running?
The demo is from FineX3, but yeah, but it has a similar performance on Open FineX2. Yeah.
Okay, so it's Qualcomm based chipset.
Yeah.
And it was accelerated on GPU or?
Oh, it's on NPU.
Okay, on DSP.
Yeah, right.
So you had, okay.
It's also 8-bit model, not a floating model.
Yeah, got it. Did you meet some issues while quantizing it?
Yeah. We use QAT quantization.
Yeah. Did you meet some issues? Or did you use some tricks to maintain the high quality of the quantized model?
Yeah, maybe. Actually, we use the TF1 for the QAT. But we have some problems. But finally, we found the most problem is we are not familiar with the TensorFlow API. Yeah. So for QAT, we just finally we just direct the default setting of the TensorFlow, and found maybe no issues for that. Also now we are for the VSR version 2, we are trying to convert our framework from TF1 to TF2. So the problem is also the maybe similar to the quantized image superposition challenge, and the problem is if you are using the TF operations instead of the carousel operations, you need to warp the TF operations to use the lambda function to warp the TF operations, and then you can use the Keros QAT.
Well, but with TensorFlow V2, you can still use compat V1 layers, and you will basically get pretty much the same functionality as with TF1. And with Keras, it's also possible just to apply it to tensors, so that you're getting pretty much the same code as with TF1.
Yeah, right.
So, any questions? And quantization, you performed it with your own tools or with TensorFlow's post-training or quantized aware training options?
What do you mean?
When you performed quantization, did you use your own tools or TensorFlow's tools?
TensorFlow tools.
Good. Okay, so if we don't have any other questions, then we are moving to the next topic. And the next topic would be a presentation of the single image depth estimation challenge. So image depth, single image depth estimation. So in general, depth estimation is also a topic, is also a task that is running on pretty much every modern smartphone. When do you need to have accurate depth estimation? For instance, when you perform bokeh effect rendering, or when you enable portrait mode in your camera. So some solutions are based on estimating data from multiple cameras. There are also some models that are performing single image depth estimation. And in general, this problem is closely related to depth, to getting accurate depth maps for your input data. Also, depth estimation is used for augmented reality applications. It's used for gesture recognition and many other problems that are running on mobile devices. And in this challenge, we are also solving this task. And the goal was to get an accurate single image depth estimation solution, and at the same time to achieve a real-time performance on mobile and IoT platforms. As for the data set, we collected our own data with a stereo Z camera. And this Z camera, it was based on the stereo pair of raw images. It was able to infer quite accurate depth maps, at least for objects that are located nearby. And these images were resized to VGA resolution, and the input RGB image, the RGB image was used as an input, and the target was 16-bit depth data. All solutions were evaluated based on the following metrics. Root mean squared error, it was used to estimate the absolute depth accuracy. So how accurate are the predictions, absolute predictions. And the second one was scale invariant root mean squared error. That is measuring the quality of relative depth estimation, which means that here we want to check whether the relative object, relative object's position was predicted correctly. And all solutions were, the runtime of all solutions was estimated on the Raspberry Pi 4 platform that was running VGA, and the models were predicting depths based on VGA images. The runtime to check the runtime of the solutions on local devices, the participants used a benchmark application, and for testing the solutions on the target platform, they used a special server where they were able to upload their models and instantaneously get the resulting inference time on the Raspberry Pi 4 device. On this slide, you can see an overview of all results obtained in this challenge. First of all, the first thing that I should say is that the solutions, pretty much all solutions were more or less fast, but we had one solution that is significantly more efficient than all other methods, and this solution was presented by Tencent GYLab. And more importantly, for those who worked previously on this topic, you know that fast depth is one of the standard models for this task, and it is considered as very efficient, very fast. And the solution from Tencent GYLab was 10 times faster than fast depth, while also providing very good numerical results. All solutions submitted, almost all solutions from different participants were relying on encoder-decoder architecture, and they were using mobile net or efficient net features for efficient image encoding. And because of these features were used to get features in the encoder block. What else about the results? Also, to check the efficiency of the design solutions, we tested the runtime on several popular mobile platforms. On pretty much all recent chips, recent high-end chipsets from all vendors. And what you can see here is that almost all solutions were able to perform depth prediction in less than half a second. And top solutions were able to do this even much faster. And in particular, the already mentioned solution from Tencent GYLab was able to do this in less than 15 milliseconds on all mobile devices. Less than 15 milliseconds, this means that this is not just real-time depth estimation, it's like several times, even several times faster. And overall, the performance of all models was pretty much good. Especially if we look at the runtime results, almost all solutions are ready for fast depth estimation mobile devices. If you need something super efficient, you can use the first solution. Or you can also use a solution, for instance, from HIT AI labs that demonstrated much better numerical results, demonstrated extremely high accuracy. And if you check its runtime results, the runtime is still quite low. And in particular, let's say on Snapdragon 888, you can achieve more than 10 frames per second performance. And here all models were accelerated on TensorFlow light GPU delegate, and this is also something that I mentioned during the first presentation, that this delegate provides the best ops coverage, and for these models, when we tested them on these platforms, the best results were actually obtained with this GPU delegate, not with an API, not with some other delegates, not with GPU delegate, because it was supporting almost all operators in the majority of models. And now let's move to the challenge winners. The main winner is Team Tensor and GY Lab. That was already mentioned twice. And their architecture is based on, their model is based on unit architecture, and it is using mobile NPU3 for performing efficient input image encoding. And this solution was partly that fast because the input image was resized from VGA resolution to the resolution of 160 times 128 pixels. And to further boost the performance of this model, the authors also used knowledge distillation, and the model was trained with a combination of the distillation and depth estimation losses. The second solution, the second challenge winner is Team Smart. It also based their model on, it also used knowledge distillation to achieve better numerical results and to achieve better depth reconstruction. And you can see the overall scheme of the solution on this slide. So small model, fast depth space model that is using mobile NPU1 for performing feature encoding was used for fast on-device inference. It was the final model submitted in this challenge, and a larger resonance-based model was also used to get much better results on this task, and the intermediate features learned by these models and outputs were also used as additional targets for the small network. And this model was also trained with a combination of the distillation, gradient matching, and scaled invariant losses. We also want to mention the results of the HIT AI team. As I already said, this model was achieving the best numerical results according to all metrics, and one of the reasons for this is that the authors used efficient NPU1 instead of mobile nodes to perform image encoding. And yeah, the second key idea of this solution is to use non-local feature processing block, and in general you can find its description in the paper. And the model was trained to minimize RMSC loss function directly, so no other losses were used. And besides that, in this challenge we obtained several other interesting solutions. If you want to understand how they work, if you want to get a better overview of all results obtained in this challenge, for a better overview of all architectures, and also check the runtime results on our platforms, you can just check the paper, and you'll be able to find all information there. Thank you for your attention. Do you have any questions? Okay, so if there are no questions, then we are moving to the challenge winner, to the solution presented by Tensor and GY Lab, and the title of the final paper is A Simple Baseline for Fast and Accurate Depth Estimation on Mobile Devices, and this paper will be presented by Siyu Tsang. Tsang, welcome. I guess if you're saying something, we cannot hear you, and we cannot also see your presentation. Okay, I think that he will now reconnect. It looks like we have the same issues as with one of the previous presentations here. Let's wait for him a little bit. Okay, right now we can see you and hear you.
Hello, everyone.
Mm-hmm.
Can you hear me? Hello, everyone. Can you hear me?
Yes. We can hear you and see the slides.
Okay. Sorry for the sorry. I'm the first to use the Zoom and let me start the presentation. Hi everyone. I'm Ziyu Zhang from TensorFlow Lab. It's my honor to share my method. It's my honor to share my method on mobile depth estimation. In this talk, we will introduce a simple network structure and a corresponding training method for the depth estimation on mobile devices. This model ranks the first in the challenge. At first, let us take a look at the challenge and see what we have. Most of these have been mentioned before. The provided data is a typical molecular depth estimation and data set. There are 7,385 pairs of images and depths as training data, and another 500 validation data without depths. We split the training data into a training set and a training wheel set. At a glance at the pairs, we could find that most of the images are captured outdoors, which means that we have to deal with a no depth sky, and the depth ground truth at a long distance is probably not accurate. Besides the dataset, we also pay attention to the final ranking formula. As you can see, both the depth of performance and the TF Lite runtime counts. Since the model is deployed on Raspberry Pi with CPU, the runtime is proportional to the model computation amount, which is also known as the G-flops or M-flops. If the model runs 2 times faster, the slog RMSE value can raise 0.05. Then it comes what we have done during the challenge. At first, it is a network architecture. We follow the traditional U-Net-like architecture. It can also be considered as an encoder and a decoder. The encoder comes from mobile nets. We reduce the channels of the mobile net backbone and downsample the input resolution by 4 times. There is a tricky structure in the decoder part. Replace the heavy deconvolution layer with 3 layers. First, we simply resize the feature map by the nearest interpolation, and then we add a depth convolution layer and a pointwise convolution layer to it. The skip connection from encoder is added to the downsample feature map. We name the whole module as the feature fusion module. The computation can reduce a lot by using this module. We trained multiple models using the same architecture but differ in model channels and tested them on the self-split training wheel dataset. Obviously, the large model with the most flops performs the best. However, we need to take a balance between the runtime and the performance. While we must take the final ranking formula into account, the third model outperforms with the highest ranking score. Secondly, we use the knowledge distillation to train the model. The teacher model equips with a Vishin transformer in the encoder, while the decoder follows the traditional model decoder. It uses a large convolution layer as the upsampling model. We do the distillation on hint features because the soft features, that is the output depth, is guided by ground truth and can be seen as a regression for each pixel. So the model will confuse if we distill unsought features. The L2 loss is used for the hint distillation loss. We keep the solution same for both the teacher and the students, and the pointwise convolution layers are added to the students so that the channels can match. These convolution layers will drop in the deployment phase, so the runtime keeps unchanged. The third part of our work is about the model deployment. The model is trained in PyTorch, and it is tested in TF Live. That means the format of the model must be converted. We follow the conversion pipeline, the passes by PyTorch, Onyx, Keras, and finally it reaches TF Lite. The most important part is to convert an Onyx model to a Keras model. Also, it is known as a TensorFlow model. Since Onyx only supports CHW formats, while TensorFlow CPU only supports HWC formats, most of the open source tools fail to deal with it, and they convert a naive convolution layer into 7 layers. They are split, permute, concat, convolution, and split, permute, and concat again. We handle. I don't know whether other solutions handle this problem, but if we convert the model correctly, the runtime of the model can be 7 times faster. Otherwise, we resize the input image small first before it is forwarded by the model, and we also resize the output depth large in the end. That means the model does not need to deal with input images with other solutions. As a result, our model ranks the first among all submitted models. The final ranking score is about 9 times by the second one. The key factor of the winning is the faster runtime. The organizers also test the models on mobile chips. Our model performs well on mobile GPU too. Actually, the network architecture we use in the model is similar to the one we use in the Tencent QQ product. They can run quite fast on most of the mobile phones. Thank you for watching. That's all of my work.
Thanks for presenting your results. And now we have 2 questions for you. The first question was pretty much about how important is the knowledge distillation approach for getting good results in your case. So yes,
you can see this table. We test the models on our self-split train wheel data set. For model 3, if we just training, the final SIRSE score is 0.33. If we add the distillation, the final value is 0.331. Okay, the second question is, what was the second question?
Yes, another question is, what features are used for distillation in the teacher and student networks?
The features on the decoder for each solution.
Yes. Okay. And okay, another question. Any challenges you ran into with knowledge distillation process? Like maybe hyperparameter tuning, model convergence, or some other issues? Okay, yeah, you can just read this question in the chat. So did you run into some challenges when using knowledge distillation?
Oh, I just used this method in this challenge, and we didn't participate in other challenges.
Yes, but this was pretty much the question about knowledge distillation. Whether you, by challenges here means problems or issues.
Oh, okay.
Yes.
this distillation will make sense in the segmentation in our own product, in our QQ production.
Okay. Okay, I'm not sure how this, if this answer, if Stone Yun is satisfied with this answer. Well, I hope that he is. Well, I mean, the main question was when you used knowledge distillation, did you have any problems with it, with training the model? Did you encounter some other issues or something like that?
Besides our models, so our models win the results, but the output depth, if we just see the depth, it's not good at all. It is so the output depth for seeing it is bad. So the gap is we will to deal with this problem in the future.
Okay, I don't think there are any other questions, so thanks a lot for the presentation. And then we move to the second challenge winner, to the solution developed by Huangsong University of Science and Technology, and the title of the paper is Knowledge Distillation for Fast and Accurate Molecular Depth Estimation on Mobile Devices, and it will be presented by Yiran Wang.
Can everyone hear me?
Yes, yes.
Can you see my screen?
No, we cannot see. Oh, there is a share screen option in Zoom, so just you can type it and okay, good, we can now see it.
Okay. Hello everyone, I'm Wang Yuran from Smart Lab, Huazhong University of Science and Technology, China. I'm really honored to be here and share our solution in MAI 2021 Molecular Depth Estimation Challenge. Our method is knowledge distillation for fast and accurate molecular depth estimation on mobile devices. Now let me introduce our solution in detail. Firstly, let me introduce the common network architecture in molecular depth estimation. In recent years, many methods have applied the UNet architecture with an encoder to extract features, a decoder to restore spatial resolution, and some skip connections to recover detailed information. However, based on the similar UNet model, two different research branches have gradually emerged. One mainly focuses on the accuracy, which means they often design models with large amount of parameters and high capacity. The drawback of this branch is that the inference time of their models tend to be long, which limits the application of their methods. On the other hand, the second branch mainly focuses on the speed. They often design lightweight models with short inference time. The drawback of this branch is that in some extent, the accuracy of the models will decrease. So there comes to one significant problem in molecular depth estimation, the trade-off between the accuracy and the speed. In order to deal with this problem, we adapt the knowledge distillation strategy to improve the accuracy of our lightweight model and won the second place in the Mobile AI 2021 Molecular Depth Estimation Challenge. Here comes to the detailed descriptions of our method. To begin with, I will introduce the network architectures of our models. On the left is a student model with lightweight encoder MobileNet. In its decoder, we use depth-wise separable convolution to reduce the amount of parameters. As for the teacher network, with a strong backbone ResNest 101 as encoder, in its decoder, we use a feature fusion block to fuse the abstract high-level features and the detailed low-level features. The student network could achieve high speed and the teacher network could achieve high accuracy. So the next step is to use the teacher model to guide the student model and improve its accuracy. So the next part, I will introduce our knowledge distillation training strategy. We mainly adapt the pairwise distillation in our framework. We extract features with spatial resolution of 24, 48, and 96, calculate the corresponding affinity map, and compute the pairwise distillation loss function, which is a supervisory signal between the teacher and the student model. Besides, we also use the scale invariant loss and the gradient matching loss as a supervisory signal from dataset ground truth. To be specific, we describe all expressions of our loss function in this slide. The affinity map can be obtained by calculating the inner product of two different points I and j, which can represent the spatial similarity of the two corresponding feature map. The pairwise loss aims to guide the student model to learn the spatial distribution of the teacher model's feature map. The scale invariant loss aims to avoid the effect of the difference in depth model scale. The gradient matching loss forces the student model to learn the gradient of the dataset depth map ground truth, which can reduce the jitter of depth value inside some areas. The third part is a description of our experiments and results. We split 600 pictures from the MAI dataset as the validation set. This slide could prove the effectiveness of our knowledge distillation strategy. The picture on the left is a comparison of the performance of the teacher network and the student network. The parameter amount of the student network is 94% lower than that of the teacher network, and its cost is only the SI-RMSE of the student 0.04 worse than the teacher. Compared with the baseline without knowledge distillation, our method have significantly improved the accuracy of the high-speed student network. It greatly relieved the aforementioned confliction of speed and accuracy. When it comes to the speed, table on the left shows the speed measurement results of our student model on mobile phones with different SoCs. It can be seen that on Snapdragon 888, the speed can reach more than 20 frames per second and basically achieve real time. Table on the right verifies the effectiveness of the depth-wise separable convolution in our decoder for improving the speed of the model. This is the official result of the MAI 2021 molecular depth estimation challenge. The table above is the speed testing. The table above is the speed testing results on more different devices. The table below is the final scores of the top 10 teams. Our group is smart and we ranked the second place in the challenge. The final visualization result is shown in this picture. The effect is quite good. You can also seek for more detailed information about our method in our paper. So that's all for my sharing. It's a great honor to be here, and thanks a lot for the hard work of the challenge organizers and all participants. Thank you for your listening.
Thanks a lot for your presentation as well. Are there any questions? Okay, we have a question for you. Was the teacher network only trained on CI-RMSE or on CI-RMSE and gradient losses?
Yes, we train our teacher network using, we don't use the SI-RMSE as the loss function, but we use scale invariant loss and the gradient matching loss, similar to the way we train our student model.
Okay, so they was trained identical.
Yes.
Okay, good. So are there any other questions to the speaker? Okay, if there are no questions, then thanks a lot for the presentation. And we move to the third paper dealing with monocular depth estimation. And this is paper from Samsung Research UK, and it will be presented by MediaTek. And the title of the paper is Real-Time Monocular Depth Estimation with Sparse Supervision on Mobile.
Hello, can you hear me?
Yes, we can hear you.
Okay, so I'll just quickly share my screen. Okay, I'm hoping you can see it now.
Not yet.
Now, maybe?
No.
Okay, just a moment. Okay.
Okay, yes, right,
yeah.
right now
okay.
we can see it.
Okay, should be okay. Okay, so I'll start. So hello, everyone. I'm Mehmet Kerim Mücel, and I'm pleased to present our work, Real-Time Monocular Depth Estimation with Sparse Supervision on Mobile, which is a joint work between Samsung Research UK and CERT ITI Greece. So depth estimation is an integral part of various mobile computer vision applications, as many have pointed out already, such as augmented reality, visual effects, image editing, object scanning, and imagery lighting. The challenges of mobile depth estimation is primarily twofold: model size and use cases. First, depth models deployed on mobile devices should be accurate and compact, which is a dilemma as larger models have higher capacity and thus have higher chances of being more accurate. Second, mobile depth estimation use cases are effectively unconstrained. A user can and will use their phone in the wild settings, including indoors, outdoors, and many others. In mobile depth estimation literature, advances have been made in model optimization for mobile deployment, as we have seen already, but results have primarily been shown in limited settings, such as indoor-only or outdoor-only datasets. In our work, our goal is to create an accurate and lightweight relative depth estimation model. Relative depth, in contrast to metric depth, is essentially modeling depth ordering of the scene by using arbitrary values. Relative depth is ideal for in-the-wild depth scenarios due to its scale invariant nature and robustness to outliers. Moreover, relative depth information is sufficient for many use cases, and it can be extended to metric depth fairly easily. However, relative depth has arguably the sparsest supervision. Just a single point pair and their ordinal relations are provided per image. So we first start with the network design. We adopt the common encoder-decoder topology and choose MobileNet v2 as our encoder. FPNet layers are utilized for the decoder layers, and we use one-by-one convolution and bilinear upsampling as our final decoder layer. And we use skip connections at each resolution. And now we investigate ways to improve our performance without adding further complexity to the model. First, we integrate intermediate upsampling layers. These layers upsample to the output resolution directly and are subject to the same loss as the final layer. And they essentially enforce the network to learn good representations and act as a regularizer as well. We use the upsampling layers at training time and remove them afterwards. Second, as many have already pointed out, we leverage knowledge distillation to further improve our model. We use the state-of-the-art model on DIW, that is the data set we work on, as our teacher, and transfer its knowledge in two ways: by using simple RMSE between depth map predictions and by using a pairwise feature loss between penultimate decoder layers of student and teacher. And we like to note that we introduce RMSE distillation loss to intermediate prediction layers as well, not just the final layer. So our loss function, our final loss function includes three terms: dataset-driven ranking loss, RMSE-based distillation loss, and feature distillation loss. And as we enforce RMSE and ranking loss to multiple layers, we effectively have up to 9 loss terms. So obviously, having 9 loss terms require a laborious loss weight tuning process and often result in suboptimal accuracy. And to address this, we integrate a loss rebalancing method that balances the loss periodically during training. But we do so with key difference to the original method. First, we ignore the value scales of the losses and only focus on loss decay rates. We fix loss weights for different layers outputs and focus on learning hard losses first. And in other words, essentially, instead of manually choosing the lambda values shown in the equation, we let the loss balancing method balance them in real time. So our final pipeline looks like this: our compact model with intermediate predictions, which are removed after training, knowledge distillation, and loss rebalancing. So we start with showing the effectiveness of our design choices. So compared to the two different baselines that we obtained, each of our design choices visibly introduce visible improvements. And we also prune our models and show even the highly pruned version achieves accurate results. Compared to the existing methods, our models are highly accurate despite having significantly fewer parameters compared to, and we also compare with two other lightweight models, and results show that our models are significantly fast and more accurate at the same time. So to roughly summarize, our model achieves state-of-the-art results on depth in the wild dataset in single dataset training setting. Our models are up to 50 times smaller without any quantization or hardware-specific optimization. Our models comfortably reach real-time performance on mobile devices. They run 5 times faster on mobile CPU and 2 times faster on mobile GPUs. Thanks for organizing the workshop, and thank you all for watching our presentation, and feel free to ask questions.
Thanks for the presentation. And yes, we have one question. Can you describe the loss rebalancing method in a bit more detail?
Yeah, sure. So it is, I think, a method published last year at ECCV, but the idea of that method is the contributions of individual loss terms that you have during training are, one, obviously different, two, and they actually differ during the training as well. So if we say if we compare loss A and B, if loss A is contributing in a more significant way, that may not be the case after, let's say, the 1,000th iteration or so. So it is essentially basically giving different weight values to different loss terms during training periodically, and periodically updating the weight. So like I tried to show in the presentation, instead of having fixed and static loss weights during training for different loss terms, we take a look at their decay rates and make sure that we balance them, let's say 5 or 6 times per epoch. So hope that helps.
Okay, thanks for the answer. And we have another question. Good question, actually. Why you are using 7x7 filters of size 7x7 instead of smaller ones? Because this is critical for device inference.
Definitely, that is something that can be improved. And we have other designs, obviously, but within the scope of that study, that is what we presented. But yeah, that's completely a good point.
So it was pretty much chosen to get better results, better numerical results.
Yes, and yeah.
Okay. Good, I guess, this answers the second question. And if we don't have any other questions, then thanks a lot for the presentation. And we are moving to the next paper, to fast and accurate cameras and detection on smartphones. And this paper will be presented by Radu.
Okay, so hi everybody. Thanks, Andrei. You did a very good job so far. Okay, so I'll present this work, fast and accurate cameras in detection on smartphones. This was a work done at ETH Zurich by a number of students, like listed here. And if we are looking a little bit at the history, in 2005, we had the Nokia N90 depicted here. And this camera was the first smartphone with a manual camera scene selection option. And we were getting 5 categories to pick off from, and the different lighting conditions, like sunny, cloudy, incandescent, fluorescent. And this possibility to adjust to the contents, the settings of the camera, was a big step forward at that time for the smartphones and for the quality of the pictures that were taken with such cameras. 16 years later, now automatic camera scene detection mode is available on most of the modern smartphones. However, we have no public dataset and no public models that are available for this task. And each manufacturer designs their own solutions and are often limited to just a number of classes or categories that are picked according to their own choices. Okay, so this problem of camera scene detection was still not addressed by the research community, especially the research community that is academic level. And in this paper and this work, we are proposing a novel camera scene detection dataset, CAM-SDT, with more than 11,000 photos and in 30 categories. And we are proposing also accurate and efficient NPU-friendly CNN models capable of achieving a 99.5% top 3 accuracy and more than 200 frames per second on a recent mobile SoCs. So just to go to the main contribution of this work, camera scene detection dataset, CAM-SDT, was collected from Flickr manually. Each picture was carefully chosen. We have 30 categories, and these 30 categories were picked by looking at the commercial solutions and to see what kind of categories are there. And we combined what we saw and picked a number of 30 categories that are the most relevant for our task. Then the resolution is brought to 576 times 384. Is just a reasonable low resolution for such a task of image level categorization. And we have around 350 photos in each category. And we have a quite large diversity that is coming from the source, the Flickr, for our pictures. Here are our 30 categories, and one picture in each category are pretty much good sampling that are showing the diversity in our dataset. And yeah, these 30 categories, if is to say a little bit more exactly what they are, and with some description, we listed here. So we can see portrait, group portrait, kids, infants, the dog, the cat, and so on. So are the most important categories from the point of the view of the final user of cameras. And the second contribution in this work comes from the camera scene detector. And in our case, we relied on the mobile net V1 and mobile net V2 as backbones that are very efficient. And if we are looking at these mobile nets architectures, are based on depth-wise separable convolutions, with the exception of the first layer that is fully convolutional. And all the layers are followed by batch normalization and ReLU. This is just pick up a little bit the mobile net architectures, and are specifically designed for mobile and constrained hardware, are quite efficient designs. And moreover, all the vendors are containing quite a lot of low-level optimizations that are allowing such architectures to run very well on their devices, on their cameras, on their mobile devices. Okay, so in our case, we adopted these backbones in these simple ways. We consider that given the rather small dataset that we have, 11,000 images, when compared with other classification datasets like ImageNet or Microsoft Coco with thousands of categories and millions of images, we consider that it is very important to do a knowledge transfer, and we are taking the MobileNet V1, MobileNet V2 already pre-trained on ImageNet, and we are just changing the final layers such that to benefit from the knowledge that is accumulated in the classification on a much larger data set with a much larger number of categories. Okay, so MobileNet V1 is adapted in this way. We are just removing the final connected layers at the end and replace it with a fully connected layer with 1024 units. We are using dropout with 0.7 and the sigmoid activation function. And on top of that, we are relying on softmax for taking the final decision. Then for MobileNet V2, we are adding a fully convolutional network layer with 256 and ReLU, another one with 1024 and ReLU, another one with 256 and dropout and sigmoid, and on top of all the softmax. So on the right side is you can see the MobileNet V1 in our choice. And why we picked sigmoid? Because in our experiments led to the best top 1 and top 3 accuracy on our training data. Okay, and this was valid also for MobileNet V2. So in both cases, we chose the sigmoid for the final fully convolutional, fully connected layer. Okay, so now if is to compare the result that we are achieving with the MobileNet V1 and the V2 with our modifications and training or further training on our dataset. Okay, we show here we are achieving quite good performance, not only for MobileNet V1 and V2, but also for the quantized versions in comparison with other networks that we trained and adapted to our task. Okay, the other networks, we did the same. We took the pre-trained ImageNet networks and further tried to achieve the best using our data. So from here we see that MobileNet is doing a very good job. And moreover, if is to look at the speed on the popular mobile SOCs, we have here a good number of such SOCs. And we see that on Dimensity 1000 plus, we are achieving more than 200 frames per second for both floating point 16, but also for NP8 quantized model. And the same goes for the MobileNet V2. So in both cases, we are getting more than 200 frames per second, and we are getting more than real time on most of the architectures that we checked here, hardware devices that we had here. Okay, so in order to compute our runtimes, we employed the AI benchmark app, and already Andrei repeatedly mentioned the main steps into using this app and the Logica model and setting the choices for the environment and picking up the final runtime and the latency and some other measures. Okay, so having these solutions was interesting to go in the wild and check if really one new images that are captured without any constraint, okay, really will perform as we are expecting with a very good accuracy. Okay, so here are a couple of examples, and in all those examples, the top selection of our detector is matching what we'll have considered to be the real ground truth label of those images. We have the candle, we have the leaves in the autumn, we have the text document, and we have a cat. And here are even more samples, and in the large majority of the cases, our mobile net-based models were predicting very good, accurate the category. Okay, here we are just showing a couple of results, showing model predictions for different object types. In the case of flowers or illumination conditions, the cat, okay, or different viewpoints. For example, if we are looking at some computer screens. Here are even more examples showing mountain images or waterfall with different angles, okay, and we are still doing quite fine. And here cloudy skies in the same scene with mobile net V1 and V2, and seems to agree and to do a good prediction. Okay, also a couple of examples where is failing. For example, in the case of over and underexposed regions, like here, we are getting a night shot when it's clearly is daylight, but we have a big shadow. And here we are getting snow when probably the correct label will have been a waterfall or mountain that is coming in top 3, actually. Okay, and here model predictions for the same mountain scene in a portrait and landscape mode. And we are seeing some difference in the classification output. Okay, also an example of macro scene. And to conclude, in this work, we propose a novel camera scene detection dataset with 11,000 manually crawled images belonging to 30 different scene categories. We propose an efficient and NPU-friendly CNN model with top 3 accuracy of 99.5% on this dataset and more than 200 frames per second on the top and more recent mobile systems on chips. Okay, and additionally, we conducted an in-the-wild evaluation to analyze the performance and the limitation in real-world scenarios. Okay, we are making the dataset and the pre-trained models from this work available on the project website, and this dataset, as Andrei will present in the next, was used for the a challenge in the mobile AI workshop. So this was the presentation. Thank you for your attention. If you have questions, please let me know.
Okay, thank you for the presentation of this paper. Are there any questions? Okay, if we don't have any questions, then we move to the challenge paper. Second. So, quantized camera scene detection challenge. Rado has already introduced the task and the problem. So, almost all modern smartphones come together with AI recognizer. And why this is critical? Because camera scene detection is used to adjust photo shooting settings and image processing, and the steps applied after you obtain the image. And right now we have pretty much only proprietary solutions developed by each vendor separately, and for many models we also have, for many solutions are also using either a limited number of categories or lots of categories, but the majority of them are actually useless for a scene recognizer problem. And in this task, in this challenge, we were addressing exactly this task. So the models had to classify image to one of 30 different scene categories. Besides that, all models had to achieve real-time performance of mobile and IT platforms. And finally, the models had to be fully quantized so that they can run efficiently on integer-only NPUs. As for the dataset, as was previously introduced, we use the camera scene detection dataset that consisted of 30 categories and more than 11,000 images. And to evaluate the solutions, we used top 1 and top 3 accuracy. And the runtime was evaluated on the Apple Bionic A11 platform. And all models were classifying 576 times 384 pixel images. And the runtime to evaluate the runtime of the models on locally, the participants used a benchmark application, and to check the runtime on the target platform, they had to upload their model to a dedicated server, and after that they were getting the runtime on the corresponding Apple device automatically. And here you can see a general overview of the challenge results. As you can see, all solutions, there were no problems with efficiency. All solutions were demonstrating very low runtime, and the majority of them were able to achieve more than 50 frames per second on the considered hardware. Almost not surprisingly, the majority of models were based on some existing architectures, mainly mobile nets or efficient nets. We had only one solution that was purely convolutional, that was not relying on any particular model, and this solution was developed by Team Siddiqui, and as you can see, its size was 72 kilobytes, so this was an extremely small model, delivering like extremely fast runtime. Yes, its accuracy was not that great, but still top 3 accuracy was more than 93%, therefore it might still be interesting for very small embedded systems. So when looking at the results, almost all solutions were able to get top 3 accuracy of more than 97%. The best result, the best overall result was achieved by, not surprisingly, was achieved by ByteSyn team, and this model was able to get a top 1 accuracy of 95% and top 3 accuracy of 99.5%. And yes, besides the evaluation of the Apple chipset, we also checked the performance on all major recent mobile SoCs from Qualcomm, Samsung, Huawei, and MediaTek. And you can see that in this, since we got into 8 models, it was possible to accelerate them efficiently on dedicated silicon. Unfortunately, we were not able to run it on the latest Snapdragon 888 device because all models pretty much failed, since a hexagon delegate was not available on this platform, and therefore we eventually had to run these models on its GPU. But despite of this, the results were very good. And in particular, if you check the runtime, the obtained frames per second results, and on all platforms, top solutions were able to achieve more than 70-80 frames per second. And let's now just discuss the solutions presented by challenge winners. Team ByteSyn proposed a model which architecture is more based on the MobileNet v3 model, and this architecture was additionally refined with hierarchical neural architecture. And this team additionally used transfer learning, so they also trained a bigger ResNet based model and used this model. First they trained it on, fine-tuned it on the camera scene detection dataset, and then used it to label some extra data that was used for training the smaller one. The model was trained with categorical cross-entropy loss function and quantized with standard post-training quantization tools, TensorFlow post-training quantization tools, and as far as you can see, there were no issues with quantization, with the accuracy in this case. The second solution proposed by Team Huawei, it was based on the MobileNet v2 based architecture, and this solution was very efficient, primarily because of heavy downscaling of the input data, of the input images. So these input images were sized to a resolution of 192 times 288. And besides that, it was pretty much a standard mobile net-V2 model with some additional modifications and some dedicated several dedicated layers on top of the main feature extraction block. The model was trained with cross-entropy loss function and also quantized with TensorFlow's post-training quantization tools. And in the paper, you can find several other interesting architectures proposed for this task and several other approaches. And again, everything is described in the article, and feel free to check it and analyze the results, the runtime, and the solutions presented by challenge participants. Thank you for your attention. And if you have any questions, you can write them in the chat. Okay, and if we don't have any other questions, then we move to the next paper, mobile human pose towards real-time 3D human pose estimation in mobile devices, that will be presented by Sangmoon Choi. Sangmoon Choi, welcome.
Hello, everything's fine?
Yes, everything is okay.
Yeah, hello. Today I'm going to introduce mobile human pose for real-time 3D human pose estimation in mobile devices. For brief information about 3D human pose estimation, traditional 3D human pose estimation has two approaches, which are a bottom-up approach and a top-down approach. To be more specific about top-down approach, since our work is a top-down approach, first, it uses human detector to crop individual human in input images, and then individually cropped images are fed into a pose network to get a final result about as this output results shows. We have one baseline paper and one similar paper. First, 3D MPP is our baseline paper presented in 2019 ICCV. It is open source, strong baseline, and easy to modify. On the other hand, MoveNect, presented in 2021 is exactly same target goal with our paper, which is mobile targeted modeling. However, both paper has drawbacks. Moon's model is not compatible to mobile devices, and Huang's model is not having a good model robustness, and also it is not an open source code. So based on this fact, our paper introduced new model which is compatible for mobile 3D human pose estimation with following two approaches. First, since our initial version of model simply changes the baseline with respective to ResNet 50 model into MobileNet V2, we had more capacity to increase flops related variables such as like channel multiplication variable alpha. So similar with neural architecture search concept, we manually define the search space candidates, experimenting with the various channel multiplication variable alpha. So as the result, we found out that enlarging with first inverted residual block lead the maximum performance gain among these 7 inverted residual blocks. Also, we tested efficiency of pre-training algorithm since we manually changed MobileNet V2. We compared the result with pre-trained and random initialized model. Due to human pose estimation dataset is large enough to train this model, we do not need any preliminary knowledge learned from ImageNet, so the result we can say the random initialized backbone was more efficient. Also, we applied additional changes which is irrelevant to inference time. First, we add skip concatenation, which is similar with UNet. These changes lead to very high performance increment with very small changes in inference time, which was less than 2% in inference time. Second, based on the Blutz paper presented in 2020 FG, PR value function led performance increments in 2D human pose estimations. We also followed these changes and had performance increment while maintaining inference time. Here is our final performance result with two different data sets. Our large model shows comparable results with state-of-the-art models with extremely lower parameters. And this is our main result comparing inference time result with two models, which is Moon's and Huang's. We had a 3 different model size comparison and XX, denoting as extra small model, is used for final real-time 3D human pose estimation in the next slide. As you can see, extra small model not only had a better performance compared to Huang's model, but also reduces the inference time. This is our final demo video comparing with Moon's model since MovieNect Huang's model is not available in public. We tested with iPad Pro 9.7 without applying any post-quantization modeling, which means running in a CPU. Our model shows 3 times faster inference time compared to the Moon's model. Thanks for listening, and please follow our project page for all the details, including the applications and also the training codes. And we thank to Do Young Kwak for making this demo app for this project. Thank you.
Thanks a lot for the presentation. Are there any questions? The results are really looking great, especially this animated video.
Sorry, did you say it again?
No, I said that the video looks great. So the performance of the model was really awesome.
Thank you.
Okay, so if there are no questions, then we're moving to the next invited talk that will be delivered by Felix Baum. He is Director of Product Management at Qualcomm Technologies. And Felix will tell you quite a lot about efficient inference on Qualcomm hardware. It will tell you about different accelerators that were already mentioned in the introductory talk, and he will tell you how to squeeze almost all power out of this dedicated AI hardware that was developed by Qualcomm. So welcome, Felix.
All right. Andrew, you can hear me, right?
Yes.
And see my screen.
Yes.
Perfect. Awesome. So what I'll talk about is some of the things that have to do with not so much model development, but I think in the last few sessions, the one thing that consistently I heard was that you guys are inventing new models, you guys inventing new techniques, but unfortunately on some of the hardware, sometimes it works and sometimes it doesn't, and performance levels don't really match to what is expected. And this is kind of the theme of my presentation. To start with, I want to make sure that folks understand that when we talk about AI, I mostly care in my day-to-day job about on-device AI algorithms, running things on device, running things on a mobile platforms where privacy, performance, and personalizations are really, really important. My customers and what I help consumers with is making sure that they can utilize AI models in mobile devices, whether it's your cell phones or things like that, in IoT devices, whether it's a secure camera sitting in, or doorbell, or smart speakers, and also in automotive environment. And what you'll find is everything that you guys talked about, all these fancy video processing algorithms, all of the mobile net models and others. As a matter of fact, they actually scale pretty well and transfer from one vertical, so to speak, to another, because a few years ago, some of us might remember that we talked about using 3D face authentication to unlock your phone or process your payment. Then exactly the same model, exactly the same technology, scaled down to a much smaller standalone cameras or the doorbell ring. So as you walk up to your house, without having to pull the keys, your doorbell camera will recognize that you're an owner of the house and open the door for you. Rewind times a few years forward, and nowadays we have cars that are also smart, that have the same cameras in them, running exactly the same algorithms that you guys talked about and deployed in a mobile environment a few years back. Well, now suddenly as you walk up to the car greets you, opens the doors for you. You sit in the front of the driver's seat, the car recognizes you and allows you to start the engine. It might even be sophisticated enough to look at you and say, well, you might be impaired, so maybe it's not a good time for you to drive, and actually shut the engine down. So, but let's not go talk about those use cases right now. But as the deployment of these models scales from the low end, kind of a smart speakers, watches, and others, all the way into mobile phones and automotive environment, the scale of AI performance and need grow further. I'm not talking about server market where you have a big data farms and everything else. I'm talking about cloud, edge, where in between your mobile device and in between the server farms, you have some additional AI processing where you can do some additional inferencing without having to send all your data back into the cloud all the way. When it comes to developers, we see kind of two types of developers in general. There are experts that know what they're doing, and most of them attending this talk right now and this sessions, this event. And then novice, people that might be not novice, but they're experts in their particular technology, and they're just using AI to help them to address particular things. And to them, performance is important, but scalability is much more important. They want to make sure that their app runs everywhere. As a matter of fact, Andrew and Radu know that perfectly well because their benchmarking app needs to run on Qualcomm devices, MTK devices, Huawei devices, Honor devices, Xiaomi devices, and obviously Samsung phones as well. So scalability is much more important to them. Some of the misconceptions: if you're building and deploying your models, as some of you guys talked about on the call right now, in the cloud and an edge and the embedded devices are similar, and this is not exactly true. The frameworks are different. The quantization used to be hard, but nowadays, even for this competition that Andrew talked about earlier, the competition was built in mind to help with, from the get-go, with the quantized models. We didn't start saying, hey, build a floating point model and get it to run everywhere, and then let's see how low can you go when you quantize it. So I think that we see the change in the market because of that. But if I am a developer and I'm building an application, the simplest thing to do is to run on a CPU. Everybody has a CPU in their devices out there. Mobile devices has ARM CPUs. There are some Intel CPUs. If you get your app to run on a CPU, you can run it everywhere. Yes, it's going to run probably floating point 32, not very efficiently, but portability is, if portability is important to you, then this is a one way to go. If you want to go to the embedded devices, you're probably starting up with a training your model, whatever it's a PyTorch or TensorFlow or OnyxNet. I've heard a presentation earlier where the folks were saying, well, we build a model with a PyTorch, but then we have to quantize it to convert it to Onyx, but then we couldn't get the Onyx to run, so we had to translate it in TensorFlow Lite, and then we got it to run. Well, that's a lot of conversions. Each one of these frameworks are different. And I don't want to go into the religious battle of which frameworks to use. Let's just say there are many of them. And some of them are more optimal for certain things than others. When you go to the hardware, not on the CPU, but in a real hardware with accelerators, a lot of times customers start with a floating point 32. And the first initial questions that I ask them, why not quantized? Because with the int8 quantizations, things are much more efficient. Things are much smaller. These are just a few of the examples, how much savings you get if you go from floating point to the int 16-bit or int 8 or even int 4 for that matter. I think the next question that we usually ask is, okay, so you start with a floating point 2, you train your models, you go to the device, and then you determine whatever you can drop down to int 8, int 16, or FP16 or floating point 32 on a runtime, on acceleration level. And then there are certain tools that can help you with that. You need help with quantization, help with pruning, maybe optimize and minimize your model, all of that without trying to lose your accuracy. And then we come to the runtime framework. You get your model, you train it, and then you get it to run on an embedded device. There are different frameworks that are available there than the ones that you use to train. Some of them have different cadence, some of them have different performance, some of them have different scalability. And as a developer that wants to build a model and deploy it everywhere else, the choice of the runtime framework becomes really, really important. Here we have from Qualcomm, for example, Qualcomm neural processing SDKs, their Onyx RT frameworks, there's a PyTorch mobile framework, there's a TensorFlow Lite framework, obviously there's an NNAPI framework. I think it is extremely important for you as a developer, once you build your model, once you try to get it to run in the most optimal fashion, to understand what are the advantages or disadvantages of one of these models, and also the scalability that comes with it. And an API up till recently, for example, only used to be updated, cadence used to be once a year. So it doesn't really matter if you're building super duper efficient model using TensorFlow or TensorFlow Lite. You can't get it to pass through an API. So the only accelerator you have available for you to execute your TensorFlow Lite model would be CPU with lackluster performance. Lastly, a lot of the frameworks, the runtime frameworks from some vendors actually hide accelerators from you. So you get your model, you quantize it, you do everything that you need to do, you run it on a hardware, and it runs really slowly because you don't even have visibility into which accelerator you might pick. Again, if you're an expert, then you might go and say, you know what, I want my model to run on a CPU or on a GPU or a NPU or hexagon tensor processor, because those are particular accelerators that deliver me the best performance, whatever your requirements are. Maybe you care about accuracy, maybe you care about inference per second or inference per watt. They're not the same. They support different data types most of the time, and also support different level of concurrencies. And for developer, it's really important to understand how this works. At Qualcomm, we provide kind of a low-level library that allows us to take any one of these runtime frameworks and be able to accelerate them by providing these backends to each one of the accelerators. So once we support any one of these frameworks through this low-level library, you can guarantee that doesn't matter which other framework you're using, you have the same operator set available and everything there to be able to take advantage of the underlying hardware. Our latest hardware is actually the sixth generation hardware that we have for accelerating AI workloads, specifically on a mobile devices. We call it Hexagon 780 processor. It is a combination of a few things, because over the last few years, what we learned is that some folks talk about convolutions when they're thinking about AI, but convolutions is just part of the AI processing. Yes, there's matrix math, but you also have to do a lot of setups. There is also a lot of fully connected layers. So if you look at kind of combination of scalar processing and a vector processing and a matrix math, you realize that it is important to have an accelerator that can be good at all of these operations, which is why in the latest generation of our device, we actually fused all these technologies into one cohesive engine that can do all of them. We see some vendors that would have kind of a big DSP to process camera, vision, traditional algorithms. And then they would have a smaller AI accelerators. Well, a lot of the workflows, a lot of the use cases, and Radu, a previous speaker, actually talked about some of the experiments that they run. They're actually a combination of that. And not only there's a flow, you do this to an image, then you do this to an image, then you do that to the image. You actually have to parallelize a lot of this while you're processing certain things on a frame number one. if you're doing live video inferencing, as the frame number 2 comes in, you actually kind of shift and do certain things in order. So concurrency is also important, which is why we're fusing this technology and doing everything in one. So with our AI accelerator, we do scalar math, tensor math, vector math. We're also utilizing our GPU in parallel with that. So there are certain workloads that we can say, you know what, we're really running out of compute power available in our hexagon tensor processor. So we would go and parallelize certain things by allowing GPU to take some slack and also execute certain workloads to be able to come up with a compute power to handle some of these advanced use cases that you guys talked about. Lastly, if you look at our software stack, it looks very similar to what I just described, kind of a normal process. We have runtimes that we support for the runtime frameworks. We have a lot of converters for the training and everything else. We have tools like an AI model efficiency toolkit to help you with pruning of the models and doing other things. And then we even have compilers like TVM in case if, God forbid, we don't support a particular layer or particular operator. We provide you with a TVM so you can run your code, write your layer in a PyTorch and compile it using TVM and get it to run on our hexagon tensor processor or GPU or CPU if needed. Lastly, performance. Again, I talked a lot about performance. I talked a little bit about accuracy. But if I want to go and look at the end result, there's nothing better than trying to use the benchmarks that's out there. The benchmarks are different. Each one of them has its own pros and cons. Here, what I have is I just grabbed a screen from the AI benchmark website, and it lists the processor. It also lists some tests, and it lists some scores. It is really important to kind of look at it and try to be able to understand what am I trying to do and what scores am I looking at. And in this particular case, you can kind of break down the test and say, you know what, here's my CPU test and CPU performance. Here's my GPU test and performance. Here's my hexagon tensor processor, for example, if you're using Snapdragon devices performance. And you can kind of look and say, well, gee, you know what, on a CPU, my score is 5,000, whatever. It doesn't really matter what the absolute number is. But if I go look at a hexagon tensor processor, the final score is 10 times more, 54,000 in this particular case. It's also important to try to look at your workloads and try to figure out if you're trying to process one image at a time, kind of batch of one processing versus batch of many, where you have a video stream coming in and you load a model, and as a picture is showing up, you're trying to do the same processing on a many images at the time. So again, sorry for going pretty fast, but the takeaways is not all applications are built the same way, and the way you use the software stack is really important and will determine how well your application will perform and how scalable it is going to be. So please, please, please take a look at the software stack, and please take a look at the hardware available, and then you can truly achieve great performance for these really super duper advanced models that you guys are working on and we're presenting at this event. So with that, I will wrap it up. Any questions?
Okay, thanks a lot for the presentation and for all provided information. So we have one question about TVM compiler, whether it is publicly available, whether it can be just used by regular developers to compile the models.
Absolutely. We have our website with a customer where customer can log in. That TVM compiler is posted there, so our clients can come in, get a downloaded version of the TVM for the hexagon, and then be able to literally write any operator, any code, compile it in int8 or int16 flavors, and in fact, not only they can compile that code to generate their own custom operators. The frameworks that we have, whatever it's a Snappy product from Qualcomm or QNN product from Qualcomm, we have a ways where you can what we call is user-defined operator technology, where you can actually hook up those operators, custom operators that you just defined and built, and extend the capabilities of our runtime frameworks to now add support for a particular layer that you just built. Yep.
Okay, thanks for the answer. Okay, and then several other questions probably from my side. So today in the previous presentations, Google announced that Qualcomm 888 will be the first chipset to get updatable NN API drivers. As for the other chipsets, are there any other plans to also release updatable drivers for some other SoC models?
For other models, I'm sorry.
Yeah,
for other runtime frameworks?
No, for other SoC models. So as I said, for Snapdragon 808, and then API drivers become updatable. Are there plans to also do this for some other chipsets?
So I think this was one of the biggest limitations in my mind for the success of the NN API framework, because the cadence used to be a cadence of an operating system. So as Android goes from Candy to a Candy to a Candy, from a version S to a T to a Q, or whatever, well, the other way around alphabetically. But every time you go to the new version of an Android, you get a new version of NN API, and you get new operators or some new features. That's a year apart. And the year in AI world is like a century. So we work with Google very closely to try to be able to help them to figure out how to get it done and how to come up with a framework that will allow you kind of dynamically upload newer versions of the NN API and the backends that accelerate it. We work with them to help them on our devices. I would assume that they also have other partnership with MTKs and with other customers to make it work the same way. Unfortunately, that question should go to Google, and I don't have visibility into how are they working with MTK or Huawei or other silicon vendors. Sorry.
Okay, no, the question was pretty much about Snapdragon chipsets, whether apart from Snapdragon 888, some other models will get.
Right. So that is actually a very tricky question. And what we were trying to do is you need to have certain hooks in operating system and certain hooks in underlying technologies to be able to go and dynamically update it. Obviously, going forward from kind of this generation of the chipsets, everything will be built into the OS to allow for this upgradability. And we're working with Google. We work with Google to figure out how to do it at least 2 or 3 years backwards as well. So obviously, there's updates required. Obviously, there's some security considerations to be able to go backwards, update those versions of an operating system to enable those hooks that will allow Google mobile services to operate properly, to be able to download the newer version of NN API into these year or two old phones. And I think that the framework is in place. How fast can Google roll it out, and how fast and often the but the phone manufacturers will pick up those patches and propagate them into the deployed phones. That's unfortunately up to the individual mobile phone OEM, not even to us or to Google.
Okay, another question. So today I already mentioned that there is Hexagon DSP delegate and that it should be used pretty much for all the devices. Can you say a few words about its future development? I mean, in the introductory talk, I mentioned that whenever the guys want to run something on Qualcomm hardware, whenever they want to run quantized models on DSPs, on older generation devices, they should be using Hexagon and NN delegate, since it is delivering better performance. And the question is that, yeah, maybe you can say something about the future of this delegate.
Absolutely, absolutely. That's a very good question. I think with what we had in place is we had an existing capabilities with existing frameworks, and we worked with Google a few years back to develop this Hexagon and NN delegate. This year, we transition into this fused hardware architecture and a different software stack to enable it. And unfortunately, for a large company like Google or TensorFlow, Light folks for that matter, they don't really care that much about advanced and next generation devices as much as they care about scalability and volumes. So obviously, they care about most of the phones out there that have been shipped for the last few years, whereas Qualcomm cares about new phones, new architectures. So what we did because of that is we transitioned, and from kind of a traditional Google built and distributed hexagon and delegate, we transitioned into something where Qualcomm ourselves, we ship TensorFlow delegate for these newer devices. It is called QNN TFLite delegate. We already built it. We already provided it to a few customers for testing and validation. And we're within the next few quarters, we'll provide it to everybody else, whether it's benchmark vendors or OEM or third-party developers, so they can integrate directly with it and take advantage of some of the features that are, or performance that kind of not available inside of NN API.
Okay, thank you for the answer. And then probably the last question. So this question popped up several times today. So if our model contains some floating point and quantized operators, so like half of the model is just doing floating point operations, half of the model is doing quantized operations. We know all that with NN API there are some problems with accelerating the model because usually it fallbacks to CPU and there are no other options how to run it. How to accelerate it on Qualcomm's hardware?
So I think the first of all, if you have a model, any kind of model, we would really love if you take your model and you move it to the int8. Obviously, as you said, sometimes the accuracy would be degraded so much that it's unusable. Our next choice would be, and we have tools for that, where we allow you to take your model, fall back to see if it's good enough to run in int16, because it will still give you a good performance with almost on par to FP16 accuracy. We've done a number of studies. As a matter of fact, we're presenting at this event in another session where we're talking about the int16 versus FP16 accuracy and how close they are. If you get to the point where indeed int16 is good enough accuracy, then the very next thing we're doing something this year, and you'll hear us talking about it going forward, is we're actually allowing customers not just split their models into chunks where you say, here's a subgraph that's int16, here's a subgraph that's int8 or FP16 and int8, and then run maybe this part on a hexagon and this part on a GPU or a CPU. We're actually working on kind of a mixed precision capabilities where our runtimes will allow you to run your models and have sophisticated tools that will go and partition it and say, this chunk does this particular type of data types, and then transition to the int8, then transition back to int16, and then back and forth, and doing it in a very sophisticated manner where we don't just allow you to kind of go back and forth for every operator. We kind of split the subgraphs into chunks that are large enough to make sure that you don't get penalties from transitioning back and forth, upscaling, downscaling, upscaling, downscaling. So that would be something that I think a lot of folks can try out. And we have tools, actually, they're publicly available, AI Model Efficiency Toolkit. You can go to the Git and download it and see how it works. And you should be able to go and see how you can take your floating point 32 or 16 models and get them to run in int16 or int8 with as good accuracy and a much better performance.
Okay, but this toolkit, it will not be able to perform int16 quantization of TensorFlow models, so that at the end you are getting also int16 TF-Lite file, right?
Sorry, Andrei, can you ask it again?
So with this tool, it's still not possible to just quantize, perform int16 quantization of the standard TensorFlow model and get the resultant TF-Lite file. So you are, at the end, after applying this toolkit, you are getting models stored in your appropriate format, right?
I think that the tool, again, I'm not an expert in the tool, but my understanding that it takes your model in whatever format you come, whatever it's a TensorFlow or PyTorch, and the tool does analysis and comes back with kind of your original model and suggestions on how to modify that model to achieve the results that you want to. Then you take that result and you feed it into your quantization process to whatever Quantized that we're training or some other tool that you would use from Qualcomm or other vendors to be able to integrate those suggestions into your actually quantization phase. The tool just does analysis and provides you with the results of that analysis. It doesn't really quantize things or changes things.
Okay, well, the reason why I answered this question is that TensorFlow Lite still has issues with N16 support, and so this is basically the problem, that no one argues that with N16 you'll get good accuracy. The problem is that for normal guys, for normal developers, if they want to get quantized in N16 quantized TF-Lite model, there is actually not an option. And so that's the biggest.
Okay.
That's the
All
biggest
right.
limitation.
Well, I think that the Git tree is out there. There's a website for that tool. Feel free to either send the request to that website or post it on that website, or just send that to me directly. You have my contact information here, and we'll consider the features and capabilities and see what we can do to integrate those into the product.
Okay, thanks a lot for providing the answers to all questions. Thank you for the presentation.
Absolutely.
And
thank you very much.
I don't think that we have any other questions are left, and therefore we'll move to the next talk. Also, actually talking about image quantization, and the title of this talk is "Do all mobile nets quantize poorly? Gaining insights into the effect of quantization on depth-wise separable convolutional networks through the eyes of multi-scale distributional dynamics." And this talk will be given by Stone Yun. Stone Yun,
can everyone hear me?
Yes, we can hear you.
Yeah, it's a pretty long title, so I didn't even plan on reading the whole thing.
Yes.
But yeah, so I'll just share my screen first. Sorry, so I think it would be this one. Right, is this showing up, the laser pointer and everything?
Yes.
Okay, great. So yeah, I guess like kind of an easy transition into the challenges of quantization. We've kind of seen from the different events and the different models that have been presented that there's depth-wise separable convolution is going to be is become a ubiquitous form of making our models more efficient. And on top of that, quantization is a great tool for creating energy efficient and latency efficient models for our mobile inference. And so as we've kind of seen though, is that besides being really fast with mobile nets architectures, there's a lot of issues with quantization. When you just do normal post-training quantization, it often degrades to almost like random chance accuracy for ImageNet. You can see here from our own recreated results, we could get slightly better than random, or actually, but it's still very poor performance, and there's a lot of error. And so in this work, we wanted to see why we need all these tricks like quantization-aware training or data-free quantization or even mixed precision quantization. And because there might be settings where if you want to create a more robust model that can be deployed at different precisions. I've seen there's literature lately about 4-bit quantization or 5-bit quantization. If you do stuff like quantization-aware training where it's very bit width specific, then it might not necessarily, it's not guaranteed not to scale, but it's also not guaranteed to retain that quantization accuracy as you go to different bit widths. And so we wanted to get a better understanding of why mobile nets quantize so poorly, and we were doing this through some layer-wise analyses of the weights and activation distributions in some depth-wise separable networks, and we found that oftentimes the depth-wise conv layers, the weights learn some rather large ranges, and there's this greater distributional mismatch between the channels and tensors. And so this is, we saw from layer to layer, this leads to some greater accumulations of quantization error and distributional shift. And so for our main study, we were doing an ablation study on CIFAR 10. We wanted to compare a basic regular convolutional network and a depth-wise separable convolutional network. So you can see the architecture here on the left. And so yeah, we had these two basically toy net architectures, and then we besides changing the architecture, also varied the random initialization methods and whether or not to use batch norm scaling, just to try and better delineate and disentangle the effects of architecture versus other hyperparameters that might affect the final train distributions of your model. And so on top of doing a systematic ablation study, we did a novel multi-scale distributional analysis of each trained network and looking at the quantized 8-bit behavior. And so by multi-scale, really what I mean is we wanted to analyze at the network scale, the layer-wise scale, and then the channel-wise scale. And so by doing this analysis, we could get like a better picture of how the CNNs interacting with quantization noise and how that leads to the observed output behavior we have with our various quantized models. And so we saw mobile nets, there's the spiking ranges and what I end up calling a distributional mismatch. So even on like an easy data set like CIFAR 10, we can see that on average, the depth-wise separable networks are going to perform worse after quantization if you just do your normal post-training quantization. And that's kind of reflected in the larger, besides the degradation in accuracy, you can see there's a larger quantized mean squared error, indicating more error, and then the QKL divergence was basically KL divergence between your floating point model and your quantized model. So there's like a distributional shift reflected there. And so these output quantization error metrics give us an idea of the overall effect of quantization. And then on the next slide, I'm going to do like a little more fine-grained looking at the layer-wise weights and activations distributions and how that might interact with the quantization noise and the resulting dynamics that we've observed with these networks. So yeah, over the top here, we have our depth-wise separable layer-wise plots, and then on the bottom was the regular convolutional network. And so I mentioned the spiking ranges on the depth-wise layers, and that also happens to coincide with a drop in precision. And so by average precision, what I mean is like the ratio between the channel range and the layer range. And so if you have a lower precision, that means that's this distributional mismatch where the overall 8-bit encoding for the entire tensor isn't really representative of the true distribution of information encoded in our weights. And so we kind of see how, like from this difference in scale, that there's a much greater accumulation of quantized error in our depth-wise separable networks compared to like a regular or dense convolutional network, as well as the precision, it doesn't have as much fluctuation in the regular networks. And we see a similar but greatly aggravated version of this picture when we looked at two ImageNet trained models. I got the MobileNet V1 and VGG ImageNet trained checkpoints from the Google repo. And so you can see here there's a massive spike in range, especially early on in the MobileNets network. And that coincides with this drop in precision. So the information in the network is effectively like destroyed at that point, even early on in the network. And so this was due in part to batch norm folding. So typically with mobile inference, you're going to fold the batch norms into the previous layer's convolutional weights to optimize the inference speed. But that can lead to distributional shifts in large ranges. But we also saw that besides batch norm folding, the mobile nets weights themselves, when we were doing our analysis, were also pretty large, even prior to the batch norm folding. And so this issue of like the greater distributional shifts is like further exemplified by this plot here comparing the QKL divergence of MobileNet and VGGNet for ImageNet training. And so finally, for future work, obviously, we know that like the features extracting these distributions learned, they come from the data set. And so I'd like to see how different optimizers and different data sets could further affect these distributions. I'd also like to try applying some regularization or normalization techniques for helping reduce this distributional mismatch and hopefully boost quantization accuracy and make it more robust. And then also like for this initial study, we looked at like MobileNet V1 and like a more VGGNet-like architecture because I wanted to isolate just the convolutional layers. But as we know, with most of our models these days, they're more complex with various connection patterns like skip connections and concatenations. And so there definitely needs to be some more work analyzing more complex CNN architectures like that. Thank you.
Thanks a lot for the presentation and valuable insights into quantization. Okay, we have a question. Is there open source code for analyzing complex CNN architectures?
Sorry, open source for the more complex CNN architectures?
Yes, open source code for analyzing complex CNN architecture.
I haven't actually started those experiments yet, so there's currently isn't any code on the complex CNN ones at the moment. It's still the more simple VGG like and MobileNet like architectures. I did have some experiments on, I think it was ResNet 32, and so that code would be online. I haven't actually released the GitHub like made it public yet though.
Okay, so the results for ResNet 152 will be presented in the next mobile AI workshop.
Yeah, okay, hopefully.
Okay, good. Okay, any other questions? Okay, if no other questions, then thanks a lot for the presentation.
Okay, great. Thanks a lot. Thanks for having me.
Thank you. And now we have a talk about layer importance estimation with imprinting for neural network quantization from Hong Kong Liu.
Hello, can you guys hear me?
Yes.
All right, I'll share my screen.
Mhm.
And also, I also record a video beforehand, so just to make things easier.
Hello, everyone. I'll talk about our paper, layer importance estimation with imprinting for neural network quantization. So we already know that there are a lot of ways to make a neural network more efficient on mobile devices. For example, you can use architecture design, you can use knowledge distillation, you can use pruning or quantization. So I'll talk about quantization here. So quantization is a method to compress the model using low precision instead of full precision. For example, you can use 8-bit, 4-bit, or even binary numbers. So it involves projecting a real number to discrete number. So numbers within a certain range or certain interval are projected to the CN number. To choose that projection range or interval, there are different schemas. You can project the numbers uniformly. However, since the distribution of weights is bell-shaped, it is much better to use non-uniform schemas. Some paper use power of 2 values instead. Some paper, there is also a method with APOT, additive power of 2, which focus more on the center of the distribution compared to power of t values. However, all these paper proposed methods are using fixed precision only. We already know that different layers in a neural network may contain different level of information. So it does make sense to use mixed precision to treat a layer differently, right? Therefore, there is mixed precision quantization. However, for those quantization, there is usually a search process involved. So that search usually takes a long time, and there is usually no meaningful interpretation of why or how the algorithm comes up with that configuration. To address these problems, we have our method importance estimation with imprinting. So we have 2 steps. So first step is the bit selection with imprinting, and the next step is to apply the configuration that our selection algorithm found to any quantization method. So for select the billets, we'll add a hat or a neural network to each layer. So this is just a small, fully connected classification network. And instead of actually training the network, we calculate the weights using imprinting. So the weights is estimated with imprinting with only 1 epoch. So if you want to know more about imprinting, you can read the paper. So with imprinting, we will get the accuracy for that layer. So once we have this for each layer, we'll get a graph like this. So this means accuracy for what's the accuracy will be if we exit at this layer. And if you look deeply into the graph here, you can see these 2 layers have exactly the same accuracy, which means the later layer, the COM 8.2, has exactly the same level of information contained in 8.2. So that means this layer is safe to quantize the second layer. So here I choose this layer to be quantized. Once we quantize this layer, that means we want to reduce the bit of this layer. So once we reduce it by 1, we'll run the algorithm again and to on another layer to reduce its valence. And we'll do this until we reach a certain threshold, for example, until we reach a memory constraint or average valence constraint. So once we get that, final configuration, we'll apply it to quantization method. Here we apply to APOT method, and you can see one thing about APOT method is that they require a progressive fine-tuning. That means if you want to reach a level of 2, like average valence of 2, you have to start with average valence of 4 and then go to average valence of 3. Then you go to averages. Then you train another, fine-tune another 300 epochs to get a accuracy of a better accuracy for lower valence. However, with our method, you don't have to fine-tune that much. You just need the final valence and then train that. And once we apply our method, you can see that the accuracy of is not hurt that much. We also apply our method to POT and uniform quantization and compare it with other state-of-art methods. And our method still looks promising. The result is still relatively high. So the conclusion is our method has the ability to further compress any fixed precision quantization to a mixed precision without hurting the performance much. We also give a better interpretation of why we choose the final valence configuration. And the one-shot imprinting method makes it faster to decide the valence compared to other search methods out there. And thanks for listening. That's my presentation.
All right.
Thanks for the presentation. Are there any questions to the speaker? Okay, looks like there are no major questions, which means that everyone understood everything. So therefore, thanks a lot for the talk. And we'll then move to the next presentation. Computer vision-based assistant system for the visually impaired using mobile edge AI. The presentation will be given by Jagadish Mahendran. So welcome. I hope that I pronounced you correctly. So you can
Yes,
start.
that was correct. Yeah, thanks, Andre. Can you hear me?
Yes, yes.
Yeah, let me share my screen. Can you see my screen?
Yes. Yes, yes.
Yeah. Yeah, so in this work, we present a computer vision-based assistant system for the visually impaired using mobile edge AI. So we developed a solution that is cost-effective and unobtrusive, that is capable of running deep learning models and point cloud processing methods for scene understanding. We're able to significantly reduce the form factor and cost using edge AI devices, and we're also able to achieve a higher inference rate using a model optimization technique. So here is a physical setup. The setup consists of OPPO camera that is concealed behind the vest. Along with the OPPO camera is capable of running AI models that is being collected before sent to the host machine. The sensor is further connected to the laptop in the backpack. The laptop is further connected to 2 neural compute sticks for AI processing. For localization, we utilized a USB-enabled GPS. And for user interface, we used the Bluetooth-enabled earphones. So this is our overall system. Primitive perception is used for detecting obstacle presence, and advanced perception is used for detecting and performing complex scene understanding. And we also utilized a GPS-based localizer. For user interface, we utilized voice recognition, text-to-speech, and SMS module. SMS modules were used for exchanging GPS coordinates with preferred contacts in case of emergencies. So in primitive perception, the field of view is divided into multiple grids, and each grid is further processed to count the occurrences of points within certain range of the user. In case of presence of an obstacle, we fit a cuboid to approximate the size and shape of the obstacle. And also, in case of presence of an obstacle, the user is updated about the location of the obstacle with respect to the center of the user. So in this case, we present a scenario where the system is able to recognize thin obstacles such as electric wire on the sidewalk. So this is a use case where the system is able to recognize hanging obstacles such as branches extending into the sidewalk. So in advanced perception is used for performing complex scene understanding. This module is used for understanding traffic conditions by running crosswalk detection and traffic signs and traffic lights. We also developed a machine learning model for detecting elevation changes. To achieve this, we had to collect two classes of data set by walking. One is the sidewalk data set. This data set was collected by walking in the neighboring streets of Monrovia City. It's comprised of 600 images. The other class is the curve data set, which was utilized for training a machine learning model for detecting elevation changes. And to detect elevation changes, we trained a couple of mini VGGNet for faster inferencing rate. Along with this, we also use the standard traffic data sets such as LISA and German traffic set, along with subset of Google Open Images. So this is our overall object detection pipeline. We used two SST MobileNet-based object detection models. One is a pre-trained model from OPPO's Depth AI, trained on Pascal dataset, and other is a custom dataset, custom object detection model. So sometimes these models tend to produce false positives, which was further reduced by training a traffic signet model. The structure is shown here. Once the false positives are reduced, we look if the detection contains traffic sign detections. In case of a traffic sign detections, we trained another traffic signet model to classify into further categories such as stop signs or pedestrian crossing or sidewalks closed. Here is a sample detection where the system is able to detect various classes such as traffic lights, yellow pavement, stop signs, fire hydrants, and so on. And we also performed semantic segmentation for understanding road conditions. We particularly used road semantic segmentation ADAS model from OpenVINO to recognize crosswalk. We separated the road markings from the detections and performed further image processing techniques such as dilations, aspect ratio calculations, and eccentricity calculation to separate the crosswalk lines from the rest of the image. This is the overall performance of the system, where we are able to run all the models, including primitive perception, advanced GPS model, and voice recognition, and we are able to achieve up to 10 frames per second. So here's a short demo video which shows the system that is able to describe the surroundings to the user. Note that the presence of obstacles is translated to the user using
Yellow,
clock notation.
10 o'clock, person, 11 o'clock, traffic light, 2 o'clock. Yellow, pavement, 1 o'clock, traffic light, 2 o'clock. Yellow, pavement, 1 traffic light, 11 o'clock. Traffic light, 11 o'clock, car, 2 o'clock.
Yeah, so
Car, 12 o'clock.
So this feature is describing the features to the user is provided only upon request because the focus was paid mainly on user interface. One of the common drawbacks with the existing app is that these apps, continuously bombard the user with a lot of data, and the user lose their focus. So features like this, where the system can provide detailed information of the surroundings, is provided only upon the request. By default, the system will provide only the critical updates, such as presence of obstacles within so and so distance, and any other extra features will be provided only by the request by the user. So that is my end of talk. Any questions?
Okay, thanks a lot for the presentation. So are there any questions to the speaker? Okay, then I will ask you a question. Have you really tested this? Oh, okay. There is a question on how was false negative testing early on?
Is it for the background classification?
Okay, yeah, is it for the background classification? Storm you.
Yeah. So the idea is like, so the object detection models generally tend to provide false positive. So what we did was we collected the data set and separated this part of images that does not belong to the object. And generally we end up with having a bunch of data set for background because it's easily available. And this uneven distribution of background and the foreground data set was kind of equalized by removing extra background data set, and we trained this reduced background data set using the traffic signet model, which contained only two classes, which is background and the object, right? And this particular traffic signet model can just distinguish whether this image contains a foreground object or a background information.
Oh, nice, yeah.
Okay, thanks a lot for answering the questions.
Thank you.
Thanks a lot for the talk. And if there are no questions, then we're moving to the next presentation. And the next presentation is, thank you too, is real-time segmentation-based context-aware scene text detection. And this presentation is from InnoPeak Technology and will be given by Jashan Lee. Jashan Lee, welcome.
Okay, so I'll play the video. Hello, everyone. This talk is about RSCE, real-time segmentation-based context-aware syntax detection. So syntax detection is about to detect all the text instance in different indoor and outdoor scenarios. And it has been deployed on a lot of mobile apps. So current state-of-the-art deep learning-based solutions follow the segmentation-based models, like this PSENet, which first segments the text foreground areas, and then reconstructs text instance from segmentation results by some post-processing. However, current segmentation-based model suffer from two problems. One is that the length of the modeling on curved text instance, because common convolution and the pooling layers only operate with fixed geometry structures, which will limit its performance on arbitrary shift text detection. Another one is current models requires complex label generation and assignment rules, which usually requires many handcrafted parameters with grid search on different benchmarks, and it limits its generalization ability on different scenarios. So based on these two observations, we proposed RSA, a real-time segmentation-based context-aware syntax detector, which adds local context-aware upsampling to make up the weakness of modeling of curve test of original segmentation-based models. By simply adding a context-aware upsampling module, which upsampling weighs on different locations. So for more details, this figure shows how the context-aware upsampling works for modeling curve test area. It operates with different weights on different locations, and we compared it with other common upsamplers like nearness neighbors and bilinear interpolation and the deconvolution layers. Experiments shows that local context-aware upsampling performs better for curve test detection. And also to simplify label generation and assignment, we simply use shrink text instance ground truth as foreground area for training the segmentation network. And different from previous methods that use fixed text spine shrink ratios. Here we use a dynamic text spine labeling method, which adaptively increase the shrink ratios as the training goes on. The shrink ratios increases as the training epochs goes. So which makes the network to learn samples from the easy ones to the hard ones. The experiment shows that dynamic text spine labeling outperforms fixed ones with appropriate range setting of the shrink ratios. So we mainly conduct our experiments on two curve test detection datasets, the CTW 1500 and also the total text. Well, in both that we reaches competitive results with real-time inference speed. Well, we also conduct experiments on multi-oriented test detection datasets like MSRA TD500 and IGDA 2015. Well, we also reach comparable results with other state-of-the-art method. So it shows that our model can handle both the curve detection and the multi-oriented test detection. And you may refer to our paper for more experimental details. And here are some visualization of detections on the CTW 1500 dataset. It shows that our model can accurately detect most of the curve test instance in different things, while including text on a billboard or some traffic sign or some slogans. Well, that's all for our presentation today, and thanks for listening. Okay, that's all of our presentation, and any questions?
So thanks for the presentation. Do we have any questions to the speaker? Okay, looks like everything was clear. Therefore, thanks a lot for the presentation, and we are moving to the next paper. The next paper is real-time analog Gauge transcriptor on mobile phone. The paper will be presented by Ben Howells from University of Cambridge.
Hello, Andre, can you hear me all right?
Yes, we can hear you.
Great. 1 second. Awesome, can you see my screen as well?
Yes.
Cool, I'll make a start. Okay, so our paper is real-time analog gauge transcription on mobile phone. My name is Ben Howells. Co-authors were James Charles and Roberto Cipolla, and we're from the Cambridge University Engineering Department. So what was the problem we're trying to solve? Well, industry is currently moving through its fourth revolution, driven by automation, big data, and artificial intelligence. And there are many industrial plants which still have a wealth of old machinery using analog instrumentation. And in order to interface this with digital monitoring solutions, plants must modernize by either replacing or retrofitting these machines. Replacing machines comes at a huge financial and environmental cost, and this is the problem we're trying to solve. So what's our solution? Well, we propose retrofitting these machines by building a sensor that can automatically transcribe an analog gauge to interface with a digital system. This should work in real time via a live camera feed and on mobile devices to demonstrate it's a lightweight solution. Why is this difficult? Well, for several reasons. Gauges have a high variability in style and appearance, meaning they have to be interpreted individually. Due to the materials they're typically made out of, which is either metal or glass, they can suffer from lots of glare, and also parallax errors can arise from viewing from a non-face-on angle. So this is how we tackle the task. So we have an image here, and the first thing we want to do is detect where the gauge is using a bounding box, and we call this stage 1 of our system. You'll then notice in this image that the gauge is captured from a non-face-on angle. So to account for perspective distortion effects and parallax error, we want to recover pose. So we imagine the gauge is on a virtual plane, as you can see here, and we detect the 4 corners of this plane, which bound the gauge. We then assume that these will warp to a perfect square in a face-on view, and from this we can infer a homography matrix, which can be used to produce a rectified image of the gauge. We can then detect 4 further key points corresponding to the scale minimum, the scale maximum, the pointer center, and the pointer tip, and use basic geometry to find the position of the pointer tip, the position of the scale maximum, and use a linear interpolation to find the true gauge reading, provided we know the scale minimum and maximum values through OCR detection or manual entering. We use deep learning as part of this pipeline, so we began with a high-res source image, and we downsample this to a 1192 by 192 image pixel input, and we fed this into our first convolutional neural network. This gives us a bounding box for gauge detection, and it also gives us some perspective key points, which were used alongside our original high-res source image to produce a rectified image. This accounted for perspective correction. We then used this rectified image as an input to a second neural network, which then produced gauge reading key points. You'll notice here that we have 2 convolutional neural networks with 2 input images, and the reason we do this is to keep input image resolution low. So we have a high computational efficiency for mobile, while also ensuring we have a high quality image for stage 3 for accurate reading. The CNNs we use were based off a single stage framework called CenterNet, which detects objects as key points, and we used a MobileNet v2 backbone. To train the networks, we used a synthetic image dataset, which comprised of 10,000 train images and 1,000 test images. This is one of the largest and most varied gauge datasets out there, and we built this using a custom synthesizer with 3D gauge CAD models on real image backgrounds. To evaluate our system, we used some real image datasets, so alongside a publicly available dataset, which consisted of 7 gauges, we also produced our own. And this could be split into 3 different evaluation tasks: gauge detections, which comprise of gauges on various different backgrounds, pose recovery to measure read error sensitivity as a function of camera angle, and gauge reading to measure read error. So we measured performance of this on our data set, and for gauge detection, we measured detection accuracy, which was the proportion of images we could correctly detect whether a gauge was in an image or not, and we found this close to be 100%. And we also measured how accurately we could predict the bounding box center compared to the ground truth, and found this to be very small errors at only 35.4 pixels compared to the average width of a gauge in the image around 1,000. We measured sensitivity to camera angle, so the blue line in this graph measures detection accuracy, which is whether we could detect a gauge in an image, and obviously the higher the better, and the red line measures angular read error, so how accurately we could measure the angle of the pointer of the gauge, and so the lower the better. And so for 0 degrees, which is a face-on camera angle, we could see performance is very strong, and this allowed us to define a safe operating region for our system. Finally, we measured gauge reading, so we compared our system to a baseline method that used traditional computer vision techniques, and we found that our system generalized to unseen gauges much better and was significantly more accurate at reading any type of gauge. So we ported our system onto iOS devices, so models were converted into Core ML, and an app was developed using Xcode. Our system runs at 100 frames per second on iPad Pro and takes advantage of the neural engine. In this app, you can see that bounding boxes are visualized in red, pose recovery key points are visualized in the green box, and the resulting rectified image is shown in the left of the screen. Currently, the user manually enters the scale minimum and maximum values, and the reading is output automatically, and this value is temporally averaged over 30 frames. So you can see that the system's working for a variety of different unseen gauges, and it's important to stress that the model was trained entirely with synthetic data, so domain adaptation is working very well. So to summarize with our contributions, so we've built a state-of-the-art analog gauge transcription system. It's been ported onto iOS devices running at 100 frames per second. Both the synthetic image dataset and the real image dataset we've produced have been publicly released, and you can download them here. And we're also working on some future work around OCR detection and investigating different system architectures. So if you've got any questions, either ask them now or please direct them to myself or James Charles, and the emails are on screen. Thank you.
Thank you for the presentation. Are there any questions? Do you have any questions? Okay, I will now ask you a question. So this project, was it developed for some, is it actually a commercial project? And was it
no, at the moment it was just developed as part of like an academic project, but you know, in the future possibly.
Okay, and I mean, how this, well, so you are solving the problem of gauge of detection the values of detecting the values that are shown, and where do you plan to use the solution?
So as I said, probably the best thing would be retrofitting sort of industrial plants so that we can, rather than replacing old analog machinery, we can sort of interface them with like digital monitoring solutions to bring anything into sort of a more automated platform.
Okay, interesting. Yeah, because I didn't see any similar solutions before in the past. Cool. So this is the first one that I so therefore, yeah, I'm definitely interested in from where the problem came from, and so what is the future? Yes. Okay, thanks a lot for the presentation then, if there are no questions. And then the next talk is stacked deep multi-scale hierarchical network for fast bokeh effect rendering, and the talk will be delivered by Saika Dutta. Okay, just one thing, if when playing the video, you need to select the option to share the sound with the audience. Because we cannot hear now anything. Okay, to avoid the delays, I will play the video myself because I also have its copy. Oh, if you have started. No, we still cannot hear anything. Oh, yeah.
Hello everyone. Today I'm going to present our work, Stacked Deep Multiscale Hierarchical Network for Fast Bokeh Effect Rendering from a Single Image. Bokeh effect is a desirable property in photography for creating aesthetics and artistic photos. Usually bokeh images are captured using a DSLR camera with certain settings and needs certain photography skills to capture them. This feature is also available in smartphones these days, and computational methods and additional sensors are used for creating such effects. Most of the existing deep learning based techniques use pre-trained depth estimation networks and saliency detection networks for bokeh effect synthesis. Because of these reasons, the bokeh effect synthesis networks have many parameters and become runtime intensive. To this end, we propose a deep multiscale hierarchical network for bokeh effect rendering from RGB data. To further improve the perceptual quality of the synthesized bokeh effect, we stack two DMSHN modules to form a stacked DMSHN network. Our models do not rely on any monocular depth estimates or saliency detection. Hence, our model is lightweight and have significantly less number of parameters. This is our DMSHN architecture for bokeh effect rendering. DMSHN architecture is based on 3-level image pyramid. Each level consists of a encoder and decoder pair. Decoder output of one level is fed residually to the encoder of next level. Encoded features of one level is upscaled and added to the encoded feature of next level before feeding it to the decoder. Our stack DMSHN architecture consists of two DMSHN modules cascaded. We have used everything is better with bokeh or EBB dataset in our work. The official training set consists of almost 5K image pairs of bokeh-free and bokeh images. These are a few sample bokeh and bokeh-free image pairs from this dataset. We have used VAL294 set for evaluation in our work. Our DMSHN network is trained in two stages. In the first stage, we have used a linear combination of L1 and SSIM loss as our loss function. In the stage 2, we have fine-tuned our model using MS-SSIM loss. For training of stacked DMSHN network, we have first loaded the weights of pre-trained DMSHN model and fine-tuned the network using MS-SSIM. We have used 4 evaluation metrics in our work, such as PSNR, SSIM, LPIPS, and mean opinion score. Here are some quantitative results. We can see that stacked DMSHN achieves better results than DMSHN. Also, stacked DMSHN achieves best SSIM score on VAL294 set and close to state-of-the-art accuracy on other metrics. Here are some qualitative results on VAL294 set. We can see that DMSHN achieves the best runtime among the other methods, while stacked DMSHN also performs the second best runtime. We can also note that the parameters in DMSHN and stacked DMSHN are significantly less than the state-of-the-art PyNet. Our models are also deployable in mobile devices. We have tested our models on AI benchmark Android application on 3 different devices. Here are the runtimes of our models on those devices. Finally, we have proposed 2 networks, namely DMSHN and stacked DMSHN for bokeh effect rendering. Our models do not rely on depth estimation or saliency map detection. We can see that DMSHN is outperformed by stacked DMSHN both qualitatively and quantitatively, whereas stacked DMSHN yields close to state-of-the-art accuracy in VAL294 dataset. Our methods are lightweight and efficient. We have also showed that our models are deployable in mid-range smartphones. In future, we can also use dense connections and spatial attention to further improve the perceptual quality in bokeh images. Here are some references. You can look into our code and models by scanning in this QR code. Thank you.
Thank you for the presentation. Are there any questions to the speaker? Okay, and I think I just missed this part. On which devices did you evaluate the runtime? As I got, we cannot hear you. I think you need, no, you're not muted.
Hello, can you hear me?
Yes. Yeah.
So the device details are mentioned in this paper. Actually, the chipset details are there. So these were on 2 Xiaomi phones and 1 OnePlus phone.
And you were running the models with which acceleration option?
Sorry?
You accelerate. You run this model on CPU or with acceleration?
With acceleration.
With an enable.
What? Sorry?
With an API or on GPU?
No, it was like a TF-led GPU delivered.
Mm-hmm. Okay, the results looking good.
Yes.
So hope to see the improved version of this book that is faster and shows even better results on the data set.
Yes.
Okay, do we have questions from the other attendees? No, I don't think so. Therefore, thanks a lot for the presentation. And we move to the next talk, which is filtering empty camera trap images in embedded systems. And the talk will be delivered by Fagner Kunha.
Hello.
Hello.
Just if I can share the screen.
Mm-hmm.
Can you see my screen?
Yes, yes.
Okay. Hello, everyone. My name is Fagner Cunha. I'm a PhD student at Federal University of Amazonas, and I present the paper Filtering Empty Camera Trap Images in Embedded Systems. Camera trap are cameras triggered by presence sensors used for passive wildlife monitoring. Usually, researchers program these cameras to capture from 3 to 10 images per capture event. However, it is very common to have a large amount of images with no animal. On snapshot setting at dataset, for instance, about 75% of the images are empty. Embedding deep learning models to filter empty images directly on those cameras brings advantages such as savings in the storage and transmission of data, usually resource constrained in this type of equipment. In the last years, deep learning models have been applied to extract information from camera trap images. Some of these works analyze CNNs of varied complexities. In fact, ResNet 18 has become one of the most used models due to its small complexity. However, there are just a few studies regarding the trade-off between model performance and inference latency directly on edge devices. Tilden and Olson compared SSD and SSD Lite running on a Raspberry Pi. Zuckerman et al. Studied classifiers, but only evaluated the best one on Raspberry Pi. Snyder et al. Suggest that detection models would work better than classifiers, but no experiments were conducted to evaluate that. In this paper, we conduct a comparative study on animal recognition models to analyze the trade-off between precision and inference latency on edge devices. Specifically, we compare classifiers and detectors and also apply some models optimizations. As reference hardware, we choose Raspberry Pi, representing a low-cost platform. For our experiments, we use 2 public datasets, Snapshot Seringet and Caltech. To have a fair comparison regarding the amount of data used during training, all images from non-empty class have bounding boxes labels. Besides, the amount of images used are just a small subset of the total data available. This number can provide a more realistic perspective of the problem, since the vast majority of small-scale research projects on camera trap do not have a large amount of labeled images. For classifiers, we use MobileNet v2 and EfficientNet v0 and v3. For detectors, we use SSD Lite with MobileNet v2 as backbone and EfficientNet v0. To compare detectors with classifiers, we consider the confidence of the bounding box with the highest score as the detector confidence on animal as detector confidence on have an animal on that image. Our results show that, in fact, detectors are better than classifiers for the problem of filtering empty camera trap images. Considering a recall level of 96% for the non-empty class, SSD Lite can eliminate 10% more empty images than classifiers with comparable latency. This is also true when using the same input resolution. Consider that labeling with bounding box is time consuming, and some projects do have a large amount of labeled images for classification. We evaluated classifiers trained with about 1 million images. In this situation, classifiers are able to reach results comparable to detectors, but with half latency. Finally, we also applied some model optimizations, such as quantization and reduction of network width. See more details about this on paper. Here are some sample results. The bounding box represents are for better visualization of the animals. As you can see, they are very challenging pictures. We made our code and models publicly available. Thanks for listening.
Thanks for the presentation. Are there any questions to the speaker? Okay, then I have one question again. How are you planning to use the obtained system for some commercial activity, for some commercial applications? Or maybe you already have partnership with someone who needs this solution?
Actually, I've had already participated in a project to use to classify animals. So I developed some projects on this, but at that time we had no concerns about latency. So we have 2 seconds to predict. So it was too long time, but now we decided to study this, but this project specifically just for academic purpose. There is no partnership with the previous institute.
Okay, well, it's always interesting to apply the obtained solution to some real in practice. So yes, therefore I was asking this question. Okay. Are there any other questions? Okay, looks like there are no further questions. And then we move to the last talk, deep shift towards multiplication-less neural networks. The talk will be presented by Mustafa Al-Haushi from Huawei Technologies. Mustafa, welcome.
Hello. Hello, can you hear me?
Yes, we can hear and see the slides.
Okay. So hello everyone, and thank you for staying to the last presentation. So I'm presenting Deep Shift, which was done along with my colleagues in Huawei. Yeah, the main takeaway from this paper is we would like to replace multiplications that happen in convolution or matmults with bitwise shift. Why? Basically, a bitwise shift, when you let's say you have a fixed point or integer value that is shifted to the left by p bits, it is equivalent to multiplying by 2 to the power of p. And if you're going to shift to the right, it's p would be equivalent to multiplying by 2 to the power of p, where p is a negative number. And we also need to add a sign bit as well to deal with positive or negative values. So why do we do this? The idea is that if we're going to represent operations at bitwise shift, we require fewer bits to represent the weights. So a 32-bit floating point value can be replaced with a 5 or 6-bit or even 4-bit shift value. And also another reason is that bitwise shifts are much are faster than multiplication. So given a certain processor here, we can see that in terms of power, bitwise shift is as much as power than 32-bit floating point multiplication, fewer transistor counts and fewer clock cycle latency. So now the question is how do you going to train the model, and whether are we going to get decent accuracy or not? So we propose two methods to train these shift-based models, deep shift Q and deep shift PS. Deep shift Q is basically it's similar to what most quantization papers do. We round the weights. Here we round it to power of 2. In the forward pass, we could apply this quantized weight on the activation. In the backward pass, we use the quantized weights on the gradients, and then during update, we update the high precision weights. This is what most quantization methods do. Deep shift PS is a bit different. Here the weights themselves are actually, or the trainable parameters or learnable parameters are the actual power and sign. So power and sign, they will be during training, they can be any value, but in order to apply the forward pass, we need to round the power of 2, and need to round the sign, because sign can either be here the sign is ternary sign, could be -1, 0, or +1, and then we express the weights as to the power of p, which is the bitwise shift and the sign operation. And in the backward pass, we apply, we learn or upgrade the P and S values, and also we update them here. So in terms of accuracy, we're going to show results on different data sets. We're going to show results for training from scratch as well as training from a pre-trained model. So MNIST is an easy one, so everybody can get high results on it. So I'll skip this. CFAR 10, ResNet 18. So training from scratch, we obtain very close accuracy to the baseline, and pre-trained as well. I also tested mobile net v2. So we see sometimes that deep shift Q is doing better than PS in this scenario. However, when we try, so we also tried to represent the weight bits using fewer bits. So instead of just 5 bits, we try 4 bits, 3 bits, or 2 bits. And we also tried to, instead of using 32-bit fixed point activation, we tried 16 bits and 8 bits as well. So we noticed that for fewer bits and training from scratch, deep shift PS does better for fewer weight bits, but for fewer activation bits, deep shift Q performs better. And here is the training from scratch using on ResNet 18. The black line is the baseline, and this is deep shift Q and deep shift PS. Yeah, so now I'm showing ImageNet results. So for training from scratch, there's a drop of around 4% in accuracy. But training from pre-trained, we almost reach the same accuracy as the baseline, ResNet 18. For GoogleNet, we actually, when training from pre-trained, we actually exceed the baseline accuracy. Okay, what about computation performance? Can we save latency or power? So we did create a GPU CUDA kernel that will implement the two does implement. We implement two one kernel for matrix multiplication, another kernel for convolution. That where the number of bits is variable, it can change from 2 bits to 6 bits. And what we do, in order to speed up the inference, we pack a group of shift values into one 32-bit integer. So we have one big 32-bit integer which contains, let's say, if we use the 4-bit shift and 1-bit sign, so one 32-bit integer can contain more than 4 or 5 different shift weights, and this packing will speed up the operation. And doing here the inference of the whole validation that's in the ResNet 18, we created our own for a fair comparison. We created our own regular multiplication based kernel, and we compared it and compared to our own bitwise shift kernel, so we achieve around like 25% speed up. We'd like to mention, if we compare this latency with highly optimized cuDNN kernels, will be much slower. The reason is that we need to apply all different optimizations and kernel fusion and tuning of the tiling parameters and so on. So a lot needs to be done if we want to achieve the same accuracy, same performance as the highly optimized cuDNN kernels. So to make a fair comparison, we created one multiplication-based kernel, and I just made minor modifications to make it a shift-based kernel. For CPU, there's a challenge to get speed up on CPU, because we would like to have we need to have like a vector instruction where we if you want to compare the CPU-based bit shift with the current CPU kernels, we need to have a vector instructions where we have a vector of activation and a vector of shifts, and to apply this against them, and this currently doesn't exist. Currently, I think with Intel processors, we have a vector structure where we have a vector of activations, but only one single shift value, which is applied on all the elements of the vector, and this is not what we need. Okay, how do you compare with other papers? So there have been papers that replace multiplication. So we have bitwise networks and ternary networks ABC. They replace multiplications with XOR operations. There's also another paper published in ICLR back in 2017 that uses powers of 2. That does replace multiplication with powers of 2, so it is very similar to ours. So now we're going to compare against them. Yeah, so we do use more bits than bitwise shift ternary-wise, but we have a single operation as well, bitwise shift. So we do have higher accuracy if we train from scratch. So the question is, how do you compare against a similar paper? INQ does like round the weights of a model to powers of 2, but this method can only work with can only speed up inference. It cannot speed up training because the way INQ works is that it takes a portion of the weights, converts them to powers of 2, and then trains the unrounded portion, and the round portion stays fixed. So so this we cannot use. So during training we are not. We are still using multiplication. So, but I'm comparing the accuracy of on different models. Our method with INQ or ABC. ABC only showed results for ResNet 18, and for the same. And here I'm comparing the same number of bits, 4 bits or specifically 5 bits. For if I use 5-bit weights, by 5-bit weights I mean we're using 1 bit for sign and 4 bits for shift. So. VGG GoogleNet, we do have a higher of accuracy. ResNet 15, ResNet 18 we have lower, and AlexNet we also have lower. So yeah, the conclusion like to the best of our knowledge, this is the first paper to train models from bitwise shift. There has been previous works that do influence bitwise shift, but we are the first to do training, and we showed results on 2 different approaches to train deep shift Q and deep shift PS. Yeah, for the future, we could do more hyperparameter tuning to improve the results, and we need to investigate modifications to hardware to exploit the method and get a better performance on hardware. And thank you very much for attending. We have I would like to encourage you all to visit our GitHub page. Actually, it has been active for a while. our GitHub profile was on there for about a year, and we have received, like, many people have been cloning it and trying it. And actually, there have been different papers that published methods based on our solution. And yeah, you can find in our GitHub all the results and how to reproduce every result in the paper as well. And thank you for all the organizers of the workshop, and especially thanks to Andrea. And yeah, I'm open to any questions.
Thank you too for the presentation. Yes, we have a question. We have a question from Stone Young. Do you think modifying the straight-through estimator equations used could help to improve the training of deep shift PS from scratch?
Definitely, yes. I think there's a lot of area for improvement. I haven't thought much about straight-through estimators. APOT, I have looked at APOT. They made modification. I think APOT, they added an additional learning parameter, which is alpha, the clipping value. In my case, I haven't done it. So yeah, I think maybe revisiting the straight-through estimator and maybe adding a trainable clipping parameter might help as well. And also APOT, they used weight normalization. And when I played around with the repo, weight normalization was very important for them. When weight normalization is removed, the accuracy collapses. To clarify, training bits from scratch with 8 bits and 16 bits, activation or deep shift. Yeah, I'm not sure this part of the question, but to clarify,
yeah, just to clarify.
Yeah, okay. I would like to add that I've been using by default 32-bit fixed point. So I've been using 16-bit integer and 16-bit representative floats. For 16 bits, I used 3 bits for the integer and 13 bits for the 30 bits for the fraction. And for 8 bits, I used 3 bits for integer part and 5 bits for the fraction part. Yes.
Okay, thanks for the answer. And one more question. So I saw that you implemented and if you try to implement an efficient solution for desktop CPUs. Have you tried to port this to mobile CPUs, maybe by using ARM Neon, SIMD, or something else? Have you tried, or are you considering to do this?
So I did try CPU. I haven't tried specifically ARM Neon, but I did try CPU, and we didn't get a speed up. Actually, it was slow because we were using our solution will use scalar operations. So will play, but while the existing CPU backends for PyTorch, TensorFlow, or whatever, they use vector instructions. So it will be an unfair comparison. We will compare a scalar bitwise shift with a vector of multiplications. The vector multiplication will be faster because in one clock cycle it does, let's say, 8 or 16 multiplications, while in our case in one clock cycle we're doing 1 bitwise shift, but overall the vector will be faster. So this is why I tried to explain in the presentation that we are hoping to find in the future CPUs that have bitwise shift vector instructions, so that we can get higher speed ups compared to vector multiplications.
Okay. This clarifies everything. Thank you for the answer. And this was the last presentation for today. So right now I hope that you learned quite a lot during this session. You learned quite a lot about how to run the models. You learned quite a lot about different problems and efficient solutions for them. You learned a lot definitely about quantization, about approaches, about caveats, about some ideas how to solve them. And with all this information, you'll be able to go and develop efficient models for mobile devices. So a few notes about organizational notes, final organizational notes. So the recordings of today's presentations, they should be published on our YouTube channel within the next 2 weeks. So as soon as this is done, we'll announce this, we'll send announcements to all registered challenge participants and all registered authors. If you have any questions, you can still write them on the website, on the website forum. So you remember that aibenchmark.net. So you can just go there. If you have some issues with running the models, if you have some issues with converting the models, if you have some general questions, just feel free to register on the forum, post your question, and we'll try to clarify, to provide the answers. Right now, we'll stay here for probably several more minutes in case you have some other questions. And if there are no questions, then that's it for Mobile AI Workshop 2021. And we really hope to see you all at the next Mobile AI Workshop that will happen with the next CVPR conference. And we have already prepared quite a lot of interesting tasks, quite a lot of interesting data sets that will be evaluated using the same manner as this year. So we hope to see you all in our next workshop, in our next challenges. And if you have some other, if there are some questions left for us, you feel free to ask them during the next few minutes.
Thank you very much.
Thank you too.